So now let us see a very important concept, because throughout the course we are going to use these keys things actually. So we are going to have different types of keys. Let us see first of all how many are there, and one by one let us try to understand in each lecture. Okay. So here keys in RDBMS is an attribute or set of attributes which help you to identify tuples in a relation actually. So in a relation, to identify the rows, these keys are going to help you a lot. How and all we will see in the discussion. Okay. And at the same time, they allow you to find the relation between two tables. So these points, just let it be. As we are moving on, we will get the clarity on these points actually. And this is nothing also. Okay. So first of all, let us try to understand how many keys are there in DBMS. Okay, so the important keys. So the very first one is candidate key. What is this one? Let us try to understand separately. And another key is primary key, and the another one is alternate key. So these three have some relation. And the next key is super key. Of course, this also have some relation with this candidate key, and we have a foreign key. So these are the 5 types of keys. Very frequently in many places we are going to refer. Let us try to understand all these keys separately in separate lectures one by one. So first of all, we have 5 different keys are there. Those are these things actually. Of course, we have another keys are also there, that is, for example, surrogate key. So where we will use surrogate key. So whenever, after understanding of these meanings, it will be clear. If you are unable to find the candidate key, this one, if you are unable to find the candidate key, then system is going to generate temporary key actually. So that is called surrogate key. So let it be, we will get the clarity. If you just keep it in mind that what is surrogate key, if you don't have candidate key in the relation, in a table, if you are unable to find the candidate key, then system generated key temporarily it will generate, that is going to become surrogate key. So let it be this one. So let us see in the coming lectures each key separately. Okay. Hi. Now let us try to understand the first key, that is candidate key. Okay. So this is very simple. What is candidate key? Let us try to understand. Basing on this, remaining keys discussion is there actually. So this part we have to understand very clearly. So what is that one? Let us see. So the minimal set of attributes that can uniquely identify a tuple is known as a candidate key. So you say very importantly, unique identification actually. So we are in a relation or in a table, we are going to have a set of records. So the attribute or set of attributes, maybe one attribute or more than one attribute, that must be minimal actually, so that you are in a position to identify uniquely. So let us see what does it mean in the discussion. So the value of the candidate key, very important, is unique and not null. So under the attribute, whichever you selected, attribute one, if I selected as a candidate key. So whatever values you have under this, everything must be unique. So whatever value here you have, that should not repeat. So there is no duplicate values, and it should not be null actually. So every cell must fill with some value. That is candidate key actually. Who are all attributes satisfying this property, that is unique and not null, automatically those are the candidate keys. Simple. So the very standard definition you must remember for the candidate key is the attributes are set of attributes which are satisfying unique and not null is nothing but a candidate key. So for more better clarity, let us take a simple table here. So that is what we are going to take employee table here. So in the employee table, we have a EMP number, e-name, mail ID, Aadhaar number, driving license. So this is just for making you to understand candidate key. We took these attributes actually. Now in this, if you observe, generally if you see, every employee is going to have a one unique number, right? So that is what unique ID he is going to have. So no two employees are going to have same number, same ID. So that is what this is satisfying same this one, right? Uniqueness, and no employee going to have null value. So that means every employee definitely have one ID actually, one number he is definitely have. So null is not going to have in this field. That is why this is one possible candidate key. Is it or not? So that is what, if you take in a relation, EMP number, e-name, mail ID, Aadhaar number, driving license, this part we taken here as a relation. Now EMP number is one possible candidate key. So observe other attributes also. Is there any possibility to have one more candidate key? You can come here. So this is employee ID. Every employee definitely going to have one unique identification national number. So national unique identification number, that is Aadhaar number in India. So every person going to have unique Aadhaar number, right? So that is also satisfying same thing, unique Aadhaar number, and no person with no idea, no person with Aadhaar number, right? So that means no null values here. So even this is also possible candidate. And another one is what? Driving license also. Assume that every employee in your company must have a driving license if you have that constraint. So every driving license number is also unique actually. No two numbers are same. And as we put the constraint, everyone must have a driving license. So no null values. So it is, this field is also satisfying uniqueness and not null. So that is also coming under the driving candidate key actually. So these are the three different candidate keys are possible. Don't combine them. Okay. So then whoever is there in the candidate keys, all will become prime attributes. So in the coming lectures, in many places, we are going to use this term, prime attribute. Candidate key, prime attribute. Who will be the prime attributes? What are all attributes are there in the candidate keys? All will become prime attributes. You can see employee number, Aadhaar number, driving license, all of them is the different candidate keys. So all of them is going to become prime attribute. Basing on these different properties and many things we are going to do in the functional dependency or in the normalization part. So that is why simply try to understand. So if these are the prime attributes, then non-prime attributes, what are the non-prime attributes? Remaining are going to become non-prime attributes. So you can see here, ename is non-prime attribute, mail ID non-prime attribute. So this is what actually, first of all, candidate key, try to understand. So it is very simple, uniqueness. So whichever column, whichever attribute for satisfying uniqueness and not null. So that is nothing but candidate key actually, simply you can say. Okay. Right. So now let us see next key, that is primary key. So if you understand candidate key, it is just a matter of few seconds actually. What is primary key? Nothing is there if you understand the candidate key. So let us see what is its definition. So you can have one or more than one candidate key, is it? So out of all these possible candidate keys, we are just selecting one actually as a primary key. That's it. So that means every primary key is unique plus not null, simply you can say, is it or not? So you can have more than one candidate key, but you are going to have only one primary key. So exactly one primary key we are going to have, exactly one, not more than that. So that primary key is also one of the candidate key. If you have only one candidate key, that is automatically primary key. If you have more than one candidate key, then you select whichever is flexible for you. So for example, whatever we see in the earlier example, same thing if you take. So here, what are all the possible candidate keys? So employee number is one candidate key, Aadhaar number is another candidate key, driving license is another candidate key. So simple thing is that which you will select as a primary key, that is always whatever is flexible for you, that you can select as a primary key. So in a company, for example, taking other number is actually a tedious, or calling with the other number is very tedious, or even with the driving license also. So it's better whatever employee number ID they have, with that only, if you select that as a primary key, then you have a lot of flexibility, right? So that is what, out of all candidate keys, whichever is flexible for us, that we can select as a primary key. So that is what, for example, in this scenario, we selected EMP number as a primary key. So that's it. So that is what actually we are saying. Candidate key part, if it is clear, then primary key is clear actually. So primary key is actually subset or equal to candidate key. And candidate keys may be greater than or equal to 1. But primary key is always exactly 1, not more than that. Is it clear? Hi. So now let us see the next key, that is alternate key. So this is also very simple. We don't need to have much discussion. So we will understand very simply. So you can see, we find candidate keys, and one of them you selected as a primary key. So automatically remaining is calling as a alternate key. That's it, right? So this is very simple. So you can see, so this is the table we are referring, and these are the candidate keys we have, right? And we selected EMP number as a primary key. Then automatically remaining two are going to become alternate keys. So that is what alternate keys are: Aadhaar number and driving license. So these things you can use in different purposes actually. So those things also it will be clear whenever time occurs. We will see actually alternate keys where we will use. Okay, so simply understand that whatever keys are there other than primary key is called as a alternate keys actually. So every alternate key is a candidate key. Every primary key is a candidate key. Okay. Hi. So now let us see the next one. So that is super key. So actually everything is related to candidate keys only. That is why initially only we told, if you understand candidate key, then all other automatically we will understand little changes only. So that is what you can see first of all. So the set of attributes which are giving the unique identity a tuple actually. That means uh, a one attribute or more than one attribute, set of attributes, if they are, if every record is unique under those attributes only, then that is going to become super key simply. Okay, so if you see the table here, so what are the super keys? For example, EMP number is a super key, because under super key, under this column, all values are unique, right? You no need to bother about null, but all values are unique. So that is why this is a super key. And what I can do is EMP number comma ename, even these two also unique, right? So that is what actually 101 Ravi not repeated anywhere, 102 John is not repeated anywhere. So that is what you can observe, that EMP number and ename together I am saying, not individual. So this is also going to become super key. Or for example, Aadhaar number and city. So you can have like this. You just observe that which set of attributes is giving the uniqueness. Those are all going to become the super keys. Okay, so basing on this, what we can discuss is inference point is, the first one is adding 0 or more attributes to the candidate key is going to become super key. So you see, this is the EMP number. So that itself super key. And for the EMP number, if I add one more attribute, that altogether, that combination is also going to become super key. That is why actually, whenever we are discussing the candidate key, if you go back to that definition, candidate key is nothing but we told minimal set actually. Minimal set in the sense, EMP number ename, of course, generating unique combination. But even if you remove the ename also, then still it is generating uniqueness. This is minimal set. Further removing is not possible. So that is why super key. So every candidate key is a super key actually. You can say in that way, right? And at the same time, candidate key is a super key. Every candidate key is a super key, but vice versa need not be true. So here one simple relation you have to understand. So here, let us see here, one simple relation we have to understand. So we are going to have a super keys. In that, some of them is the candidate keys and some of them is the primary key. Only one of the candidate key is the primary key, and remaining all you can take as a alternate keys. Okay, so these two together candidate keys, and for every candidate key if you add anything is the super key. Or even not only no need to add to the candidate key, if any other non-prime attributes combination, if they are generating uniqueness for their combination, then it is also a super key. So simply that is why here candidate key part you no need to mention. Simply set of attributes, if they are generating uniqueness, then that is going to become super key. Okay. Hi. So now let us see very important key, that is foreign key. Okay. So it is very simple actually for understanding foreign. So that means when you can say foreigner. Okay. So if he is not in a native place, he is a foreigner for that place actually, right? So if any outside country person came to India, in India, he is the foreigner. So if Indian went to the USA, in the USA, Indian is the foreigner, right? Simple. He's a native, his origin is at somewhere and you are roaming in some other where. So very simple understanding that you can see foreign keys are the columns of the table, which is used to point to the primary key of another table actually. So in very simple manner, let us try to understand with a simple example. So you can take this employee table. So here we have a employee number, ename, manager, DEPT number. So here EMP number is the primary key. So let it be. Then we have another table, department number, department table. In the department table, department number, department name and location we have. So this is the primary key. If you observe, this attribute is also there in the employee table. So Ravi is working under which department? So take that number 10, go to the department table, find out here he is working under accounts department. So you see here, this is the primary key in the department table. This information, you are referring this information here actually, you are using here. So this value you are referring from here. So that is what actually 10 or 20, 10, 30, 20, all these values are the foreign values. Their native is not in this table actually. Their native is in the department table, simple understanding. So that is why department number is going to become foreign key in an employee table. That attribute in the department table is the primary key. So that is what primary key of another table. Primary key of another table we are using in some other table actually. Sometimes in the same table you can use it, that is not a matter. So you can see here. So this is one simple understanding first of all. So what is foreign key? Foreign key, you are going to use the values which is the primary key in another table actually. So that is what these values you are using here. So Krishna working under which department? So take it's a department number, go to the department table. Here 30 is the research. So Krishna is working under research department. So simply we can say, okay. So that is what actually here, if you see the relation, department table have DEPT number, DNAME location, and employee number, ENAME manager, DEPT number. Actually, one simple discussion is there here. Who is the parent? Who is the child? That means parent table is what? Child table is what? Okay. So here the parent table is this one. From here, this is the source actually. This is actual source. Or for these values, this is the native. So that is why department is going to become parent table. And these values you are using here. So these values are foreign values actually, not here. That is why employee is going to become child table. So this department number, wherever it is existed, in which table existed, that table is going to become parent table. Very simple. So this is one simple discussion. So as we discussed that primary key values, see, it is need not be primary key always. So candidate key values also you can use as foreign key values actually. So in this table, if you have a one candidate key, another candidate key, that you can use in another table as a foreign key. And primary key and foreign key both may exist in the same table also. Here we discussed in different tables. But you can say here employee number and manager. So manager, so who is the manager for John? So 101 employee. Who is 101? Ravi actually. So for the John, manager is Ravi. And who is the manager for Ravi? So another Ravi. So names are same, but person is different because employee number is different. So for this Ravi, who is the manager? 102. 102 who actually? John. So for the Ravi, John is the manager. And for the John, who is the manager? Krishna is the manager. So here these two names are repeated, but the persons are different. So that is what try to understand first of all clearly. So here main thing is what is foreign key. So under foreign key attribute, we are going to use the values. Those are the unique values in some other table or same table. Okay, so you are going to refer wherever that is the candidate key. So department number here foreign key, and this is going to become candidate key. That is nothing but of course in this case primary key actually. So this is what foreign key in many places we are going to use. Let us try to understand very clearly. Okay. Hi. So now let us see very first chapter, that is entity relationship model. Okay. So this is going to give you the overall idea, some idea at least about database actually. So what we are going to study in the further chapters. So first of all, it is going to give some idea actually. So that means some logical structure of the database, how it will be, you are going to understand. Okay. So first of all, what is entity relationship model actually? So entity is one word, relationship is another word actually. Both of them is different. So those two together we are going to understand in this chapter. Okay. So if you see the definition of the ER model, so describe the structure of database with the help of the diagrams, which is known as entity relationship diagram. So very simple understanding. So if you see here, so that is, here you can see it describes the structure of the database with the help of the diagram, simply you can say. So very simple manner. So that meaning is you are going to see logical structure actually. Logical structure of database. Okay. How and all we will see in the discussion. Then an ER model is a design of blueprint. So design or a blueprint of a database. That is nothing but logical structure, right? So that is what, before going to implement, so what you want to implement? First of all, for that, you must have a one blueprint, right? So it is like a blueprint of a house. You want to construct a house. Before constructing it physically, you must have the plan, a design that is nothing but a blueprint. So that is what actually, even for the database also, you must have a blueprint before implementing it. So that is what we are going to study in this ER model. Okay. Then the main components are ER model are entity sets, relationship sets. That is what, as I told, entity is different word, relationship is a different word. So we are going to have some set of entities, some set of relationships. We will get the more clarity. This is just for namesake. I am giving the points here, but as we are discussing more, then we will understand this line, especially its meaning. Okay. Overall, in this chapter, what we are going to study, the main thing is ER model. Under ER model, the main three categories we are going to study. One is entity, another one is attribute, another one is relationship. Under the entity, we are going to see the regular entity or strong entity, like that we are going to see. And another one is weak entity. So this is nothing but strong entity also, you can say. So that weak entity we are going to have. And now under the attribute part, key attribute, then composite attribute, single valued attribute, multi-valued attributes, stored attributes, and derived attributes. So these are all very simple, as name implies, their meanings also going to be there. So we will understand in simple manner. Okay. And then we see the relationships, one-to-one, one-to-many, many-to-one, and many-to-many, all possible combinations with one and many. Okay. And along with this, we are going to see the partial participation and total participation. So that also, if you see, partial participation and total participation. So if you are able to understand all these concepts, then we are able to construct the diagrams actually. That is nothing but blueprint of a database. We are going to construct actually basing on the requirement. Okay. So in the coming chapters, let us try to understand first of all these meanings. And at the end, we will try to construct for a simple databases, how to construct its blueprint in the form of diagrams we are going to understand. Okay. Hi. So now let us see the first definition, that is entity. Okay. So what is meaning of entity actually? So you can see here, first of all, an entity is an object or component of a data. Okay. So don't confuse about this name. So entity we can say simply as a table, as a layman discussion. So table is what actually set of records. So we are going to have set of records, right? So what does it mean? For example, if I take EMP table, so we are going to have a EMP number, E name, for example, salary we have. So let us take simple words. So EMP number 1, ABC is the E name and salary is 500, for example. And 2, XYZ and salary is 600. So you can see this is one table, right? So this is one entity, you can say. And sometimes this column you can say as a entity. Sometimes this record as a entity. So that is actually, so most of the places you can say table as an entity, but depends on the situation, its meaning will change it. But we will understand automatically actually. So this is one instance, you can say this record is actually one instance in the entity. When you say this EMP calling as an entity. Okay, so that is why don't bother about the definition. So it is just a object or component of a data. Yes, this overall you can call as a data, or this single row calling as a data, or this single column calling as a data. That is what actually. That is why anything is going to become an entity basing on the situation. But most of the times we can say one table, that means this whole complete set of records together with column names, we are calling as a entity actually. In the most of the places we will use actually. Okay. So how you can represent a one entity is with a rectangle actually. So for example, if you see student is one entity. So in the student, we may have the attributes like student number, student name, student grade, address, phone number. Also, all these things are going to become entity actually. So if you take another entity, college. So college ID, college name, address, and what are all branches it is providing. So that is going to become another entity. So this is what actually simply a entity. Okay. Now from this, as we've seen already, we have another definition that is weak entity. So as we've seen already different keys in the previous lectures, so that is a primary key, candidate key. So when an entity is going to become a weak entity. So for example, student, if you take, in this, we have a student number. So, or you can say roll number, that is simply in simple words. So roll number is actually what actually every student you can identify uniquely. So that means it have a key actually, that is what a primary key. So which table have a key that is going to become strong entity. Okay, strong entity meaning is what? An entity with primary key. So out of all the columns, what are all columns we have? One of the column or combination of the columns, we are able to identify primary key actually. So such an entity we are calling as a strong entity. Fine. Now when it become weak entity, so you can see now an entity that cannot be uniquely identified by its own attributes is the weak entity. So that means there is no primary key. We are unable to identify any attribute or combination of attributes together with as a primary key actually. So such a entities we are calling as a weak entities. So that we are going to represent. So it relies on the relationship with other entities actually. So to identify the records uniquely, it depends on the other entities. That part we will get the clarity in the discussion. So that we are going to represent with a double rectangle. So that is what, for example, if you take bank account. So for example, in a organization, for every employee, bank account we have to take. So one employee may give one bank account, so XYZ bank account, and another employee may give another bank account. So like, for example, one employee given ICICI. Okay. So another employee given HDFC bank's account. Another employee given, so SBI bank account. So like this, if you see, they given 1, 2, 3. For example, in the HDFC also you may have 1, 2, 3. Is it or not? So in SBI, for example, 5, 6, 7. So you can see we are unable to identify each bank account uniquely. So that is why simply just taking the bank account, you cannot identify them uniquely. So you may have the bank name. So if you have the bank name, so this is under SBI, ICICI, this is under HDFC. Now together we are able to form uniquely. So that is what actually this entity is going to become weak entity, and by adding this bank entity to this one, it is going to become you are able to identify uniquely actually. That is what it relies on the relationship. We are going to have a relationship with the other entity so that you can identify all the records uniquely. So that part you will get the clarity more. Here simply try to understand that you don't have simply a primary key in the entity. Such a entities we are calling as a weak entity. Okay, so that is what overall entity meaning, strong entity and weak entity. Okay. Hi. So now let us see the next definition, very, very important one, that is attribute. Okay. So what is meaning of an attribute? So this is not big thing actually. So we might already seen that. So what is meaning of an attribute? Attribute describe the property of an entity actually. Describes the property of an entity. So it is simply like a column name. No, we don't have much discussion. So like try to understand in a simple manner. In a table, as we've seen already that in a table where it is a set of rows, set of columns. So columns we are calling as a attributes, rows we are calling as a tuples. That's it. So that is what the attribute, column name we are calling as an attribute. That is what one property, right? Name is one property. We are going to have set of characters. Salary is one another property. So like that, every column we are calling as a attribute in the database terminology. Okay, technically we are calling. Now it is we are going to represent with vowel shape actually. Attributes we are going to represent with vowel shape. Okay, so let us see another definition with for better understanding. That is key attribute. So a key attribute is nothing but primary key. So or if you see more deeply, candidate key. So a key attribute can uniquely identify an entity from an entity set actually. So as we discussed, entity is nothing but a set of entities. So those set of entities we are calling as one table. So every row you must identify uniquely, right? So to identify uniquely, one column, that means one attribute you have to select as a key attribute. So one attribute is nothing but what actually, one attribute or set of attributes actually. So that is what primary key. So that we are calling as a key attribute. Okay. So now if you see here, student. So this student is actually an entity as we discussed already earlier. And it is going to have, for example, roll number, name, age, address. So first of all, what we discussed, this is the attribute, right? So these are all the attributes in this relation, in this student actually, entity. So these four attributes are there. Now, as name implies here, the definition, key attribute. So roll number, name, age, address. Every student, these four things are going to be there. So if you select a key attribute as name, there may be two students with same name. And age, of course, same age. Address, duplicate values are possible for all these three attributes. But the roll number is what actually, for every student, we are going to give unique roll number. So there is no duplicate roll numbers for two students. So that is why roll number is going to become key attribute. For the key attributes, we are going to give the underline. Out of all attributes for an entity, which one is the key attribute? Whichever attribute have the underline, that is going to become key attribute actually. So simple discussion. Okay. So which key attribute you are identifying uniquely, that attribute you are going to differentiate with other attributes by giving underline. So that is simple discussion. And then after that, we have another definition, that is simple attribute. So this is very simple. So you can see the meaning, an attribute which cannot be divided into simple components actually. So that means further division is not possible. For example, age is there. Age further you cannot divide actually. Okay. So age means for every student only one value will be there. Maybe 20, 18, 19, 21 basing on their date of birth. So that's it, simple attribute. Further division is not possible. Or to understand this meaning, let us go for the next definition, that is composite attribute. If you understand this, this is going to become simple. So what is meaning of composite attribute is attribute that is combination of other attributes. So what does it mean? You can see from this diagram. If you take the address part, address is actually further you can divide like a state, country, pin. So further you can divide actually. So that is what composite attribute. Or if you see the name, so name, if you see, first name will be there. Is it? This is a one attribute, and middle name will be there. Is it or not? Middle name and last name will be there. So that is what further division is possible here. So that is what composite attribute. Name is a composite attribute, address is a composite attribute. But now roll number is only one value, only further division is not possible. Age is further division is not possible. So these two are going to become simple attributes. Name is going to become composite attribute, and address of course composite attribute. So that is what now these three definitions, and the remaining definitions we will see in the next lecture. So here we see in the meaning of the attribute. So simply a column name, and what is key attribute, and how to differentiate in the diagram. That is whoever have the underline, that is going to become key attribute. Simple attribute, further division not possible. Composite attribute, further division is possible. So here name and address are the composite attributes actually. Okay. Hi. So now let us see further definitions under attribute actually. Okay. So the first one is here single valued attribute. So as name implies actually an attribute which will take only single value for each entity instance actually. So for example, if you see age. So for example, any person, or for example, if it is a student table. So every student, only one value it is possible. So to understand this betterly, let us go for the next definition, that is multi-valued. So opposite to single, multi-valued attributes. What does it mean? So an attribute which may take more than one value actually, which may take, sometimes may take more than one value. What is example? Phone number. One student may have two numbers actually, and one student may have two mail IDs. So two mail IDs you are entering by giving comma actually. So for example, phone number 123, comma, another phone number 456 is given. So two values, multi-valued. So multiple values are there under single column phone number column. So this is what actually multi-valued attribute. So how you will know in a relation, in a table, that means in a entity, which attribute is the multi-valued attribute, so that you can differentiate with these two circles actually. So you can see here vowel with a normal with a single line, that is a normal attribute. If it is a multi-valued attribute, we are going to have a two circles. Okay, like a weak entity actually. Okay. And another definition is stored attribute. So an attribute which need to be stored permanently, that we are not going to change actually. So for example, name of a student. So name of a student is not going to change, right? And date of birth, particular person, particular student date of birth is not going to change. That is permanent. And from this, we have another definition, that is derived attribute. What is meaning of derived attribute? An attribute that is calculated or derived from other attributes actually. For example, age. So if date of birth is, for example, 2005, then what is the age actually? Current year minus date of birth. So that means this age you are getting from this DOB. You are deriving from other attributes actually. Is it or not? So that in that way, so maybe approximately 17 years. Is it or not? So this value you got from the DOB. That is what derived attributes. So if you see all at once, derived attributes, especially with the dashed line, you can observe actually. So this is going to become derived attribute. Now, whatever attributes we discussed till now, you can see all of them in this diagram actually. So this is going to become, address is going to become composite attribute, and this is going to become multi-valued attributes. Is it or not? So that is what actually, and this is a key attribute. So these are all things with different attributes we must understand clearly. So now this is what one entity you can see. Student entity, if you take, this is the entity. Overall, just try to understand whatever we discussed till now. Student is one entity. That means one table. it have set of attributes, that means columns, roll number, name, DOB, age, address, and of course further divided state, country, PIN number, and it have a mail ID. Now, in that, roll number is actually a key attribute, and age is actually a derived attribute that is deriving from DOB, and address is a composite attribute, further divided attributes, and mail ID is actually a multi-valued attribute. So that is what attributes, whatever we discussed, all together in this single diagram, we can observe actually. Okay. Hi. So now let us see the another important definition, that is relationship. Okay. So what is meaning of relationship? So if you see, association between entities are called a relationship. So it is very simple. Okay, fine. So whenever if you take two entities, so here association between entities actually. So two entities, if you take, what kind of association they have, what kind of relationship they have. So that relationship we are going to represent with the diamond symbol actually. So that is what this is the symbol we are going to use for representing the relationship between two attributes or among the attributes, you can say. Okay. So for better understanding, let us take a simple example, that is employee works for organization. So employee is one entity, organization is another entity. Now, what is the relationship between these two entities actually? This is entity 1 and this is entity 2. In these two entities, what is the relation actually between these two? That is works for. So that is what you can see here. Employee entity 1, organization entity 2, and what is the relation between these two is, that is the works for, and we are going to connect like this. Okay, so this is what the relationship. So in this way, first of all, we are going to define the relationship between two entities or more than two entities actually. Okay, that we will see. More than two we will see in the discussion further. Okay. Now, weak relationship. See, weak relationship means it is used to connect with a weak entity. So we already discussed that strong entity, weak entity. Weak entity meaning is which don't have a key actually. Candidate key is not exist out of all attributes in that particular entity. Then that is going to become weak entity. That is what we discussed already. Now, if you have a weak entity, then the relationship is also going to become weak relationship. So that you can see that we are going to represent with the double diamond actually, double outlined diamond. Okay, so this is what, for example, as we seen earlier, bank account. So bank account, simply if you take the bank account, there may be duplicate values. So that is why this is going to become weak entity. Now this we are going to connect with bank actually. So like SBI bank. So if you connect bank to this one, then we are going to take here a diamond you can take. But that is weak relationship. That is what you can connect like this. Of course, further details we will see in the discussion. The very first thing is if the relationship between two entities, in those entities, one of the entity is the weak entity, then relationship is going to become weak relationship. So that strong relationship, normal relationship, you are going to say take with a single outline, and here double outline diamond we are going to take for the weak relationship. Okay. Right. So now let us see the next concept, that is degree of relationship. So here it is simple. Degree meaning is what actually? So some number, involvement number. So what does it mean? Let us try to understand. So very simple. So degree of a relationship is number of entities are involved. So number of entity types are involved or number of entities are involved. How many entities are involving in a relationship? That is calling as a degree actually. So you can say here the n-ary relationship is nothing but n entities are involved. Degree is n. So for example, unary relationship, binary relationship, ternary relationship. Unary meaning is one entity involved in the relation, and binary means two entities are involved. Ternary means three entities. N-ary means n entities are involved in the relation actually. So just for better understanding, if you take the unary relationship, for example, unary relationship in real time, an employee is a manager of another employee. So you can see, for example, you can see here, employee will be there. So one employee is the manager for another employee, is it or not? So in the EMP table, if you take a EMP table, so EMP number will be there, some ename will be there, and MGR, manager. So EMP number 1, 2, 3, if you take, ename ABC, and XYZ, for example, simple things, PQR. So manager, for example, one is the boss, he don't have any manager. For 2, manager is 1. For 3, manager is 2, for example. Now you can see employee, this is the whole thing is employee. Here it is referring EMP number. Of course, this is foreign key. And you can see where it is referring in the same table. So one employee is the manager for another employee actually. So that is what unary relationship. So in the manager relationship, how many entities are involving? Only one entity. So that is calling as unary relationship. And the another one is binary relationship. So employee works for departments. So now you can see that. Organization, employee is the one entity, and actually this is department. So department or organization, anything is fine actually. So department, anything you can take, and works for. So employee works for department. Okay. So in this relation, simply you can see relation R1, relation R2, two relations are involved. So this relation, this is a binary relationship. Now you can see ternary relationship. That means three relations are involved, that you can see relation 1, 2, 3. Okay, so in the coming lectures, you will get the more clarity. And first of all, the basic meaning of this relationship degree is this one. How many entities are involving in the relationship? That is what actually the number, that number we are calling as a degree. Okay. Hi. So now let us see the next concept. That is what the cardinality. So here actually we are going to see the relationships meaning in this lecture. Okay, so that is what the definition is: the numerical attributes of the relationship between two entities actually. So actually entity 1 will be there, entity 2 will be there, and we are going to have a set of records in entity 1, and entity 2 also set of records will be there. How these are connected actually? So that is what we are going to explore more on this. So these relationships can have 4 possible connectivities are given below. So one is one-to-one relationship. Another one is one-to-n relationship. That is what one-to-many relationship, and many-to-one relationship, and many-to-many relationship. So these 4 things, let us try to understand clearly. Then we will see many things. Almost we can create a ER diagrams for any given requirement actually. Okay. So that is what here we are talking about, the minimum and maximum values of the connectivities we are going to discuss. That is called the cardinality of a relationship. So we will get the more clarity with the examples. First of all, let us try to understand these 4 actually. So that is what the first one is: one-to-one relationship. So single instance of an entity is associated with a single instance of another entity actually. What does it mean? So you can see here, a person has only one passport, and a passport is given to only one person. Is it or not? So that you can observe here. So one person has one passport. Is it or not? So person is one entity, E1. Passport is another entity, E2. So every person have a connection to one passport only. So that is what one-to-one relationship. Is it or not? So no person have two passports. Okay, so that is what actually one-to-one relationship. Okay, every person one, person two, person three will be there. Passport one, passport two, passport three will be there. So person one passport is this, person two passport is this, person three passport is this one. So that is called actually one-to-one relationship. Okay. Now if you see another one-to-many relationship. So single instance, that is what here single instance one. So here also single instance is associated with more than one instance, but here you can see single instance one-to-one. So that is what you see the example. Customer can place many orders, right? So one customer can place many orders. So that is what customer one is there. So order one, order two, order three. So one customer given three orders. Is it or not? So one customer given. So that is what one to many orders. So that is what second customer, if you take, he given order one and order two. So that is what many orders, one to many persons. So that relationship, this kind of relationships calling as a one to many actually. Now it's a reverse if you see many to one actually. See, when you see customer to order, if this is the order, then this is going to become one to many. But if it is order to customer, then this is going to become many to one. That is what the reverse part here. That's it. Nothing is there. So if you are going from the customer to order, then you have to say one to many relationship. If you are saying many to customer, order to customer order, then you can say many to one relationship actually. So that is what more than one instance of an entity is associated with single instance actually. So that is the many students can study in one college. So that is what the example you can see. So student one, student two, student three, these are studying in one college, college number one. And student four, student five, student six, all these are studying in college two. So many students are studying in one college. So that is what actually many to one actually. But if you see reverse, college to students, so you can say one to many relationship. That is what you must be careful actually. Okay. And then next example is many to many relationship. So of course, this you can write down the definition. More than one instance of an entity is associated with more than one instance actually. So what is the best example? You can see student can assign to many projects and project can done by many students. So that is what you can see. So one student can do many projects. One project can be done by many students. So that is what, for example, S1, S2, S3 if I take. Project 1, project 2 if I take. So assume that student 1, student 2 doing project number 1. Okay, then student 2 and student 3 is doing by project number 2. Okay, so now you can see and student 1 also can do project number 3 actually. So student 1 doing many projects. So in that way, one student doing many projects and one project done by many students, one to many actually. So this all combination together calling as a M to M, M to N or M to N, that number, that character not important, meaning is important. So student to project is 1 to M, project to student is 1 to M. So these many to 1. Okay, so these two together calling as a many to many relationship. This is what somewhat tricky actually. Don't try to confuse. So here S1 is actually doing two projects. Project 1 is done by 2 students. So from this side 1 to many, from this side many to 1 to many actually. So together we can say many to many relationships. These are the 4 different possible relationships, that is 1 to 1, 1 to many to 1, many to many actually. Basing on this, lot of further discussion, actual insights we are going to see based on the discussion till now we have actually. So we already seen that different entity types, that is strong entity, weak entity, and we already seen that different types of attributes and a further discussion, and we've seen that relationship and different possible relationships. All together we are going to have many real-time examples, so we are going to analyze actually in the coming lectures actually. Okay, so the actual discussion is in the next coming lectures, basing on the understanding of all these terminologies and concepts till now what we have. Okay. Hi. So now let us see the next concept in ER modeling. So that is cardinality ratio, partial and total participation. Okay. So let us try to understand first of all what is this concept. So here if you see, it describes the maximum number of entity occurrences participating through relationship actually. So we know that in the relationship entities are participating. So maximum number of times occurrences we are trying to calculate actually. So let us try to understand with the simple examples actually. So if you take the scenario 1, so this is what the relation 1 and relation 2, and this is the relationship between these two entities actually. Now if you see, these are the entity instances of relation 1, A, B, C, D, E, and relation 2, entity instances are 1, 2, 3, 4, 5, 6. And you see how they have a relationship. A have a relationship with entity instance A of relation 1 have a relationship with entity instance 2 of relation 2 actually. Similarly, you just try to understand the sentence actually. Entity instance B of relation 1 have a relationship with entity instance 6 of relation 2. That is what these lines are saying actually. So what we are going to observe from this diagram, this relationship is A, B, C, D, E are participating in the relationship. And in the relation 2, if you observe, 1 is not participating in the relationship. That means entity instance 1 of relation 2 not participating in the relationship. And here, every entity instance is participating in the relationship. That is what through relationship, occurrence participating through relationship. Now here actually two concepts we have, minimum and maximum. So two concepts we have. Minimum. So minimum, every entity, at least one time they are participating in the relationship. Is it or not? At least one time you have a line actually. That is what minimum is 1. Maximum is also 1. Is it or not? So maximum participating in the relationship is 1. So 1 comma 1. Now if you come to this relation, this entity 2, minimum, 1 is not participating in the relationship, right? That means it is 0. So minimum out of all entity instances, minimum participation is 0. That is what 1. And maximum participation is 1. Everyone participating only one time. So that is what actually. So for every entity we are going to calculate minimum participation, maximum participation actually. So basing on this, we are going to define some definitions after this. For example, for more clarity, let us take another scenario. So in this scenario, same ER diagram we are taking, but entity instances and their relationships are going to change a little. Here, if you observe entity instance A of relation 1 participating 2 times, that means it have a relationship with 2 entity instances of relation 2. Is it or not? 2 and 4 are connected to A actually. Now, if you come here, this is participating 2 times. This is one time,
and this is 2 time, this is 1 time. Simple. Out of all these values, minimum is what? 1, maximum is what? 2. That's it. That is what we are writing. That is what our understanding overall. And now if you come to this side, relation 2 side, this is participating 0 times in the relationship. And 2, 1 time, 3, 1 time, 4, 3 times participating, is it or not, in the relationship. And 5, 1 time, 6, 1 time. Minimum is what? 0, maximum is what? 3. So that is what actually we are going to write down here. Got the point or not? So that is what, first of all, minimum cardinality, maximum cardinality we are going to tell. Minimum number of times, how many minimum number of times participating in the relationship, maximum number of times participating in the relationship. Now from this discussion, we are going to write down some important points. Those are actually really important things. So that is, minimum cardinality is 0. If any relationship have minimum cardinality 0, that is actually partial participation. That means all entity instances are not participating in the relationship. That you can see here, all entity instances of relation 2 not participating in the relationship. So this is partial participation. All of them are not part of the relationship. If minimum cardinality is 1, meaning is what? Everyone participating in the relationship. That is what actually, that is going to become total participation. All of them are participating. Generally try to understand. That is what minimum 0 and 1 meaning. 0, if you have, that meaning is that relation, that entity have a partial participation with the relationship. So that means all of them are not connected to relationship actually. Now another point, maximum, related to maximum cardinality 1. At most one, any instance of that particular entity, maximum participating only 1 time. This is not that much significant. Minimum is the decider actually. Okay. And of course, n means entity occurrences participating n times in the relationship. And this is 1 time actually. Now, basing on this discussion, how you will know which entity total participation, which entity partial participation diagrammatically. So that is what let us observe in this diagram. So this is what we already seen, right? This is 1, 1 and this is 0, 1. So if you observe here, minimum cardinality is 1. Minimum cardinality is 1 means this is a total participation. So for the total participation, graphically how you are representing is that particular relationship. I am removing it. Here you can observe and you can see here. With the 2 lines, you are representing a relationship, participating relationship. That means that entity is total participation. That entity doing total participation with the relationship actually. Single line means that is a partial participation. So similarly here also, if you observe 1, 1, the 1 maximum is 2, and here 0, maximum is 3. So here also minimum is 1 means relation 1 is total participation. There is no same thing, right? So that means this is the total participation. So accordingly, let us change with the 2 lines actually. So that relationship, whichever line have a 2 line, whichever relation have a 2 lines, that is participating totally with the relationship actually. So in this way, you can identify which relation is total participating, which relation is partial participating. And this is what finding the minimum cardinality and maximum cardinality actually. Okay. Hi. So now let us see some examples in this ER model so that whatever concepts we learn, those are going to become strong actually. So especially in case of this partial participation, total participation. So let us take one simple example. So for example, this is the ER diagram we taken, and it is saying that many to many relationship. Okay. If you see here, project relation, project entity have minimum cardinality 1, maximum cardinality 10. and the employee entity, minimum cardinality 0, maximum cardinality 4. Now from this, we have to write down its meaning actually in the sentence. In the text form, let us try to write down. So if you see, this meaning is what actually all projects supposed to have at least one employee. That is what it is saying. Is it or not? One meaning is what? Every project must have at least one employee actually. That is what its meaning. And this meaning is what? Maximum means maximum 10 employees actually. That is what maximum number of employees in a project is 10. That is what based from this its meaning. So it is what? Sometimes they give these two sentences, then you have to tell minimum cardinality, maximum cardinality. So here minimum cardinality is 1. So what you can say this participation? This participation is total participation. Is it or not? So that is what this is, a total participation. And if you come to this part, here you have 0 means every employee need not be participate in the project, right? That is what minimum cardinality say. That means this is a partial participation, this relation. Every employee need not be participate in a relationship actually. So that is what you can see the first one. All employees need not to participate in the project. Then this second part 4 is saying that if any employee working under projects, maximum under how many projects he can work, that is what 4 actually. Maximum 4 projects he can work. So because minimum is 0, this is going to become partial participation. So in that way we can decide actually. And maximum, what way you can use is, you can say relationship actually. So how you are saying that employee relationship is one to many relationship, because 4, maximum 4 they can participate. That means one employee can participate more than one project. That means many projects. So one to many relationship, that is what employee to project relationship is one to many. And if you come to project also, maximum is 10. That means they can work in more than one. Every project may have more than one employee. That means one project have many employees. That is what project to employee relationship is one to many. This is one to many, this is one to many. That is why overall this is a M to N relationship. So two one to many relationship combinations is actually many to many relationship. That is what M to N. That means many to many relationship overall. So from this side we have one to many, and from this side one to many. So overall relationship is many to many relationship. Okay. So this is what from this diagram you can understand the concept actually. Now let us take one more example. In this example, what he's saying is, if you see here, he's saying something basing on that we have to construct the diagram. Each project supposed to have minimum 2, maximum 15 employees. Okay, let it be. Every employee should be part of projects and they can participate only in one project. So now how you can say this one? So let us see here. Draw the ER diagram, mention minimum and maximum cardinality, participation, type of relationship. Let us observe all these things actually. Now you can see these are the, this is the one relation, project relation entity, and this is another relation, that is nothing but employee entity and relationship. First of all, let us take this statement. He is saying that project supposed to have minimum 2 employees. Minimum 2 employees means minimum always, minimum will never mention 2 actually, though 2 employees is minimum. So either 0, that means some of them are need not participate. If more than 1, if they are mentioning minimum, then still we are going to take as a 1 only. That is one thing you must observe. Minimum cardinality either 0 or 1. Though minimum participation is more than one also, you should mention one only here. That is what drawback in the ER diagrams. Okay, let it be. Now come to the maximum part. So that means cardinality part. So 15 employees maximum actually. So that we are going to mention. So one, at least one, that is what it is saying, at least one employee must be there in the project. That is what overall it's meaning. What kind of understanding we are going to have? At least one employee participate in the project actually, and maximum 15 employees. Now let us take this line. So this line is saying what? Every employee should part of project. Every employee should part of project means they must participate at least one project. That is what minimum cardinality one. Is it or not? They can participate only in one project. And he's saying the second part is they can participate only one project. That means maximum one project. That is what actually. Now from this, here minimum is one. So it is a total participation. Is it or not? And here also minimum is one. So this is a total participation. That is what the participation part. So both the relationships, both the entities have a total participation. Now, here you can see 15 actually. That means one project may have many employees. That means from project to employee, this is a one-to-many relationship. Now, if you come to employee, one employee can participate, can work under in one project only. That is what maximum part say. That means from this side, this is one-to-one relationship. So overall, this is going to become one-to-many relationship, this part. Got the point or not? Basing on that only, it will become overall what? This is one-to-many, this is one-to-one. So overall relationship is this side one, this side M actually. So that is what type of relationship. This is one-to-many relationship, and this is one-to-one relationship. Got the point or not? So minimum cardinality, maximum cardinality of project and employee you can observe, and the participation, both of them is total participation, and the relationship is one is one-to-many and another one is one-to-one actually. Okay.
Hi. So now let us see very important concept in the DBMS subject, and we are going to see actually normalization. So for the before normalization, you have a wonderful concept and very important concept you have to understand. So that is actually this functional dependency actually. Okay. So this is what first of all we must understand. So what is this functional dependency? Let us try to understand in simple manner, and then we will see all the required concepts under this definition, functional dependencies. Then we will see actually the normalization. Okay. So in my words, normalization is very simple, and it is nothing if you understand functional dependency concept actually. Okay. So let us try to understand all the things under this functional dependency. Okay. So what is the definition of this one? As name implies, functional dependency. So something dependence actually. So what is that? Let us try to understand. So here, the functional dependency is a relationship, first of all, that exists among the attributes. As we know that in the relation, we are going to have a set of attributes. Okay. So you are going to put some relation among these attributes actually. So what is that one you can see here? So for example, X is a set of attributes and Y is also set of attributes. Set of attributes in the X are deriving set of attributes Y actually. So here X you can say determinant and Y you can say dependent, because you are deriving Y from X actually. So that means here dependency is there. That is what. And what is its meaning actually? So wherever X is there, same value of X, then same value of Y you are deriving. Sometimes maybe same value are going to repeat in more than one row actually.
So wherever you have x, same value x, then same value of y you are going to derive. Then only you are able to place this relation x derives y. So that x is the determinant, y is the dependent. So for better understanding, so here let us take a simple example here. So let us take this only. X is one column name, that is nothing but one attribute, and y is also another attribute. So here if you observe, when you can write down this relation x to y, actually x deriving y, that you can observe here. Here x, one of the value is x1, that is deriving y1. So here x1 is deriving. If I ask you x1, what is the y value? You are going to say y1. Is it every time? So here you can see x1 is there. In the both those times, it is deriving y1. And even also here also x1 is there. That is also deriving y1. And not only just for this one value at the same time. For all other values of x, how many times they are repeating? Every time you must have same value actually. If you observe such a kind of relation, then you can put the relation between two attributes like this. So that you can observe actually for other values. x2, if you observe, x2 is deriving every time y2. Is it or not? So here also x2 is there. So though it is deriving y2. Fine. And then even x3 also, if you observe, 2 times x3 is there. Both the times it is deriving y3. So then this is valid functional dependency. You can say this is one of the FD in short. So that is what actually, first of all, try to understand meaning of this concept is very simple. In the flow, automatically we will get everything. Okay. So for example, when this condition is false, when this relation is false. So simple, for example, if at least one of the value x1, some value if I took, in all places it is deriving y1, but in one of the row x1 is deriving, for example, y2, then you should not place this relation. That is what, if at least one value it is deriving different values actually. So here overall you can say x is deriving y1, in some places x1 is deriving y2. So it is not valid actually. It is not a FD because y is not dependent on x actually. So if this is not there, then this is fine. X is deriving y actually. So hope this discussion make you first of all understanding that when you can use this relation. So to make this understanding more stronger, let us see a few examples here. So consider the following relation R, which dependency does not hold over R. So this is what the relation R. So over this relation, you have three attributes A, B, C, and corresponding values are also there. He given that four options actually. So whether these FDs are holding over this relation or not, let us observe. Option A is saying that A deriving B. Let us observe A deriving B. So you can see the first thing is when you can say straight away this is valid FD or not. If whatever is there LHS side is always determinant, is it or not? So whatever is there in the LHS side, if it have all values distinct, all values are distinct, you can observe A have all values distinct. You no need to cross check this actually. Because all of them is distinct, definitely whether they are same or different, we don't bother. If there are some places they are equal, like here, x1 here, there, x1 here, also there. At that time, you have to go for the cross check. So that is why, in that way, this is the valid FT, first of all. That means this is not the answer actually, basing on the question. Okay. Then you can see BC deriving A actually. So BC together, that is why we told X is not just a one attribute. X may be a set of attributes. At least one attribute must be there. So now BC deriving A actually. So let us see BC together. So here BC, that together you have to see actually. So here BC and here also BC, there is same combination. So whenever you have the same combination, it must derive same value. Let us check. BC deriving A, here it is deriving A, and here it is deriving D. So this is not valid FD actually, functional dependency. So in that way, that means he is asking which dependency does not hold over R. Yes, this is not at all valid actually. Maybe answer is actually B, you can say. Okay, let us check others also. So B deriving C. Let us see. B deriving C. See, B 2 times are there here. In both the times it is deriving same value. Yes, valid. And C is there, of course, only one time. So you don't need to bother. See, if any value under a particular attribute or combination of attributes, if one time is there any value in the LHS side of LHS side part, X part I am talking, don't bother about the RHS part actually. If a LHS side more than one time if it is existed, maybe one attribute or combination of attributes, their combination, then you just cross check actually. These simple tricks makes you more perfect actually. So this is fine, right? So this is also valid FD, you can see. And here you can see AC derives B. So AC, these two you have to cross check. See, values if you see AC, LHS side AC, and here DC, and here EC. See, do you have any repeated combination? No. So straight away you can say again here also, this is valid FD. So the actual answer is B actually for this question. Got it? So in that way, simply you can decide. And let us get familiar of this concept of functional dependency. X derives Y. What does it mean actually? Now let us go for the next one. One more thing, let us try to practice so that things are going to become more perfect actually. So now if you see, consider the following relation R. Which set of the FD satisfy over relation R? So you can see this is the table given now, and these are the 4 things are given. Actually here, instead of giving one functional dependency, in each option, he given more than one FD actually. So all FDs are if satisfying, then that is the answer actually. So let us simply check. A derives BCD. So here A derives BCD, that is what asking. So here A, this one, A1 repeated here, okay? And here also repeat. So 2 times is there. Do you have the 2 times same value for BCD? B1, C1, D1, B3, C3, D1. That means you don't have RHS part same. So this is not valid FD. So this is not actually the answer. We don't need to cross check BC derives D or not. Because one of the FD is not valid. So set is not valid actually, simply, right? So you can cross check also for better practice. Okay, let it be. Now let us go for the B. C derives ABD. So C derives ABD. So you see LHS part C, if you observe, C1, C2, C3, C4, C5. All of them are distinct. That is very important thing. Since all of them are distinct in this FD, LHS part, this is valid FD because whether repeated or different for the RHS, we don't bother. Okay. Now if you take the another FD, AB derives CD. AB let us take. A1, B1 and A2, B2, A1, B3, A3, B3, A4, B4. So here only B3 repeated, but here it is not repeated, so that every combination is distinct again. AB is the, every combination is distinct. So this is also valid FD. Let us go for the third FD actually. A derives D. Let us observe A. A1, A2, A1, A3, A4. So A1 is 2 times. In those 2 times, observe D. D1 here and here also D1. Okay, in this way you can see. So D1 and here also D1. Wherever you have A1, those places D1 and remaining are distinct. Remaining are there one time only. So that is why this is valid FD. So answer is this one. All FDs are valid actually. So option B is the correct one. So you can simply cross check this also. this is repeated FD above also there. So you can go for the next. You can take the AD derives B actually. So AD derives B. Let us cross check AD. So AD derives B, he is saying. So AD combination, if you take A1, D1 two times is there. In both the times, is it deriving same value? Let us check. So here B1 deriving and here B3 deriving. So don't confuse with these lines. So one time it is deriving B1 and another time it is deriving B3. So it is invalid FD actually. So this also not correct, and because already we find the answer option B. So overall these two questions especially is given for get the familiarity of this concept actually. What are the valid FDs? What is meaning of FDs? How to find the FDs actually? Okay. So this is what overall the functional dependency is a relation among the attributes actually that you are going to derive basing on the either you have the values basing on the values, or in future basing on the in future whatever you are writing basing on that, now only you will derive actually. Okay. Hi. So now let us see in this functional dependency, the next one. So that is types of functional dependencies actually. So what is that one? So what are different types of the functional dependencies? So simply it is one is a trivial functional dependency and the another one is non-trivial functional dependency actually. So these meanings are very simple. There is no big deal actually. So you can see trivial functional dependency. What does it mean? So if you have FD A to B has trivial functional dependency if B is subset of A actually. So that is what. So B is completely subset or equal to A. So let us see with simple example. So A derives A. So this is what RHS part. Simply you can say RHS is always subset or equal to LHS. That's it. How and all you can see another example. ABC LHS derives BC. That is actually trivial thing. You no need to say separately actually. So whatever attributes are there LHS side, if you have completely same attributes in the RHS are a part of that, then automatically it will derive. So that is you no need to consider actually. That is why it is coming under the trivial functional dependence. Okay. And another regular example, if you take employee ID, employee name, automatically derives employee ID or employee name. So that is the reason all these are so simply RHS if it is a subset are equal to LHS. So you can say that is trivial functional dependency. Then now you can understand what is non-trivial functional dependency. That is very simple. So you can see here what is non-trivial functional dependency. So here A derives B, non-trivial functional dependency when it will become if B is not subset of A. That means their intersection part is 5. So that you can see here. For example, A derives B. Yes, you can see this is one attribute, this is another attribute. Both of them not same. And ABC derives DC. Actually, it is not C actually. You can take some other attributes E. Okay, D, E. Okay. Actually, we will eliminate these things also in the further discussion. We will see when you are going for the closer, this kind of things actually. So that is what even C, if C is there also you can eliminate with other whatever LHS side is there. Along with those, if you have any extra, that is only valid. Like D is valid, C you can skip actually. There is no problem also if you delete actually. That is what trivial things. By using some inference rules, we can change them also. So that is why you take DE here. And then next, if you see employee ID deriving employee name. So LHS part and RHS part is not same. So their intersection is 5. So simply which FDs are coming under non-trivial, LHS and RHS, their intersection is 5. There is no common attributes. But in the trivial functional dependency, RHS is completely subset to LHS part actually. So in such cases, you can say that is trivial FD actually. Okay. So these are the two types: trivial functional dependency, non-trivial functional dependency. Okay. Hi. So now let us see one simple question basing on the discussion till now we have on the functional dependency actually. So find the number of functional dependencies that can be formed over relation to attributes actually. How many functional dependencies we can form? So let us take a relation. In that, assume two attributes he told. That we are going to take as a and B. So these are the two attributes. That is what he given. Now, suppose X derives Y. What are all possible things here under X? Under X, nothing. Another one is either A, another one is either B or AB. Is it? Y side also same attributes from the same relation. Is it or not? So that is why phi, one possibility A, another possibility B, and another possibility AB. That's it. Is it or not? So that is what. So all these things, how many combinations are possible? Let us try to observe actually. So if I take phi derives phi, one possibility. Phi derives A, phi, whether it is valid or not, let it be. But all possibilities we are trying to find so that we can derive one simple formula actually. So phi derives B, so phi derives AB. That is one possibility. And another one is A. A derives phi, A derives A derives B, A derives AB. Is it? Then next B. B derives phi, B derives A, B derives B, B derives AB actually. Is it? And then next AB actually, AB derives phi, AB derives A, AB derives B, and AB derives AB. That's it. So this is what total possibilities actually. And let us try to see what are all the valid, that means non-trivial FDs. Always valid is non-trivial. So these entire 5 related things, you can skip them, these 4. And this is trivial functional dependency. This is one of the valid FD. Is it or not? Of course, here actually it is AB. This is one of the valid FD. Even this is also equal to previous one. Later we will realize by using inference rules actually. A derives AB. This is actually equal to this one after if you apply the inference rules. Okay. So let it be. So this is the valid one till now. And this is another valid one. And this is also whatever discussion I have here, we have same thing, even this is equal to this part. And all these things are also trivial FDs actually. Because LHS side, all attributes you have in the table. So RHS side is definitely subset to the LHS. That is why all of them is trivial. So here useful number of useful means always non-trivial. Useful non-trivial FDs, how many from this actually? Non-trivial FDs are that is 2 only from this part. That is this and this. A derives B, B derives A. And if you see now total how many possible, if you have n attributes like this here we have total 16, right? So total how many FDs are possible actually? So that is what here, how many attributes you have? A, B I have. So this, if you see little logical one, I have A and B. Either A exists, not exist. B exists, not exist. Is it or not? So how many possibilities you have? How many combinations possible? 0, 0, both not exist. That is what 5. 0, 1, only B exists. 1, 0, only A exists. 1, 1, A, B exists. So such a way if you approach, here total 2 square combinations. Is it or not? That is nothing but number of attributes is this power 2 actually. If I have 3 attributes, I am going to have 3 actually. So that is what you can write down 2 power n combinations here. And even here also 2 power n combinations. Same discussion even here also. Now, this is one thing. This is 4 and this is 4. Now this with everyone, like discrete mass functions actually. And this is also with everyone. That means what? These two you have to multiply. Total possible FDs simply. That may be trivial, non-trivial, valid or invalid. Won't bother. This is 2 power n into 2 power n. That is 2 power 2n actually. Sometimes this kind of questions also you can expect if you are preparing for numerical exams or competitive exams. So try to understand inside a discussion. So that is what we are going to note down that as a note. You can see total number of functions, functional dependencies possible over a relation with the n attributes actually. That is what 2 power 2n. In this manner you can tell. X side 2 power n possibilities, combinations. Y side 2 power n combinations. That means LHS side 2 power n, RHS side 2 power 1. Total how many relations are possible means X side combinations only, LHS side combinations, RHS side combinations only we derive. Total relations how many possible, FDs are how many possible, that is what you have to multiply both the sides. So both the sides are same, that if you multiply 2 power 2n actually. Okay. So that is what the simple question for better understanding of the whatever we have discussed until now. Okay. Hello. So now let us see another concept in this functional dependency, and which is very important and many places we are going to use actually you can apply in the further discussion. So that is what actually inference rules. So these inference rules, for what purpose we are using them and what we are doing actually. So here if you see the inference rule is a type of assertion. It can apply to a set of FDs to derive other FDs actually. So we already have some set of FDs actually, some maybe to one or two or some set of FDs are there. By using them and by using these inference rules, you can derive another FDs actually. So that is what it is saying. Using the inference rule, you can derive additional functional dependencies on the initial set. Whatever is basically is given, by using that, you are going to get the new FDs which are valid also. So such a kind of valid FDs, how you are getting? By using these inference rules. So totally 5 inference rules we are going to see. So let us see what are those actually. So the first one is in that reflexive rule. So this is very simple and we already seen this kind of discussion also. What is that? In this, if y is subset of x, then x is determines y actually. So this we already seen actually, non-trivial for FDs. So that is what, if you see y is a superset of x actually, that is nothing but y is subset to y, x actually, y is subset or equal to x, then x is deriving y. So that is what, if you take the example A, B, C, BC is completely subset to LHS part, okay? Or here you can see title and author, of course title is subset to LHS part, okay? So this is what simple reflexive meaning is what, deriving itself actually. Reflexive meaning is if you go for the discrete mass concepts. So same thing here you can apply, okay? Then the another inference rule is augmentation rule actually. This is important. In many places we can use it. What is this augmentation rule is? In this, if x determines y, xz determines yz for any z actually. So that you can see. This is already you have. You take any other attribute in the relation, that is z assume. Any other attribute if I take, if you add that in the both the sides, LHS side and RHS side, that is also going to become valid FD. So that is what here it is saying. So for example, you have a relation A, B, C, D. So same example actually, A derives B, and if I add both the sides C actually, here it is B, BC. So if I add both the sides C, then still AC derives BC, that is also valid. Uniquely it will derive, okay? So augmentation rule is also very simple one. Now let us see the next one. So that is transitive rule. So this also you might see in many places, but the meaning is same actually. That is in this x determines y and y determines z. So transitively what we can say, x determines z actually, is it? So that is what x determines y, y determines z. So because both of them is same, so x is determines z actually, is it? So that is what same thing, same kind of example actually. So transitive rule. So these are the three rules. First of all, basically reflexive rule, augmentation rule, transitive rule. These things we are going to apply in many places actually. Try to get a familiarity of this. Now, next one, if you see, that is the union rule. This is important. So that you can see in this, if X determines Y and X determines Z, then X determines YZ actually. So how and all you can see. So that is what you can see. X determines Y. So that is what you can see here. Let us try to prove this one. X determines Y. So this is actually given. And X determines Z. This is also given. Then how you will say this one? So by using inference rule 2, what we are going to do is, okay, we are adding here X both the sides for this one, for the first one. So that is what X. So always X is going to become X only. So X determines XY. Then that you can write down as X determines XY. Okay, fine. And then this part, if you take the second one, for the second one also same thing if you do, but by adding a Y both the sides. So XY determines YZ. Then from this, what you can write down, this is XY determines YZ. If you observe this part and this part transitively by using inference rule 3, transitive rule, then what you can say, X determines YZ. Is it or not? So by using till now whatever inference rules we used, basing on that only you can tell that this is valid again. Okay. So that is what union. So simply if LHS part is same for different FDs, then RHS part you can combine them actually. That's it. Nothing is there. Okay. And then that is what in the both the LHS part is same, both the sides. Only if same, then you can union the RHS parts actually. Okay. Now if you take another inference rule, last one, so that is decomposition rule. It is just opposite to this part actually. What is that? Let us observe. So in this, X determines YZ, then X determines Y, and then you can write down Y determines Z. Exactly this opposite actually. So that is what X determines YZ, he given. So this is one. Now, can we write like this? Y determines, see, YZ determines Y. Can we write like this? Then transitively from this, this is by using reflexive rule. Is it or not? This part we can write down. And then transitively, if you see from this to what you can write down, X determines Y. So that is what one you proved. And same way, this time you will take Z here. Y determines YZ determines Z actually. Then from this, what you can write down, X determines Z also, transitively, this part and this part if you consider. So in that way, both the things you are able to derive. So just 4 and 5, union rule and decomposition rule, quite opposite to each other actually. Okay. So individually, that means nothing is there. Every attribute individually you can write down with LHS part. That's it. So by using these inferences rules, if you have a set of attributes, from that you can derive new additional FDs actually. For that purpose, we have these 5 inference rule important. Okay. Hi. So now let us see one simple example. So for understanding this closure actually. So here we are going to find the attribute closure actually. Okay. So here the first one is AB closure together. So when you are finding the any attribute closure, by default it will derive itself, right? So first we can write down A comma B. Then who are all there in the set? A is there. So identify variable A. So attribute A is deriving individually anything else? Yes, A is deriving DE actually. So you can note down D and E in the set. And after that, see, A, B is there, right? So A, B together is also deriving C. So this LHS part is already there in the set. So that is why RHS you can include in the set actually. Now, so B is there already. So B deriving F, note down F in the set. And then if you come to the next FD, F is there in the set actually. So F is there in the set means F deriving GH. And here D is also there in the set. So D deriving I comma J. So this is what closure of AB actually. So in this way, we can derive what are all the attributes that AB is deriving directly or indirectly. Okay. So in the same manner, let us try to find out for A closure. So A closure, first you can add that attribute itself into the set, and then let us come here. So LHS part is not there in the set, so skip this FD, go to the next one. So here A is deriving DE. So LHS part is there in the set already. So include RHS part actually. Then B is not there in the set, skip this FD, and F is also not there in the set. So skip this FD, and D is there in the set. So add RHS attributes actually. Now, so again go back, again you cross check. AB is not there. A is already, this part is already done. B is not there in the set till now, and F is not there, and this FD already added. So that means even after one more iteration, no new attribute is added to the closure. So this is what the final set, which is A closure actually. Okay. So now if you come to the DC closure, so DC closure. So first of all, D and then C you can add because it is deriving itself, right? So that is what DC we added. Now come here. So AB is not there in the set till now. A is also not there in the set. B is also not there in the set. And F is also not there. But you see here LHS part D is there in the set. So that means RHS IJ, it is deriving. Now what we will do, again go back to the first FD onwards. Now AB is there? No. A is there? No. B is there in the set? No. F is there? No. D already. See, after one iteration, nothing is added to this closure actually. That means this is the final set for DC closure. So that is what very simple thing actually. Now let us go for the B closure itself. Let us add first of all. So B, so A is not there, B is there of course, but entire LHS part must be there in the set. So you can skip this FD first one. A is not there, but B is there, B is deriving F. Yes. Now F deriving GH, so F is there, right? So GH you can include. After that, D is not there. Now go back to the one more iteration. See, for the iteration I and the next iteration I plus 1. So I plus 1, whatever set we have, in I also if you have same set, then you can stop the process actually. If I and I plus 1 iteration are different, then you must go for the next iteration actually. So always current iteration and previous iteration, if sets are same, then you have to stop actually. If sets are different, go for the next iteration. So that is what the simple indication where you have to stop. So that is what you have B, F, G, H. Even if you go next iteration, A B not there, A is not there, B is there, that is why F already added, and F is there, so GH already added. So D is not there. So you can see now current iteration and previous iteration sets are same, so you can stop the process. So B closure is B, F, G, H. Okay. So since we did these 4, you can practice these 3 actually. Anyhow, I will write down, but you please try on your own. So A, see I am writing. So A is deriving DE. A is deriving DE. And D is deriving IJ. Okay. So anything else? AB is not there. A already added. B is not there. F is not there. D part already added. So that is what the AC closure. Now AD closure. So first A and then D, and A is of course deriving DE. So D already there, right? So we no need to add 2 times, no duplicates allowed. And after that D is deriving IJ. So anything else possible. So AB, so simple, just to do FD by FD. If anything we need to add, you can add. So if nothing is added means you stop it. So that is what AB, no, A added, B, no, F is also not there. So D part is also added. So this is what the final. Now let us see the D closure. So D, and only one place D have directly, that is what IJ, and IJ are not there in any of these LHS part. So this is what the final thing. So in this way, attribute closure we can find out very easily. So that is what current iteration and previous iteration sets are same, then you can stop it. If sets are different, continue one more iteration actually, till where last 2 iterations sets are same actually. Okay. Hi. So now let us see how to find the total number of functional dependencies from a relation basing on the given FDs actually. So actually, how many total possible? Of course, in that trivial FDs will be there, non-trivial FDs will be there. But let us see how to calculate overall actually. So that is also sometimes important. Okay. So here, so the first thing is how many attributes are there in the given R? We have actually attribute A, attribute B, attribute C actually. All possible combinations we must consider. Then we can find the total number of FDs actually. All possible means, so how many subsets are possible? That is what from mathematics we can say. So that is what power set actually. So here, first thing is nothing you selected. So no attribute you selected. So 5 closer we are finding. So 5 closer is nothing but 5 only, right? Okay. Then let us select one attribute individually. So that means A first, A closer. So A closer deriving what? So A is deriving of course A itself, and then B actually. A is deriving B from the first FD. So 1 and 2 if you take. And then by adding B, now B is also deriving C, right? So by using second FD, you can add C also. So this is what entire table it is deriving. So fine, you can close it. Now let us go for the next single attribute, B closer. So in case of B closer, if you observe how many attributes it is deriving. So itself, first of all, and then B is deriving C actually. Yes. Then do you have A in the set? No. So this is what the final B closer set. Go for the C closer same way. Itself C first of all. And C is not exist in the LHS part anywhere. So that is why C is not deriving anything else except itself. So that is what C deriving C only. So this is what single attribute if you select. What if you select 2 attributes actually? That is what different combinations A, B closer. So in this case, you can see A you can add individually, B itself you can add first of all attributes, and A is deriving B, that is already covered. B is deriving C, so that you can add actually. So that's it. Next combination, for example, A C closer. See, A is there, A part of this entire closure actually. A, whatever deriving, everything definitely will exist. So every time you no need to go here. What A is deriving here, what C is deriving here, you just combine them actually. That is what the automatically the result also. So that is what A deriving A, B, C. That's it. Even if you work from this also, you will get same thing. Is it? So that is what. Now let us see BC closer. In case of BC closer, these two you just combine actually. Even that also you can observe. B you can add individually, C you can add individually. So that itself is deriving actually. So this is what another possibility. And one more thing, that is all three attributes if you select ABC closer. Of course, all attributes in the table we selected for closer, and all attributes itself, first of all, they will derive, right? So ABC you can write down. So what is the use of selecting all these things actually? So that is what total number of FDs we have to derive. So that part let us try to understand clearly. So what we are doing is here, for example, ABC, if I take this part, if I take, how many it is deriving actually. So here, whenever you have this many, I can write down. So for better, this let us take because it will take more actually. Understand from this actually. So B is deriving B from the set you can write down, and B is deriving C from this set we can write down, and B deriving together also BC. In this way also we can write down different forms we are writing, and B deriving nothing 5. So how many possibilities we have actually? 4 possibilities we have. That is nothing but 2 square. So this attribute B attribute may present in the RHS part, may not present in the RHS part. And C also may present, may not present. So how many attributes are there in the set? So B, C. So B not present, both the attributes not present, this is what. And B only present, this one. And C only present, this one. Both present, this one. So total how many possibilities are there? So number of symbols we used is 2, that is what base power. How many positions? 2 actually, number of positions. Number of positions. So in that way it is 2 square, base is 2, that is 0 or 1, and number of attributes are 2. So like this, here 0 attributes only 1 possibility, and here 2 power, how many attributes we have? 3 actually, 2 cube. Total FDs are possible 8 actually from this part. Like A deriving A deriving B, A deriving C, A deriving AB, A deriving BC, A deriving AC, and A deriving ABC, and A deriving nothing. That is what total 8. Got it? So this deriving 4, and here you have 1. That means 2 power 1 actually. That is what 2. C deriving nothing, C deriving C. Don't bother about the deriving 5, they are trivial attributes. We are simply asking total number of FDs actually. So here also 3 attributes. So 2 cube 8 FDs are possible. And here also 8 possible. Here 2 square, 2 attributes are there, 4 possible. And here 3 are there. So here also 8 possible. So total number of attributes, how many possible? Sum of all these things. So that is 1 plus 8 plus 4 plus 2 plus 8 plus 8 plus 4, this one, and this 8. So this total is how much? There are 8, there are 4 8s are there, 8 4s are 32, 32 plus 6, 38, 42 plus 1, 43 FDs are possible actually. So this is what answer for this question. Find the total number of FDs is 43. So in this way, how many attributes are there in that relation? Take the all possible combinations, okay, and find them individually. And like this, how many attributes you are getting in the set? That is what 2 power actually. Number of attributes in the set is in the power, then automatically how many FDs are possible by using that particular closure you will get, and then individually everything is you sum it. That is what overall possible FDs by using this given FD section. If this is changed, then this number is also going to change. That is what you have to inference understanding from this overall discussion. Okay. Hi. So now let us see one more problem for finding the total number of FDs actually. Okay. So here, these are the 2 FDs are given. By using this, let us try to find out total possible FDs actually. Okay. So it's same like the previous part only. So first we will let us try to find out 5 closure. So that is nothing but 5 only, nothing it is deriving. Next, let us take a single attribute. So that is what A closure. So of course, A is deriving itself. Now A is deriving B actually here. Okay, so let us add that. Now AB is deriving C. So that is what. And one thing is all attributes you derived in the table. So you can close it automatically. And then next possibility is B closure. So B closure is what? So you see here in the LHS part, individually B not there first of all. So that means it is deriving itself and no other attribute it is deriving. That is what in LHS part you must have individually here whatever attributes are there in the set. So B is not there, so you can stop the process for B closure actually. Same way for C closure also, even C of course it will derive C, but C is also not there individual in the any of these LHS part. So let us close it. Okay, and after that let us go for other combinations A-B closure with two attributes. So A-B closure, you see here A is there in the closure part. So whatever individually A deriving that you can add directly actually. That is what you no need to work every time here. What A is deriving here, what B is deriving here, you just combine them. That means perform union operation on these two sets. And if anything else attributes are remain, then you come back to here and you can derive actually. But in this case, all attributes are derived, so you can close it. And same way, AC closure quickly you can write down, right? So that is what A, B, C, because A is there, so all attributes deriving. Now if you see another combination, a BC closure. So BC closure is what? BC individually B and C, and nothing is there. B individually not deriving, C individually not deriving, or BC together also not deriving anything. So that is what this is over. And as usually, all attributes is nothing but all actually. So A, B, C. Now, basing on the previous discussion, so now you can write down directly because that it discussed clearly. So one, here 3 attributes are there. So that is what 2 cube, 8 FDs are possible. And here only one attribute is there, 2 power 1. So that is what 2 FDs are possible. And here also 2 power 1, 2 FDs are possible. Now here 3 attributes are there in the set. So 2 cube, that is what 8 FDs are possible. 2 cube, 8, and here 2 square, 4, and here 2 cube, 8. So this total summation is what actually? 1 plus 8 plus 2 plus 2, and 8 plus 8 plus 4 plus 8. So this is what total summation we took here. Okay. So that is what, how much? So 32, 36, 40, 41 FDs are possible from this actually. That is what F closure you can say. Okay. So 41 attributes FDs are possible. Functional dependencies are possible from this relation by using these FDs. Of course, as we discussed earlier, some of the FDs are not meaningful actually. That is what trivial attributes will be there. Okay, but here simply asking total number of FDs possible from this given relation actually. Okay. Hi. So till now we seen closure actually, attribute closure or FDs closure we say. Okay. So now by using this closure, we can do many things actually. So especially we have the applications by using this closure actually. Okay. So that is what, let us see first of all, what are all the applications by using this attribute closure. So all those things we are going to see individually, and those are the very important concepts for our normalization process. Okay. So let us see in this lecture, what are all applications we have. So the first one is we can find additional functional dependencies. Of course, that part we already seen in the previous lectures actually. So that we are going to see very formally what are all other additional functional dependencies, that too meaningful FDs we can derive from the existing FD section. So that is one simple application. And another one is we can find the key of a relation. What does it mean, key actually? Mainly candidate keys we can find out actually. See, of course, key is nothing but primary key, but primary key is also one of the candidate key. So we can find out all possible candidate keys by using this closure again. And of course, from that automatically you can get the super keys. So that is why we mentioned here super keys also. But the main thing is we can find all possible candidate keys. That is very important actually for our discussion. So that is one another application. And then we can find the equivalence of FDs. This is exclusively important when whenever one relation is there, and if you have two different sets of FDs. So that we will see very clearly. If you have two different sets of FDs from the same table for the same purpose, at that time, whether both the FDs are same or different, you have to compare them actually. When you compare them, if you are able to identify both of them is same, then we are going for the one set of FDs actually. So that is why you have to compare two sets of FDs. By using closure we can do it actually. Okay, so that we will get the clarity once we go for that concept. Okay, and then we can find the irreducible sets of FDs actually. See, this is canonical form you can call sometimes, or sometimes minimal set or irreducible set. So as name implies, you just try to understand irreducible. So further reducing is not possible. So such a FDs you can find actually. So from this also, especially fourth application is whenever you have set of FDs, in those FDs some may be duplicate, some may be not meaningful. So all such kind of things we are going to eliminate from the given FDs so that the result is actually the irreducible sets. And that also we will see very clearly. So the first of all, just try to understand that by using attribute closure, what are all things we can do actually? So these four things mainly we can do. So let us see all these four individually in the next lectures. Okay. Hi. So now let us see the first application by using closure actually. So the first one is finding additional functional dependencies. Okay. So that means we have already some FDs actually for the relation, and now you are going to derive new one basing on the given FDs actually. So that is what actually the functional dependency X is deriving A is possible if and only if Fx closure contains A actually. So don't bother about this meaning. That will be clear if you understand one simple example. So you can see here R is we have three attributes in this relation R, and these are the two FDs we have actually. Now let us see one simple questions. Is AC deriving B possible or not? And BC deriving A possible or not? So let us cross check them. So very easily you can cross it. So what you have here, AC. So AC closure you just find out. Of course, A and C you can add automatically. Now you come to this part. So A deriving B, right? So A is there. LHS part of this FD already there in the set. So RHS part you can add actually. So this is what. Now AC is deriving, you can write down like this. AC is deriving ABC. And by using this decomposition rule, you can write down as AC deriving B actually. So that is what asking, right? Is AC deriving B possible? Yes, it is possible. So this is possible actually. Now same way, let us come here. So this is what one extra additional FD you derived from this part. So that is what X closure contains A. Yes, AC closure contains that B. So you can say this is a valid FD actually. So that you can include in this set actually. Now, same way, BC closure deriving A or not. So same way, let us find first of all BC closure. So BC individually first of all. Then, so there is no B individually, there is no C individually in the any FD, and together BC also not there. So that means this is what the final closure of BC. Now, from this, do you have, that means BC deriving A actually, do you have A in the set? That is what A in the set? No. That is why this is invalid. It is not a valid FD actually. So is BC deriving A possible? No, it is not possible actually. Simple. So that is what additional FDs you can find out very easily by using this closure property actually. Hi. So now let us see another application. So that is finding the keys of a relation. So that is what the second application of a closure, right? So now how you can find out the keys? That is nothing but finding the finally candidate keys. Okay. So that is very simple. If you see for any attribute X closure, if you find is a set of all attributes that can determine using X actually. So this is normal discussion, like how to find the closure. And we are going to get a one set, right? So we are going to get set of attributes. If that set contains all attributes of a relation, then X we can call as a super key. Okay. So that is what you see. First of all, you are going to find the X closure. Then we are going to get a some set. If this set contains all attributes of a relation, then we are going to call that X as a super key. And further, if you see, if X is minimal set, okay, that means if you remove any attribute from the set, still if you are able to get the same derivation, then that is not minimal. That means reducible is possible. But if you remove any attribute from the given set, and if you are not able to derive all attributes, that is irreducible set. That is what minimal set. Then such a minimal set X calling as candidate key. So that we can find out very easily. So this is what first of all meaning. So these two sentences meaning you will get the more clarity once after doing this example. So this is what the given table. In this table, we have to find out the possible keys actually, possible candidate keys. How and all. So let us try individually. So single attribute you take, try to find out the it's a key closer actually. So for that, I am going to take A first, A closer. What is A closer? So A individually you can write down. And then A is deriving B, add B here. And because B is there in the set already, B deriving C, add that. Observe that X closure, if you find that closure contains all attributes. Yes, A closure contains all attributes in the relation. So you can take A as a candidate key. So let it be. Now find out B closure also. Is B deriving all attributes? So B itself and B deriving C. And no other attribute, right? It is deriving. So because it is not deriving all attributes, B is not a candidate. And next C closure also, if you try, C is deriving C only. Nothing is there because there is no C in the LHS part. So let it be. So this is what if you observe, candidate key, if you see, candidate key is what actually only A. It is deriving all attributes. Now, if you come to this part, super key part. So why it is calling super key? So super key definition we already seen. For the candidate key A, if you add any attributes, that may be a B, that may be a C, then that will derive automatically all attributes in the relation that you can cross-check. And now try to understand this meaning, minimal set. This is the minimal set. This is the minimal set, but this is not the minimal set. Because even if I remove B also, I am getting ABC. Even if I remove C also, I am getting ABC. These two, A, B, A, C, or super keys actually. So its a minimal form is actually a candidate key. So try to understand this differentiation, very important. So in this way, simply we can find out the candidate keys. So simple, any attribute or combination of attributes closer, if they are giving all attributes in the relation, then that closer is calling as a candidate key. For that candidate key, you add any attribute, definitely that is deriving all other attributes, all attributes in the relation. Then those are calling as a super keys actually. So that keys definition wise we've seen already. Okay. So let us practice one more thing. Try to find out the candidate keys. So now in this example, you can try what are the candidate keys. Okay. So here, if you see individually A closer, if you try to find out, we are getting A only. Is it or not? And B closer, if you try to find out, we are getting B only. B and D actually. See here from this FD. Further is not possible. So C closer, if you find C only. D closer, if you find D only we are getting. So with a single attribute closer, we are unable to find all the attributes in the relation. So let us go for the combination of two actually. So let us try to find out A-B closer. If you try to find out the A-B closer, A individually, B individually, and AB is deriving C, that AB is already there in the set, C actually, and B deriving D, so B already there. Yes, this is deriving all attributes in the relation. So this is one candidate key. Let us take another possible keys actually. So that is what, for example, BC closer, if you take BC closer. So B and C fine, B is deriving D fine, but A is not deriving. See, from this what you can say is simply observe the RHS part, observe the RHS part. Out of all attributes in the relation, which attributes are not there in the RHS? C is there, D is there, but A is not there, B is not there. Simple thumb rule when you are finding the candidate key. In the RHS of all attributes, whichever attributes are not there, you just note down here. So A is there? No. In any of FD's RHS part, A is not there. Same way, B is also not there. C is there? Yes, there. D is there? Yes, there. So these are the attributes definitely part of candidate key. That is the simple thumb rule. So what are all attributes not there in any FD's RHS part? All those attributes, combine them, those attributes definitely part. And after that, you may have any other attributes, may have. But in this case, that is why A, B closer, if you try to find out first, that is what it is deriving all attributes, right? So candidate key is AB. And of course, super keys are AB. For the AB, you add either C or D or ABCD. Definitely AB must be there. So this is what actually finding the candidate case for this given relation R. Okay. So in this way, the thumb rule is this here just practiced, but here now onwards, you have to go like this to get the answer very in less time. What are all attributes not part in the any of FD's RHS? Then collect all those attributes, find out their closure first of all. Or simply you can say those attributes definitely part of candidate key. So here only one candidate key is possible, that is AB. Okay. Hi. So now let us see another example for finding the keys actually. Okay. So this is the example. So in this table, we have 4 attributes and 3 FDs are given, functional dependencies. So from this, let us try to find out all possible candidate keys actually. So as I told in the last example, in the RHS part, whichever attributes are not present in any of FD, collect those attributes first of all. So let us see, A is not there in any of these 3 attributes actually. So let us take A. And B is there, C is there, D is there. So this is what the first thing. Now let us try to find out. So always whichever attributes are not there in the RHS part, for those attributes, altogether try to find out the closure. Let us see what we are getting here. Of course, A. So here if you observe A deriving B, so let us take B. And AB deriving C, let us take C. And C deriving D actually. So if you observe the whatever attributes are not there in the RHS part, if that itself deriving all attributes in the table, all attributes in the relation, then that is going to become candidate key. That is only one available candidate key you can conclude actually. Is it clear? So this is the only candidate key. Of course, super keys are what actually? For the candidate key, you can add anything. So AB or AC or AD or ABC, like this. Any thing is possible actually. So there must be a candidate key. For that, you must add any other non-candidate key attributes actually. Okay, so that is what finding the keys in this example actually. So let us see one more example here. And in this example, if you see, 3 attributes are there in the relation. Now, which attributes are not there in the RHS part? A is there, B is there, C is there. All are there. So now let us go individually. So A closure, let us try to find out. A closure is giving A, so it is not possible. B closure, if you try to find out, B is also not deriving anything here. And C closure, if you see, C and C is deriving AB actually. So in this case, C is deriving all attributes in the relation. Is it clear? So this is one candidate key. Okay. Now let us see, this is one candidate key. Now let us see AB closure, let us take AB closure. So A and B, AB together deriving C actually. So even AB closure also deriving all attributes, right? So this is another possible candidate key. Okay, so candidate keys are either C or AB. Okay, so in this case, we have 2 candidate keys. Okay, and of course, super keys are what actually? AB. For that, if you add C, ABC, of course, AB is candidate key, super key, ABC is also super key, or CA is super key, CB is also super key. So these are all the possible super keys actually. Okay. Hi. So now let us see another example for finding the candidate keys actually. Okay. So in this example, so if you see, as usually, always in the RHS part, whichever keys are not there, whichever attributes are not there, let us collect them. So B. So in this case, if you try to find out the B closure, it is deriving only B actually. Okay. So B is not a candidate key alone. So for the B, you must add other attributes actually. So let us start with the A. So let us find the BA closure. So BA closure, if you find, that means AB closure. So A, B, and together they are deriving C also. So you see, it is deriving all attributes in the relation. So BA closure, that means AB closure is the one possible candidate key. And let us see for the B, let us add another attribute, that is C actually. BC closure. So BC and then BC deriving A actually. So A here. And this is also another possible candidate key. Is it clear? So in this case, we have 2 candidate keys. So that is, one is AB and another one is BC. So as we are saying that, so you see, whichever key is not there in the RHS part, that key is the mandatory attribute. That attribute is the mandatory one in the candidate key. And for that, you add extra attributes to get a candidate key section. Okay. So now let us take another one. So here also, if you see 3 attributes are there. So A, B, C, all of them are there. So let us go now individually. A closer, if you find what we are getting, A deriving B, and B is there. So B deriving C. So A derived all attributes actually. Now let us go for the B closer also. So B deriving C actually, B, and B deriving C, and C deriving A actually. So even in this case also, it is deriving all attributes. So even B is also candidate key. Even let us check C closer. So C deriving A and A deriving B. So you can see C is also deriving all attributes. So individually every attribute is candidate key. So total candidate keys in this example is A, B, C. All of them individually candidate keys. Okay. Hi. So now let us see in this example how to find the candidate keys. So here total 5 attributes are there. So what are all possible candidate keys? Let us try to find actually. So first thing is in this RHS part, which attributes are not there? So A is not there. Let us take that. B is there, C is there, D is there, E is not there. Okay. Now let us try to find out AE closer first of all. Okay. So if you find the AE closer first, we are going to get first A and then E. Now let us see. A is deriving BC here. Let us take B and C. And B is deriving, because B is already part in the set, so B is deriving D. So in this case, if you observe, AE closer deriving all attributes in the relation. So this itself more than enough that AE is the only one possible candidate key. So the candidate key is AE. See, whatever attributes are not there in the RHS part, if those attributes closer itself is giving all attributes in the relation, then that is actually the candidate key. Okay. So in this case, only one candidate key is there. So that is AE actually. Okay. Now let us take another one. So in this case, total 4 attributes are there in here actually. So here also let us try to find. Let us try to find here which are not there in the RHS part. So A is not there, B is there, C is not there. So AC closer, if you find what we are getting. Here also, first of all, A and C. A is deriving B, note down. And C is deriving D, note down. So in this case also, it is deriving all attributes in the relation. So the candidate key is what? AC only. Okay. So this is only one possible candidate key. Okay. Hi. So now let us find the candidate key for this example. Okay. So here if you see which attribute is not there in the RHS part, B is not there. Let us take B here. So if you find B closer, we are unable to find all attributes that you can observe. Only B we are getting. So let us take along with B other attributes one by one. So B A closer. So that is what AB closer. So here AB is deriving C, right? So that is what you can take A, B and C. It is deriving all attributes actually. And here one thing if you observe, B, here we have a name called, already we discussed it, prime attribute. Okay. So prime attribute. What is prime attribute actually? Attributes which are in candidate key actually. So A will become a prime attribute, B will become prime attribute. And if you observe, A is a prime attribute, that A is there in the RHS of this functional dependency actually. A is there in the RHS side. So B already there, B must be there in the candidate key. In the A place, it's LHS you can replace actually. What is its LHS C? So this also going to become automatically candidate key. Got it or not? So B A is the candidate key and A is the prime attribute, and A prime attribute is deriving by one attribute actually. So that is some LHS. So in the prime attribute place, in the actual candidate key, you substitute that LHS part actually. That is what this one. So LHS part is BC, C. So that is altogether BC. Let us find the BC closer. Observe what we are getting. Of course, B and C. Then C is deriving A, right? So in that way, this is also a candidate key actually. So in this case, we have two candidate keys, that is AB and BC. Okay. And let us take another example here. So here total 4 attributes are there. In this, let us see first of all, A is not there in the RHS side. Is it or not? So let us try to find out the A closer first. You will get A, and A individually is not deriving anything. So that means A closer this one only. Now, so but A is the mandatory part in the candidate key. So along with this, let us consider all other attributes one by one. So let us find AB closer. What we are getting, observe. AB is deriving C and C is deriving B here. Okay, but B is deriving D here. Let us collect that also. So you can see all attributes are there in the closure. So AB is one possible candidate key. Now next, along with A, let us take C also. Because in this position, you can place anything. And if you observe, B is deriving. See, from this point, whatever we discussed here, that you can apply here also, right? So that is why I am writing directly A. B is there in the RHS of these two FDs. So what is there in the LHS? C. AC one candidate key, and here B, its LHS is D. So AD is one candidate key. So total candidate keys are how many? 3 candidate keys are there. That is AB, AC, AD. That even you can cross check also. AC closer if you find AC, C deriving B and B deriving D. That's it. Whether we got all attributes or not. So similarly, AD closer also you can cross check. That is what AD. So D deriving B, so that B deriving D, and then AB deriving C. So we have C, all attributes. So that is why here total 3 candidate keys are there. So in this way, actually, if you practice more, you will get some points automatically actually. You don't need to find out for every pair what attributes it is deriving. By having some shortcuts, you can simply finalize which is candidate key, which is not candidate key. Okay. Hi. So now let us see another example for finding a candidate key. So if you observe here, all attributes are there in the RHS part. So let us try to find out individually everyone. So if you try to find out A closer, we are getting only A. Okay. So it is not a possible candidate key. So B closer you can try. So if you try B closer, so B we are getting and D we are getting. So B deriving D, right? And D deriving B only. So this is also not possible. And C closer if you try, C deriving A. A or AC together not deriving anything else. So this is also not possible. And D closer. So D closer also same thing. D and B is deriving. That is what D deriving B, B deriving B. So here if you observe next A B closer if you try. Okay. then there may be a chance. So let us see, A, B closer. So we are getting A and then B, A, B deriving C, and here C deriving A, but B deriving D actually. So A, B deriving all attributes in a relation. So that is why this is a one possible candidate key. And from this, if you observe, A is their prime attribute in this RHS part, in this FD. That means what is its LHS part? C. So replace C in this position, remaining write down as it is. Let us cross check CB closer what it is doing. So CB, C deriving A, then it's fine. A, B are there. So A, B deriving D actually. So this is also possible candidate key. And another one, if you observe, here B is a candidate key. So B is RHS side. So A, let us take as it is, and B, LHS is D. Even this is also candidate key. You don't need to cross check also. Okay. Even if you check, we will get the same thing. Okay. So that is what this is another possible candidate key actually. And is there any other possible candidate key? So you can cross check actually. So that is, if you see here, A is there again. A is there. A is a LHS part here, RHS part here. In that place, if you substitute C, D is another possible candidate key. Is it or not? So is there anything else? So all possible combinations you can take actually. So BD is not possible. Okay. So I think these are the only candidate keys. So the candidate keys in this relation is AB one candidate key, CB one candidate key, AD another candidate key, CD another candidate key. So total we have 4 candidate keys actually. Now let us take the another one. So in this, if you see RHS side, A is there, B is there, C is not there. Of course, individually C is not deriving anything. So C closer are not going to give all attributes actually. So let us go for the combinations. So let us take CA closer. So CA closer, if you try to find out CA and A deriving D, right? So let us take B. BC is there, BC deriving D, yes, correct. And D deriving AE, A already there, let us take E actually. So this is one possible candidate key. And CB, let us take CB closer. So CB already part. And then, BC deriving D, right? Let us take D. D deriving AE, both of them not there, add them. So even this is also deriving all attributes in a relation. Okay. Now let us take CD closer. So CD closer, CD, D deriving AE, so A, E, of course A deriving B actually. Even this is also one possible candidate key. Next CE closer, let us try. Okay, so CE. So anything else, is it deriving? No, actually. E is not there individually, C is not there, or together also not there in the LHS part. So that is why this is not a candidate key. Okay, so total 3 candidate keys are there. What are those? That is a CA, CB, CD. So these are the 3 candidate keys here, and here 4 candidate keys. Okay. Hi. So now let us see another example. So here 5 attributes are there and 3 FDs are there. So let us try to find out which attributes are not there in the RHS part. So A is not there, and B is there, C is there, D is not there. So first of all, let us try to find out individually A, D closer. So because we are practicing more examples, as we already done more examples. See, A, D, you don't have in the LHS part. So even if you try to find out AD closer, it is not going to give all attributes actually. You can observe that here. So that is why along with the AD, let us go for other attributes combination. So this is the mandatory part. Now let us take B. So that means A, D, B closer altogether. So that means as usually A, D, B are there in the set. Now let us go here, A, B. So AB is there. So AB deriving C, add C here because not there. And then CD, C, D are there in the set. So CD is deriving E. So that means this is one possible candidate key, A, D, B actually. And another one, A, D. Let us take the next attribute C actually, closer. So as usually A, D, C. And observe that CD here, CD here. CD is deriving E. And further, DE deriving B actually, DE deriving B. So that means it is also deriving all attributes. So this is one possible candidate key. Now next, AD, another possibility is E actually, ADE closer. So in this, ADE and DE deriving B and AB deriving C. So this is another possible. So these are the three possible candidate keys actually, because all of them we already included. Okay. So even if you take extra anything, that will become super key, not the candidate key. So that is why all possible candidate keys are ADB, ADC, ADE. So these are the three candidate keys possible from this actually. So let us take another one. So even here also you can do quickly now because we have enough practice. A, B, C is not there, and then D is also not there. Observe that C, D deriving anything else here? No. Are individually C or D deriving anything? No. So that means along with these two attributes, you must have other attributes actually. So that is why this is the mandatory part in the candidate key. And other attributes, let us add one by one. C, D, A closer, let us try to find out. So that is what A, C, D, and A deriving B, yes, and B, C deriving E actually, correct. So this is one possible candidate key. Next, C, D, another attribute possible is B, let us take. So that is what B, C, D, B, C deriving E actually, let us take that. And ED, ED deriving A. So even this is also giving all other attributes actually. So this is also possible candidate key. Then CD, what is another possibility? AB is over. So E only remain. CDE closer. So CDE and ED deriving A and A deriving B. So that's it. Okay. So this is what actually another possible candidate key. So in this case also, total possible candidate keys are how many? 3. Those are ADC and BDC and CDE. So here also 3 candidate keys are there. Okay. Hi. So now let us see another application of this closure, attribute closure, that is equivalence of functional dependencies actually. So as we told that whenever we have a one relation, upon that if different sets of FDs are prepared, so which one is better one to take? First of all, you have to compare them, both of them doing the same job or not. So for that, well, how to compare them actually, whether both of them is equal or not, for that we are going to have a one procedure. So that is actually two sets of functional dependencies, F and G are there, are said to be equivalent if and only if F closure and G closure must be same. So as we are saying that, for example, there is a relation R. Upon this, if you derive one set of FDs and another person derived another set of FDs, so which one you have to consider? So to consider which one is better, first of all, both must be same actually. So which one is same? How you both of them is doing the same job or not? So to cross check, that is what that cross checking is the equivalence. Okay, so this is nothing but equivalence means that every dependency of F can be determined using G, and every every dependency of G can be determined using F actually. So that is what actually F equal to G if and only if F is going to cover G, G is going to cover F, then that is actually equivalence. So this whole statements, these three statements, we can understand very easily with simple example actually. So let us take here, we are going to test whether these two FDs are same or not on this relation R. Okay, so that is what. So as he told, F covers G. So what is meaning of F covers G? Let us try to observe that. F covers G actually. What does it mean? Let us observe. So F we are covering G actually. So that means G FDs we are covering in F. That means let us take this first FD. A derives BD. From G we are covering in F actually. So that is what A derives BD. So that means LHS part is A, find out its closure. In F you must derive BD actually. Then this attribute you are covering in F actually. So you can see A closure if I find in by using F attribute, FDs. So A closure here, A deriving B, A, B, and then A, B deriving D actually. By using F, we are getting this one. That is D we are getting. See, whatever it is deriving, other things, we are not bothering. The only thing is, in the RHS part, whatever you have, that you must get in its A closure by using F. So yes, we have BT. So this is fine. So if it is deriving any other, that is also fine. But in this case, I think it is deriving ABT only. So let it. So this attribute, this FD, we are covering in F from G actually. Now let us take another thing also. C derives A. In this case, C closure if you find C, we must derive A from F actually. So here C deriving AD. So AD. You can observe RHS we covered from F actually. Of course, it will derive other things also. So A derives B. So C derives AD. A derives B. AB derives, okay. So it is deriving all attributes. So this is also fine. So that means F covers G is fine. Same way, let us go for G covers F. Let us check this one. G covers F. What does it mean? FDs you must cover in G actually. So that is what. Let us take the first one. AB derives D. That means AB closure you find in G. AB closure if you try to find A, B, we must get D actually. So here you can see A deriving BD, B already there, take D actually. So D we covered by using GFDs. So this is fine. Now let us take the next one. A derives B. So if I find A closure by using GFDs, I must get the B actually. I must determine B. So A closure deriving A, B, D. So we are able to derive B. So this is also fine. And then next what you have, C derives AD. C derives AD. So if you find C closure, what we are getting? So C closure C and C derives A. So already A we covered. Next A derives BD. So BD. So you observe both AD we covered C in C closure by using GFTs. So that means G is also covering F actually. So since both of them covering both, so you can say G is equal to F. Both of them is same. So actually, why we are going for this one, equivalence? So that is actually inference point. If you observe F and G derived for the same table, derived for the same table. So which is set of FDs we have to consider? Always see these FDs is nothing but set of rules actually. If rules are more, you don't have flexibility actually more. If rules are less, you have a lot of flexibility. So that is why recommended one is always less number of FDs. Less number of FDs set is the more flexible to implement actually. So since here 3 FDs are there, here 2 FDs are there. So this is the better one than this actually. So you can select G because both of them is same, right? Any set of FDs are same. So that is why which you are going to adopt for your implementation this relation. So F or G at that time, because both of them is same, I will go for the less FDs table, FDs set actually. So you are going for the G. With the G, you are going to implement relation R. Okay. Hi. So now let us take this example for finding these two set of FDs are same or not over this relation R. Okay. So the first one is F covers G. Let us find this one. F covers G actually. So in this case, if you see G, you have A, E in the LHS site. So let us find the A closer. Let us find A closer. So that you must get the CD from F actually. So if I find A closer, here A, of course A deriving C. Okay, fine. Then AC deriving D. See, this is more than enough, right? C and D we need to get from A closer. So that we already got. So that means this is fine. This part is you got actually. And of course, remaining things, if it is deriving anything, you can collect actually. But for us, this is more than enough. And then E closer, let us try to find. So E closer from F, we have to find. So E, and in the E closer, you must have AH. So E closer, here E is deriving AD. Let us take them. AD. So A we have, H we need. So here E deriving H also. So that's it. So AH we got. So that means F covers G is fine. And then let us take the G covers F. So whether it is doing or not, let us check. G covers F. Now that meaning is A closer, AC closer, E closer we have to find. So A closer, if you see what we are getting. A closer from this actually, A deriving CD. So that is more than enough. We need to derive C, so that we got it here. Then next AC closer. AC closer. So this you can finalize AC closer if you try to find out. When you find A closer itself, D we have. So that means AC closer means definitely you will get D from this. So that is what the ACT. So we have D that we covered actually. Next, E closer. In case of E closer is AD, here also E, ADH we have to get. So let us see here. E deriving AH, and A deriving CD. So now you can see we need ADH. So AHD, all of them is there. So this is also fine. So when these two are same, so what you can write down actually, therefore F is equal to G actually. Both of them is same. Now because both of them is same, which set of FDs we are going to consider for our implementation? So that is what here G have less number of FDs actually. Okay, than F actually. So you can go for G for implementation because both of them same, right? So that is the reason we are going for G. Okay. So now let us see another example for the equivalence actually. So first let us try to find out F covers G. Okay. So in case of F covers G means BC closure must cover D in the F and A closure must cover B in F. Okay. So first let us try to find out BC closure from F actually. So B and C. So BC, B deriving D. So that itself more than enough, right? We need D so that we are able to derive from the F. And same way, A closure. So let us try to find out the A closure from F. So A closure, if you try to find out A deriving B, so that is what? B A deriving B. So that is more than enough. So here directly this FD is common in both. So you don't need to find out also because when you have same FDs in both. Okay. So that means F is covering G actually. This is fine. But when you come to G covers F, let us check. G covers F actually. In this case, AB closure must have C in G actually. So AB closure, let us try to find out from G. So A, B, we must get C actually. So here you see A deriving B, so B already there, but A, B together also not there. So finally we are unable to get the C actually. So that means this is, so A, B covering C is not possible in G actually. So that is the reason both of them is not same. So simply F is not equal to G actually. Even if you take further, at least one FD, if you are unable to cover in another set of FDs, that is enough to say that both set of FDs are not same. They are not equivalent actually. Okay. So this is a simple example which is for not equal actually. Okay. Hi. So now let us see another example for finding the equivalence of two set of FDs actually. So now in this relation, we have total 8 attributes are there and two sets of FDs are given. So now let us first of all check that F covers G or not. So F covers G. Okay. So F covers G means let us get the all LHS of G from F actually. So that means A closure if you find from G, that means A closure in F must cover BC. So A closure, A is deriving B and of course A is also there. So AB covering C. So we got BC, right? So that is actually required thing. So this is fine. This FD is fine in F. Now let us find the D closure actually. So if you try to find out the D closure, D include, here D is covering AC. Ultimately what we need, AB required. So AB you must cover. So D deriving AC and D deriving E. Okay, B not at came and A deriving B actually. So you can take B. So that is more than enough for us. That means A, B are there when you find the D closure. So F is covering G actually. So both the FDs are covered in F. So that is why F covers G is fine. Next, G covers F or not, let us check. G covers F. Sometimes they will ask the specific, not only just whether they are equal or not. If they are not equal, in which part they are not equal, we have to mention actually. That is why try to practice everything. F FDs you must cover in G. That means A closure, AB closure, D closure, D closure we have to find from G actually. So I'm trying to find A closure first of all. A deriving BC here. What we need actually? We need B. Yes, we got B. So this first FD is fine. Now let us take the next one, AB actually. So that means AB closure if you try to find out A and B, and A deriving B. Okay, fine. AB deriving C. Okay, from this A deriving BC, right? So C we got A deriving BC. So that is what C required. Yes, we have C. Then find out D closer. So D closer. D. So D is deriving AB. Let us take AB. So here D deriving AC actually, because AD derived, A deriving again BC. So let us take C. So AC required, yes, AC is there. Even this FD is also fine in F. Find out D deriving E or not. So that is what D closer, if you find, what is going to happen. So D deriving AB and A deriving BC, B is there, C is not. And this is the only possibility in from G actually, because E, attribute E is not there anywhere here. That means deriving E is not possible from G actually. But here we have a FD, D derives E. That means this is all these three fine, but this we are not able to cover. D derives E, not able to cover in G actually. So that is why only because of this FD, we can say F is not equal to G, therefore. That is what the simply we can decide. At least one FD, if you are not able to cover from the other set of FDs, then both the sets are not same actually, simply. Okay. Hi. So now let us see fourth application, that is finding irreducible set. So as name implies, reducible, and here it is actually irreducible. So let us see, further reducing is not possible. Simply its meaning is. So let us see what does it mean. A minimal cover of the set of functional dependencies F is a set of FDs G such that every dependency of F is in the closure of G actually. So that is actually every dependency of F can be determined by using G. So that is what previously we discussed already. Equivalence actually. F covers G, G covers F. So in this case, a minimal cover of set of functional F is actually covering actual set G actually. So here G is calling a minimal set or irreducible set actually. So this statement is going to clear very much when once we see the example actually. So here if you see the procedure, how to find the irreducible set. So the step one is write a given set of functional dependencies in a such a way that each functional dependency contains exactly one attribute on its right hand side. So for example, just for understanding sake, if you have x derives CAP, then what we are doing is from this x derives A and x derives B. By using decomposition rule, we can write down like this, right? That is what actually he is saying. RH side, exactly one attribute must be there. Here two attributes, so we divided like this. Like that, how many attributes you have RH side, that many FDs individually, you please try to write down. And then what we have to do after that? So step 2, determine each FD one by one, whether it is essential or not. So here you see, if I find X closer by having this and by not having this. So that is what, once by considering FD present in the set. So this particular FD, if I take, if this FD consider and find the X closer, and once by considering FD not present in it actually. So without considering this FD one actually, by having this in the set of FDs, by not having in the set of FDs, so both if they are giving same result, then eliminate this FD actually. X to A we are going to eliminate from the set. If both are not same, this is essential. So that is what, whether it is essential or not. When it will become essential? If both results are not same. So this is going to become very simple when you are discussing example. Actually, immediately after this we will see. So like this, every FD we are going to cross check whether it is required or not. That means whether it is essential, mandatory or not in the set. We will try to decide from this step 2 actually. Then step 3, see actually x2 y if you take, where x is a set of attributes, y is a set of attributes. So this is RHS part. If you take, this is LHS part. For the RHS part, we are going to do step 2. Now in the step 3, we are going to do for LHS part. So that is what, check if there any functional dependency that contains more than one attribute on its left side. For example, now AB deriving X. Just opposite to this step 2 we are doing in step 3 actually, nothing is there. So you can see here what he told, contains more than one attribute. Yes, so you have more than one attribute, LHS side. So at that time, what we have to do? So for example, I'm going to take B. So A derives X like this I'm going to take. Am I able to get the same result without B also? So with without B with B, for example, if both the results are same, B is not required in the FD actually, in the LHS part. Is it or not? So that is what, for example, two persons are there in one day. One day they are getting the profit 10 rupees. And three persons are there next day, same 10 rupees they are getting. So by adding extra person, their result is not result is same actually. That means that third person not required actually. So that is why you can skip that third person. So same thing here also. Two attributes are there. By having B, by not having B, if you are able to generate the same result, that means B is not affecting anything actually. B contribution is nothing. So you can skip that actually. Same way we will cross check for A also. So without A, with A, if you are getting same result or not, we will observe. So that is what, compute the closure of all possible subsets of left hand side, all possible sets. So A is one subset, B is one subset, AB is another subset. Then if any subsets produce the same closure, result as produced by the entire left side, whatever result you have earlier, any one of the subset, if any subset produce the same result, then replace the left side with that subset actually. So for example, in this case, A is giving the same result, but here B is giving different results also. So because A and AB, both of them, if this is existing one and new subset A, if both of them giving same result, then this thing we are going to replace with A to X. That is what, then replace left hand side with this subset, that is what A. Now onwards, for the next steps, we are going to have this FD actually. So these things, whether you understand or not, just keep it in mind. Once we solve the one simple example, if you come back to the same steps, this is going to become very simple. Okay. Hi. So now let us check whatever is our understanding in the last lecture, that is finding the irreducible set. So on this set of FDs, let us try to find out canonical form actually. Okay. So what is the step 1 actually? As he told, our RHS side, we must have only one attribute. So that is what, if you write down this one, AB derives D, and A derives B, and C derives B. So here you can split actually. Okay, decomposition rule. So C derives D actually. Now here what we have to do actually, if you take every functional dependency, whether this is we need to essential or not, we have to find out. So for that, with this FD, without this FD, let us try to find out all possibilities actually. So you must derive D actually. So AB closure if I find, what I am getting. So without this FD, let us see. A is deriving, okay, you can take like this, AB first of all, and A derives B, but B already there. And are you able to then generate the D? No, actually, because here LHS side C only. So that is what we are unable to generate D. So this is essential. Now come for this actually. Let us try to find out A closure without having this FD. So that we must generate B actually. So if I find the A closure without having this FD, keep it in mind. Now these three only there in the set. So A closure A, fine. So here AB is there, here C is there. This is what the set. Even this is also not generating B. So that means this is also essential. Got it or not? Now let us go for this part. Find the C closure. If you find a C closure by not having this set, this FD, you must generate B actually. So is it possible? So it is generating C, of course, C generating D, fine. So, but we are unable to generate B actually. That is what, even this is also essential. Similarly, C closure, if you try to find out C, and here it is generating B. But we need D actually. But in from these three, by using C or B or by both combination, we are unable to generate D. So that is why this D we are unable to generate. So this is also essential. So that is what step 1 and step 2 we did. So step 1, writing LHS side all single attributes, RHS side single attributes, and then every attribute you take, whether it is valid or not, that means essential or not, you just cross check in this manner. So this is what step 2 done. Now in the step 3, what he is saying actually, so LHS side, observe actually. LHS side, anywhere if you have more than one attribute, consider that FD only. Because for these three, you have only one attribute. But for this FD, we have two attributes. Let us take that one first of all. AB derives D. And of course, we already concluded all of them are essential. So let it be. Now come to this part. AB derives D. Fine. Now let us check first of all without B with B. Okay. So without B, if you find the A closure, what we are getting actually. Okay. So if I find A closure without B, so what we are getting A, of course B. So then anything else are we getting? So these two only we are going to get actually. So here, of course, D we are generating. Now, AB closure, what we are getting? AB closure. So AB closure is generating. So that means with B. So AB, of course, D, of course, and then what else we are able to generate? So this only, right? So now here you can see, because both of them generating same set, what you can say, that is what this LHS part you can replace with that subset, right? That is what last point here it is saying. So then replace the left side with that subset. So that means this FD we can write down like this. AB, instead of B actually, you can write down simply A. So let us remove this part. So here A derives D, you can write down from this, and remaining is A derives B, C derives B, C derives D. So this further, if you try to reduce, this is minimal form actually, minimal set. And from this, what you can write down by union rule, A derives BD. So A derives BD, and C derives BD. So both of them deriving BD only. So this is canonical form. Okay, so that is what, if you observe here, this is the main thing. Without having one attribute, if you are able to generate it, that means all possible subsets. Even you can find out in this way also. B closer you find. B closer is finding what actually? That means A is not there. So when A is not there, if you try to find out B closer, so B and D, then here you are unable to generate any other actually. So that means this only. But both the things is same? No, actually, both of them is not same. But in this case, both of them is same. That is what you have to understand. So every individual attribute closure you find, and every subset also you try to find the closure. Whichever subset, if it is equal to total LHS closure, then that you can replace with that subset you can replace in the LHS part. That is what this is done. Now this is what the minimal form finally. So that you can write down like this. So this is the canonical form actually. Okay. Hi. So now let us see another example for the irreducible set actually. So this is what the given set of FDs or a table which have W, X, Y, Z attributes. Okay. So what is the step one? We must have RHS side only one attribute. So let us have that one first of all. So X derives W and WZ derives X, WZ derives Y. So from the second FD. And third FD, if you see, Y derives W, Y derives X, Y derives Z. Now from this, so what we have to do, this is what the step one. In the step two, what we have to do actually, take every set, every FD, whether it is essential or not, we just find out. If it is essential, we will keep it. If it is not essential, then we will simply remove it actually. So we will eliminate this in the set. So for that, what we have to do, so let us find the X closure. So from the remaining, if I am able to generate W, then this you can eliminate actually. So that is what, if I find the X closure, what I am getting. So if I find X closure, I am getting only X. Is it or not? So that means we are unable to generate W. So this is essential. Got it. Now let us go for the next FD, WZ closure. Even from the WZ closure, we must generate X. And without having this, let us see. So without having that, WZ here only there. So WZ and it is generating Y. Now you can see it is generating Y, fine. Y generating W, okay, already there. Y generating X. And Y generating, of course, Z already there. So now if you observe, we need X actually in the result. Yes, X we are able to generate. So that meaning is what? Without having this also, we can generate X actually. You can determine X actually. So this is not essential FD. Okay. Now same way, let us come for the third FD. So WZ closure. So of course, so WZ and then we must generate Y if possible. So WZ generating X. So let us note down that. And the X generating W already there. So to generate Y actually, with these three attributes, it is not possible actually. So that means we are unable to generate RHS part. Why? So what we will do? This is essential. That meaning is okay. Now let us come for the next one. Y closure. So Y closure, W must generate. So only with Y closure, Y is generating X, Y generating Z, but we need a W. So let us come here, X generating W. So you see here, X generating W, that is what RHS of this FD, right? Current FD. That means we are able to generate without having this FD also. So this is not essential again. So that you can skip, eliminate. Next, come for this one. Again, y closer without having that. So without having this FD, we must generate X. So let us see y generate y, of course y, and here y generating W, here y generating Z. Now WZ generating X. So that you note down actually. So what is our understanding? So it is generating X. So this is also not required. Got it. Now let us go for the Y closer, lost FD, this one. So here, Y generating, you can see directly Y generating WX, note down those two. And X generating W already there, WZ, because Z is not there. This is what the final. But we are unable to generate Z actually. So this is also essential. So that is the first thing. So all LHS closer you just try to find out. If you are able to generate RHS for that FD without considering that particular FD, current FD, we are able to generate RHS means you can eliminate actually. That means that FD is not essential. So this is what step 2 done. So which are all essential? Let us take them separately. So here if you take, so essential thing is X determines W and WZ determines Y and Y generates Z. Y generates Z. Now in the step 3, what he is saying, RHS side, if you have more than one attribute, LHS side. In the LHS side, if you have more than one attribute, then try to find out the every subset closer so that if you are able to generate Y, then you can skip that particular, you can take only that particular subset actually. So that is why W closer, let us try to find first. That means Z we skipped. So Z is not there. So in this, WZ generates Y. In this, Z we are skipping. It is not there. So W generates Y. Y generates Z. So this is what the result. And WZ closer is what? WZ closer, W, of course, Z. Of course, here W is there. We must take it. And WZ together generating Y. So this is what actually. So this is the final result. If you observe, without Z, with Z, you are able to generate same thing. That means Z don't have any importance here because we are generating the same set, right? So that is why we can skip Z from the LHS part. That meaning is this subset you can take in place of this LHS part. In the same way, let us cross check for Z closer also. So if you have Z closer, Z, of course, Y we will get, Y generates Z. But you are unable to generate W actually, only with Z. That means these two are not same. Got it or not? So that is why this subset giving the result, whatever LHS closer giving the result. So that is why in place of this LHS, you can write down W. So the final canonical form is X generate W. Here W generates Y and Y generates Z. Okay, so this is what the final canonical form. So in this way, very simple manner, we can find out actually. Okay.
Hi. So now let us see very, very important definitions. These are required for our normalization concept, that is partial functional dependency and full functional dependency. Okay. So let us try to understand these two. What are these partial and full functional dependency? So let us see the first of all partial functional dependency. So as name implies actually, we know already functionally dependent, its meaning. So some set of attributes deriving some other set of attributes. So that is functional dependency we see. But what is its meaning actually, partial? So you can see a functional dependency X to Y if you take, X is deriving Y. So here X is set of attributes and Y is also set of attributes. Is a partial dependency. When it will become partial dependency? If proper subset of X. So proper subset of X is determining and other non-key attributes actually. And we know already that key attributes, non-key attributes, that is nothing but prime attributes and non-prime attributes. Okay. So for better understanding, what we will do is, let us take a simple example. So here the relation is R, A, B, C, D. So total 4 attributes are there. And its corresponding FDs are these things actually. AB deriving C, B deriving D. The very first thing is whether it is partial dependency or not. To confirm that, identify the candidate key from this. So we already practiced a few things, a few examples that how to find the candidate key. So in the RHS, whichever attributes are not there, let us take them first of all. So here, A is not there, B is not there. Let us take AB. So try to find out AB closer. So AB closer, A, of course, A and B itself you can add. AB deriving C, okay, and B deriving D. B is there, so B deriving D. So because AB is deriving all attributes in the relation, then this is the candidate key. Is it or not? Candidate key is AB. So that means key is AB actually. Now, how you will decide whether it is a partial dependency or not? So, okay, here AB is deriving C. If you observe, B is a key attribute, prime attribute. So, A comma B are going to become prime attributes actually. Is it or not? So, that is what we already discussed this part. Now, individually, if A is deriving some other thing or B is deriving some other attributes, so then that is partial functional dependency. So here you can see AB deriving C. This is not a partial functional dependency, but LHS of B, if you take this one, B is a prime attribute. That is the part of the candidate key. Is it or not? So that deriving non-key attribute, non-prime attribute. So this is partial functional dependency. So, but this is not a partial functional dependency. AB deriving C is not a partial functional dependency actually. So always check like this. This is what the subset, proper subset. B is the subset of key, right? So that is what actually. Now let us take one more simple example. So if you take here also, we have 4 attributes in a relation, and AC deriving B, A deriving D, D deriving B. So what may be the key actually? So A is not there in the RHS part, A. So individually A deriving anything, so A closer if you find, so A and A deriving D, D deriving B. Okay, so this is not possible. So actually C is also there. So let us find AC closer. So if you find AC closer, A, C, and AC deriving B, and of course A deriving D. So this is the key actually. AC is the key. So key is going to become AC. Now if you observe, this is fine, LHS complete dependent. Non-key attributes B and D, non-key attribute dependent on complete key actually. That is what. But when you come to here, this functional dependency, A derives D. A is part of key actually. That is what proper subset. Proper subset deriving non-key attributes. So this is also going to become partial functional dependency. Okay. So in this way, any FD, whether it is a partial functional dependency or not, we can derive actually. First of all, you have to find the key. That is what candidate key you must identify. And then any proper subset of that candidate key deriving non-key attribute means that FD is going to become partial actually. Now let us see counterpart for this one, full functional dependency. So what is meaning of full functional dependency? That is what simple you see. If X and Y are the attribute set of relation, Y is fully functional dependent on X. Okay. If Y is functional dependent on X, but not on any proper subset of X actually. So that is what you can see here. For example, so what he is saying is X derives Y. So complete, so non-key attributes you are unable to derive with the proper subset of X actually, opposite to this one. So let us take one simple example here also. So here if you try to find out the key, A, B closure we are going to take because A and B are not there in the RHS part. So A, B closure if you find A comma B, AB deriving C, C deriving D. So that's it. So this is the key actually. So key is going to become AB. Now what is happening? You see, this is completely deriving non-key attribute. And here if you see this FD, C to D, C deriving D, C is not a part of key actually. That is what, right? Not a proper subset of X. So C is not a proper subset of X. So this is fine actually. So this is full functional dependency. Of course, this one is also full functional dependency. Okay, because all FDs in this set are full functional dependency. So this is not a problem actually. Okay, now let us take one more simple example here. So even here also try to identify A and C are not there in the right side. So AC closer if you try to find out A, C, AC deriving B here and B deriving D. So key is going to become AC. Now what we have to check is, this is fine, this is full functional dependency. Then B derives D, right? D is part of key? No. So this is full functional dependency. Here D is part of AC? No. So D derives B. So this is also full functional dependency. This is also full functional dependency. So there is no problem in this set of FDs actually. So this is what, first of all, partial functional dependency and full functional dependency. So in the key, if any prime attribute deriving non-key attribute, then that is partial functional dependency. If such a dependency is not there, then that is full functional dependency. Now, based on this understanding, what we can do is some important points you can write down. When partial dependency guaranteedly not exist in the table. So that is what you can see here. When partial dependency not exist in the table. So the case one is if primary key consists single attribute actually. So here if key have only one attribute, then there is no chance of having part, right? He is saying proper subset. Okay, so proper subset means not itself and not phi. So when you have a single attribute, there is no chance of having a part of that single attribute. So then you don't have partial functional dependency. And in the another case is if all attributes in a table are part of primary key. How many keys are there? How many attributes are there in the relation? If all of them are the keys actually, for example, key equal to ABC, then also there is no chance of having partial functional dependency. And one more case is there, if table consists only two attributes. At that time, either both of them are the candidate keys or primary key, or one of them is the candidate key. So if one means that scenario is this one, single attribute. So this is what actually, first of all, partial functional dependency, full functional dependency. These two things we are going to use in the normalization, especially second normal form actually. So second normal form is completely basing on these two definitions only. Okay. Hi. So now let us see one of the important concept, that is anomalies. Okay. So actually in a table, whenever you construct any table, that means what are all attributes we need in the table, after deciding, you have to cross check that some of the things actually. Sometimes some redundant data is going to be there. So, and it is going to lead many problems actually. So that is what anomalies we are going to observe. What are all different kinds of anomalies are possible if you don't have a good plan for the table construction. Okay, so that is what actually even we are going for the normalization to handle. One of the reason for the normalization, having the normalization, is to handle these anomalies. Okay, so now let us see first of all what is this anomaly. Anomalies in the DBMS is what actually when there is a too much redundancy data, to handle this redundant data and to not to lead sometimes this redundant data is going to lead to wrong information also. So that is why this is the one of the big problem in the database. So first of all, let us try to understand how many anomalies are there, what are those meanings, and then we will observe the solution how to handle these anomalies actually. So in that, we are going to take a one simple table to observe these anomalies elaborately. So this is the employee table, and try to understand that here EMP number is the primary key. So that is the simple thing. And assume that these are all the attributes and their corresponding data we have. So let it be this part. So here you can understand what is the much redundancy. So every employee definitely working under one of the department. So that is what department number we have. So wherever 10 is there, there you have a accounts. Wherever 20 is there, there you have a marketing. You can see 20 marketing, 20 marketing. Wherever 20 is there, marketing. So this is what the redundant data, right? So if I have 1 lakh records here, that means if I have 1 lakh employees, every employee definitely coming under one of the department. So every time same data you are repeating, that is nothing but redundancy, right? Whenever you have this kind of situation, what kind of problems we are going to face? So the very first anomaly is update anomaly. So update anomaly meaning is what? Let us read first of all this one clearly. When duplicate data is updated at one instance and not across all instances where it was duplicated, then that is the update anomaly. So very simply, let us try to observe here. Here, for example, marketing is there. So department number 20 meaning is marketing. What I want to do is the department number 20, I want to assign to some other department actually. So that is, for example, instead of marketing, I want to set this as a operations. One of my department is operations, that newly I assigned 20. So that is what you can see when duplicated data. So marketing, these many positions it is there. So duplicated data at one instance only we updated. So I updated here, or I may update it in one more instance also, but not all instances actually. So I didn't update it here, wherever marketing is there, didn't update it. Then what is going to happen actually? So if anybody asks what is the 20th department name, you are going to have at one place we have operations, yes or no? In another place we have a marketing. This is not possible, right? This is not realistic. One department number is for the one department name. So that is what, whenever duplicate data is there, if you update for the few instances and not updated for the other instances, then that is called update problem. How many times that marketing is there in this throughout the table, that many times you have to update actually. So that is also a big burden, first of all. And if you don't update some of the duplicate values, then that is leading to this kind of confusion problem actually. So conflict is going to happen. So this is one of the problem, that is update anomaly. Now let us try to understand another anomaly, that is deletion anomaly. So this is really very, very important. So you see, in case of deletion anomaly, what is going to happen? So you can see deletion anomaly. For example, you see deletion of some attributes which causes deletion of other attributes. So for example, here you see the Krishna employee number 1 his name is Krishna. So this employee assumed that he stopped doing the job in this company. So that means his record we have to delete from the database, right? So this is what you have to delete. So only Krishna you have to delete, but not that department actually. So that is what deletion of some attributes causing to deletion of other attributes actually. If I delete this one, you are also going to delete this actually. So what is happening? What is the thing is happening? If you don't delete, how it will exist without having a employee number actually? Because employee number is primary key, right? Primary key is nothing but what actually? Unique plus not null. So nulls are not allowed under this column. So that is the reason you have to delete these two the attributes data. Other attributes data also we have to delete. Okay, fine. We deleted. Assume that no problem. But see, what is the problem you are observing? Only one employee existed in this accounts department. Okay, later maybe some other employee may come under this accounts department, but that information is not available right now. So because of this lost employee in the account, if you are terminated, then this information also you are going to delete so that you are losing the department information also. Accounts department still there in the office. The only thing is employee you have to delete. But because of the employee you are deleting, other attributes like department number, department name also you have to delete because of this primary key constraint. So this is deletion anomaly. This is one kind of problem actually. Got it? Now, let us try to understand another anomaly, that is insertion anomaly. So this is also one serious problem. You can see insertion anomaly occurs when attributes cannot be inserted, into the database without presence of other attributes. So this is opposite to the deletion actually. If you are deleting some attributes, some other attributes you have to delete. If you want to insert some attributes, to insert those attributes, some other attributes information also you have to insert. What is that situation? Very simple, you see. Now you want to start a new department actually. You have one more department you are going to start today. So how you will insert that? Like this you have to insert. Suppose department number 40, its name is support. This department you want to create, you created today, so that you want to update in the database. Is it possible to insert like this in the database? Because here you have a null value. Because you just started that department, but no employees right now. So if there is no employees means in these three attributes are going to place null. In these two null, no problem, but here null is not allowed because it is a primary key. So because here you don't have any employee, you are unable to insert this department information. Now you read again the definition. Insertion anomaly occurs when attributes cannot be inserted into the database without presence of other attributes. Without having this information, you are unable to insert this information. So that is what simple example is that if you started a new department that we are unable to update in the employee table because of these three attributes information we don't have, or at least employee number we don't have right now. So because you have to place null, that is not allowed under the primary key actually. So this is called actually insertion anomaly. So this is actually child is inserted without parent. That means this is the parent actually. Okay, and this is the child. So you have to insert this one so that this you can insert further. Okay, so these are the major three problems you are facing if your database is not designed properly. So whenever you have this kind of situation, of course, we have a solution that is in the form of normalization. So that is what solution, just broadly let us try to understand here. These anomalies are avoided by normalization actually. So, and try to bring the tables in a granular state. So that means we are dividing this table into small pieces actually. So you are dividing these tables into small tables. So that is what actually, in simple words, it tries to split the tables into multiple tables actually, and define the relationship among these tables actually by using the keys. So these, especially this part, this you are dividing into employee table is one and DEPT table is another one. So in the employee table, we are going to have EMP number, E name, salary, and we have a department number. So this is what in the EMP table, and in the department table, DEPT number we are going to take and D name. So DEPT number is going to become primary key, and here employee number is going to become primary key. But this number we are using it here actually in the EMP table. So this is going to become foreign. This is just for immediate understanding what is the solution I'm just discussing. But we have a elaborated discussion how to split the tables whenever you want to, whenever you have this kind of the problems. What is the good strategy to divide actually? How to split the tables? All these things we will see in the normalization process. Okay. So in this lecture, we have to understand very clearly that what is update anomaly, what is deletion anomaly, what is insertion anomaly. So updation, you must be careful. How many times duplicate values are there? That many times you have to update clearly. If you miss any one of the duplicate value, then that is leading to conflict actually. So that is update anomaly. Deletion anomaly actually, deletion, if you want to delete some records, that is leading to delete some other records, and sometimes you may lose the actual required information. Like here, 10 and accounts department information you are losing. And insertion anomaly, if you want to insert some of the attributes data, to insert that information, we need another information which is not available right now. So that is what here, EMP number not available, but a new department data is available. So, but we are unable to insert this 40 and support. Okay. So for all these things, we are providing the solution in the form of normalization. So that we will see clearly in the coming lectures. Hi. So now let us see the main concept, whatever till now we discussed, that is the preparation for this concept only. So that is normalization. Okay. So this normalization is nothing if you understand functional dependency and its relevant concepts actually. That means simply whatever we done. Okay. So very easy manner, let us try to understand this normalization. So first of all, let us see some theory about this, and then how many normal forms are there. Just broadly, let us have an idea, and then one by one, let us get the clarity actually. So this is, for example, so this is actually, it is a process of organizing the data in the database. So if everything is there in the single table or two tables, when the database is big, then managing is not that much easy actually. So that is why to make the organization process is very easy, we can use the normalization process actually. Okay, that is one thing. And it is used to reduce the redundancy from the relation or set of relations. So redundant data easily you can identify and you can eliminate also, so that you can save the space actually. Okay. And then it is used to eliminate many, very importantly, anomalies. That is, one is insertion anomaly, deletion anomaly, update anomaly. So these things we already seen clearly. What is insertion, deletion, and update anomalies? By doing normalization, automatically we are going to eliminate these anomalies actually. Those things we will understand in the process. And it divides the law. Of course, this is what actually going to happen. How you are able to how these many applications are possible, these many advantages are possible is because it is dividing the large relation into smaller relations actually. Of course, without missing or without creating extra duplicates. Okay. And you are linking those relations accordingly. So those things, all these things we will see in the discussion.
So this is what just something about the normalization. What are all the benefits we are getting and how it is going to do. Now let us get the idea that how many normal forms we have. What are those actually? So if you see types of normal forms, the first one is first normal form. So very easy to remember. First normal form, in short, you can call as 1NF. And the second one is second normal form, 2NF. Then next, third normal form. Then the next one is bicode normal form. So this is BCNF in short, you can call. This is extension to third normal form actually. Nothing is there. Okay. And of course, fourth normal form. And then we have fifth normal form. So here mainly what you have to understand is, so here just we are saying broadly, everything we are going to see clearly in separate lecture. But let us have in which cases you can say this is first normal form, second normal form, or BCNF, or fourth or fifth. So that is what simply we are going to note down here. Atomic values. That means you must have a single value. You must have a single value in every cell actually. If you take any relation or table, every cell must have only one value, at most one value. Sometimes it may be not. That's it. Second normal form, if you see, it must be first of all in 1NF. That is always. And then full every FD must be full functional dependency. As we discussed its definition already. Okay. There should not be any partial functional dependencies. That is also important. So how we will identify those things and how we will eliminate partial dependencies, how we will make them all as a full functional dependencies, we will see in the discussion. Then when it comes to the third normal form, very importantly, it must be second normal form and then no transitive FDs actually. So along with this, we have another thing that is actually, we can say transitive is nothing but this is what actually. Every X either super key, every FD if you consider, LHS part either super key or RHS part must be prime attribute. All those things we will see actually. Then bicode normal form, when it comes to bicode normal form, you can see determinant must be super. That means if you take X to Y, X must be super key actually. That is what, only this one. This you are not going to allow. That is what bicode normal form. That is what we told extension of third normal form is the bicode normal form. Okay. Then the next one is fourth normal form, no multi-valued dependence. So that also we will get the clarity. And the fifth one is no giant dependency. So all these normal forms are going to reduce these anomalies. Redundant data is going to reduce. So that ultimately it is a table. It is dividing actually. Okay, but always going too much in normalization is also not recommended because it is increasing the complexity process actually. So that is why it's better up to bicode normal form is better actually. You no need to go up to fourth or fifth. The only thing is if you have a so the only thing is if you need, then only go for the 4 or 5 actually. Okay. So once after understanding this, we will come back to this point especially up to where it is recommended always, most of the times, and when you have to go for the fourth or fifth, we will see in the discussion. So this is what, first of all, I try to get the overall idea. What is normal form, what purpose we are doing this, and how many normal forms are there. Then in the coming lectures, let us see each normal form individually, elaborately. Okay. Hi. So now let us see the very first normal form, that is first normal form. Okay. This is very simple one. And this is the minimum thing we have to maintain whenever we are considering any relation, nothing but a table. Okay. So what is this one is, so you see the relation will be in first enough if it contains atomic values, very important. What does it mean? Single valued attributes. Okay. So there should not be any multiple values actually. So what does it mean is sometimes under some attributes, some cells going to have more than one value actually. So that is not going to allow in the first NF. Okay. It will not allow multi-valued attributes and composite attributes and their combination. So we've seen what is meaning of composite attributes actually. So for example, if you take a name, so name further you can divide it into first name, middle name, and last name. So such a composite attributes, it is not allowed. Simply overall, that is multi-valued attribute only. Okay. So for example, for getting the clarity of these words actually, let us take a one employee table. So assume that this is what the table we have. So you can observe that employee number 50 and his name is Ravi. When you come to the EMP phone number, he have two phone numbers actually. That is what multiple values under single cell. So this is one cell. In this cell, we have two values. So this is not allowed actually. Only one value must be there. That is called atomic values. If it have atomic values, then every cell, if it have atomic values, by default, it is in the first normal form. So this kind of things are not allowed actually. Not only this one, even John also have two phone numbers. And not only this attribute, you can see EMP email. Here, Jan have two mail IDs actually. So there are many attributes. There are two attributes which have multi-valued attributes actually. So this is not first of all in a first normal form. This is actually in a zero normal form. Now to make this one in a first normal form, what we have to do? So that is what actually employee table is not in first enough because EMP phone and EMP mail are multi-valued attributes very importantly. So what we have to do actually to convert into first normal form. So that is what here we are going to build. So before going to see, let us see what we are going to do is in every cell, we must have only atomic value. What we can do for this actually, this phone number, one time you add with this and another time you add with this. That means this whole data one time like this. So that means this Ravi record is going to exist two times. So how and all you will get the clarity you can see here. So this phone number with other cell data you can see and this phone number with other cell data. So now this is one record, this is one record. Though phone number, though employee number 52 times is there, but there is no atomic value, there is no multi-valued attributes actually. And when you come to the John actually, this phone number with this mail ID and this mail ID, so that is what 78, last number 78 if you take. Okay, so with XYZ one time, with PQR another time. And then same thing 89 also like this. It is like a Cartesian product actually. Okay, so this is now, this modified table is in the first normal form because you can observe that every cell have only atomic value. There is no multi-valued attribute. So by default actually, so every relation in the relational model must be in the first normal form. That is what we have to ensure actually. Okay. So this is the first normal form. Always ensure that if you want to go for the second normal form, you just cross-check that is there any multi-valued attribute or not. How and all, if any cell have more than one value, then that is not in a first normal form. So convert into first normal form. That means make distribute those values accordingly, so that it will become every cell going to have one value. So that is what atomic value for every cell. So that automatically it is in the first normal form. So that is what we are saying, that every relation in the relational model must be in the first normal form. Okay. Hi. So now let us see the second normal form. So which is one of the important normal form actually. So what is this second normal form? So simply first of all definition wise, if any relation is in the second normal form, how it will be says, first of all it must be in the first normal form. That is as usual actually. Here very important thing is every non-primary key attribute is fully functionally dependent on primary key actually. Okay. So here we already discussed that in the last lecture in the functional dependencies concepts, we discussed that partial functional dependency, and full functional dependency. So he is talking about this one actually. So every non-primary key, every non-key attribute fully functionally dependent on primary key actually. There should not be any partial functional dependency. So you are going to have set of FDs, right? So each FD you have to cross check that whether it is full functional dependency or not. If every FD in that set is full functional dependency, then we can say that is in the second normal form. Otherwise, if there any partial functional dependency, then we can say it is not in the second normal form actually. Let us take a simple example. For example, this is what your primary key, where you have set of attributes. Assume that a primary key have more than one attribute combination. Then if you take any non-key attribute, so primary key is going to derive completely this non-key attribute. So that is what full functional dependency we can say. So another non-key attribute also, if you take every non-key attribute, you are in a position to derive with full functional dependency actually. But sometimes what is going to happen? So for example, our key is AB assume. For example, for better understanding. So that means our key is this one A and B. So some attributes, for example, so attribute C, you are deriving by using both actually A, B. So that is going to become full functional dependency. But some attributes, if you see, by using, for example, attribute D is there, we are deriving by using B only. That is why it is coming from inside. This meaning is both. And some other attributes are there, that is you are deriving by using A. So this is partial functional dependency. That is what I try to understand. So this kind of FDs should not be there to tell you if it is in a second normal form. So B deriving some attributes separately, A deriving some attributes separately. That is what actually prime attributes separately deriving some other attributes, non-key attributes. All these are non-key attributes. So this kind of things are not allowed. If all FDs are like this, then that is in second normal form. If some FDs are full and some FDs are partial, then overall relation is not in second normal form. So the whole discussion for better understanding, let us take one simple example here. So you can see here patient and a drug table. This table name is patient drug table. Here we have a patient number, drug number, and how many units of drugs you have to give for that particular patient, and what patient name we have here, and drug name we have here. So what is our observation here? You see, patient 1, if you observe, patient 1 is Krishna. So this is what redundant data we have actually. So that is what meaningfully try to understand what is meaning of partial functional dependency. You have a lot of redundancy actually. And drug also, if you see, drug D1 is Dolo, drug D2 is paracetamol, D3 is crocin, D4 is Niftil. And D3 again repeated. So that is what crocin. How many times D3 you have, that many times crocin you repeated here. So that is what redundant data is there. Ultimately, that you have to reduce actually. So that is what here primary key is what actually. So let us take the FDs also, set of FDs. So these are the set of FDs we have. So that means what is the key actually here? So key, how you will find, we already discussed it. Closer, try to find out actually. So let us take the P number and drug number, which we don't have RHS side. So P number, drug number, it's a closer if you find what we are going to get. So we are going to get, of course, P number, drug number, And P number, drug number deriving number of units. So I'm just taking NU, number of units, and P number deriving P name, and drug number deriving drug name. So that means what actually? All attributes derived by using these two. That means key is these two. So that means primary key of the table is these two. And you see in the FDs actually, this is deriving. So that is what our example here you can see. So for example, this is the P number and this is the drug number. Yes or no? So drug P number deriving P name and drug number deriving drug name, and together deriving number of units. Is it or not? So you see here A separately deriving. Because of this derivation, you have separately lot of redundancy is there in the table. Krishna, you repeated how many times? How many times patient 1 is there in the table? Or even the drug also, how many times you repeated, how many times that particular drug number is there. So this kind of things are not allowed. So what is the solution? That is important. So now the solution is, this is of course full functional dependency, and but this is P number is part of key, so this is partial functional dependency. And drug number is also part of primary key, so that means this is prime attribute, so this is also partial functional dependency. Take every partial functional dependency one by one. LHS side, whatever you have, that is what P number. First of all, if you take this one, find its closure. So P number, and what we are getting, P number, P name. So closure of LHS of this partial functional dependency P number is giving this one. So make this one as a separate table. That is what. And another partial functional dependency is this one. So what you have LHS side, drug number. So take the drug number, find its closure. So drug number deriving what are all attributes? Drug number deriving drug name. So that's it. It is not deriving anything else. So that is what. Now make this one as one relation. Make this one as another relation actually. So that is what you can observe that. So this is one relation. This is another relation. And original table patient drug. So patient drug, what we are going to have. So patient drug table, we are going to have, of course, primary key will be there, P number, drug number. I'm just writing shortcut. Now, here and here not covered attributes are what? In this and in this, not covered attributes is number of units that we are going to have here, number of units. So totally it became 3 relations actually. So that is what you can observe here clearly. Patient. So the first one is patient number and patient name. That is what here. So patient number is the primary key here. So you can see 2 patients are there overally. So only 2 rows we have actually. And their names Krishna and Rama. And another table is what actually drug table. So drugs, how many total we have? 4 drugs we have. So the 4 drugs. So that drug number is the primary key here. And their names we have here. And now the original table is this one, patient drug table. So you can see that. So patient number and drug number is same. If you observe, number of units is not covered any one of the relation actually. So in the original relation, what attributes you are going to place actually? The attributes which are not covered in any of the closure. Those attributes are going to there in the original table. So now you can see actually patient number 1, Krishna, is not repeated. That is redundant data. This much redundant data we are able to avoid. And the same way, drug also we are able to avoid actually. So part of the primary key, that means prime attribute, if it is deriving some other non-key attributes, it's better to decompose the, it's better to divide the table so that you can reduce the duplicate values, actually lot of redundancy you can reduce, so that update anomaly you can avoid actually. Suppose if you want to change the name of the patient 1 to some other name, then wherever it is there, in all places you have to update actually. But now just to update here, instead of Krishna, some Ravi if you want to place, then that's it. This is the only one place you have to update. So update anomalies are avoided actually here. So that is what actually, especially in the second normal form, prime attribute. Okay. So if in the primary key, what are all attributes are there, calling as a prime attribute. If prime attribute deriving any non-key attributes, then find the closure of that prime attribute and make it separate table. That's what simple solution to make in the second normal form. Now all these three tables are in the second normal form. So that is what this single table became now three tables actually. Okay. Hi. So now let us practice some examples actually on this second normal form. Okay. So for that, we are going to take the first example here. So you can see the relation A, B, C, D, E, 5 attributes we have. And here we have a set of FDs actually, functional dependencies. So always actually, first of all, to say it is in a second normal form, what you have to do, first step is find the key actually. What is the key for that table? We have to find out. First thing is. So that means finding the candidate key, we already practiced. So you just do the same thing here also. So what is the first thing is, in the RHS part of any functional dependency, whichever attributes are not there, collect those actually. A is not there, B is not there, C, D, E, remaining three are there. So we are going to take A, B. So find their closure actually. So A, B closure. So A will be there, B will be there. Okay, then A, B together deriving C, that is what there already. So take C. And A deriving D and B deriving E. So that we are able to derive all attributes by using these two attributes actually. So the key is going to become AB. Is it? So that's it. Now what we have to do is individually A, that means a subset of this key, deriving any other attribute, non-key attributes or not, you have to observe actually. So you can see, so this is full functional dependency. Because you observe that C is non-key attribute to C, fully dependent on primary key. But if you observe D, non-key attribute to D is dependent on prime attribute actually, A, not the complete primary key. So A is one prime attribute. So this is partial functional dependency. And even here also, non-key attribute E, they are dependent on B actually. So that is why this is also partial functional dependency. So take every partial functional dependency one by one, and then find a LHS closure actually. So that is what here, let us take the first one, A derives D part. So find the A closure here. So if you find A closure A deriving here D. So anything else it is deriving? Nothing actually. So this is one thing. And then take the another partial functional dependency. So find the B closure here. So B and B deriving E. So what is going to happen? Relation R1 is going to become AD. And here primary key is A. Underline that also. And relation R2, primary BE going to become another relation, that means another table, and here primary key is B, and original table R. Original table R, that means AB definitely going to be there, and attributes which are not covered in both actually. So you can see C attribute C is not covered any of these two. So that we are going to place here. So simple, in the original table, which attributes you have to place? First of all, primary key, original primary key. And along with that, attributes which are not covered in any of the relation after decompose, those attributes you just place in the original relation actually. So these are the three tables after dividing this original table actually. So now all these are in a second normal form. Not only that, see, this is the first normal FD, second FD, third FD. So first one you are covering here, second one you are covering here, and third FD you are covering here, definitely. So B derives E. So this third FD is there in the R2 actually. So this concept is also important. Later we will see somewhere lossless decomposition and functional dependency related things we will see actually. Okay. Now let us take one more example. So in this example, if you see here also, first of all, we have to find out the primary key. So what is the key actually? So A is there, B not there, C not there. So BC closure first let us try to find. So BC closure if you find, BC deriving A and B deriving D deriving E actually. Okay, so here key is going to become BC. And here if you observe, so key is BC. Now B deriving non-key attribute. So that means prime attribute, part of the key deriving non-key attribute. So that is what B closure. So this is what actually full functional dependency, but this is partial functional dependency. And this is a full functional dependency because this is not a part of key. D is not part of key. So automatically that is full functional dependency. So only one partial functional dependency is there. So for that, find the B closure. So B and B derives D. Next, D derives E actually. So this is what one relation. So R1 is going to become B, D, E, and here primary key is B, and original relation is what? So primary key is BC, and of course here we didn't mention this is primary key. So BC, so A is not covered here. So let us take A also, and of course this is primary key. Okay, so this is what in this way we are going to divide actually. Now you can see functional dependency 1, 2, 3. So here 2 and 3 are covering here actually. Is it or not? B derives D, B derives D, D derives E. And only one function, first functional dependency covering in this relation. So in this way, now both of them is in second normal form. So it is very easy actually. Always find the primary key and part of the primary key is deriving any non-key attribute or not, you just observe, that's it. So after doing these two, you just practice on this one actually. So here if you observe, total 5 attributes are there. What is the key first of all? So here if you observe, what is the key here? A is not there, RHSI, B is there, C is not there, E is not there. So ACE closure if you find, what is going to happen? A, C, E, and then A derives B, C derives D. So that means this is the primary key. So that means key is actually A, C, E together. Now, is A deriving anything? Yes, here you see A is a part of key. So this is partial functional dependency. And C is also part of key. So this is also partial functional dependency. So for first of all, A to C, A to B, find the A closure. So A closure is A, B. So that's it. Then next take the another partial functional dependency, C derives D. So find the C closure. So C and D. So this is what. Now relation R1 is going to become, make this one AB. After dividing, A is the primary key, relation R2 is going to become CD, and this is the primary key. Now the original table is what actually ACE is the key. ACE. Okay. So B is covered here, D is covered here, and all other attributes are covered. So that's it. Only primary key we have in the original table now. Okay. So this is what actually example 3. So in this way, so now all these three relations are in second normal form. Okay. Now let us take one more. So this part you see there is it is somewhat different than other actually. So find out first of all key. So to find out key, first of all here, which attribute is not there in the RHS part? A is not there. So find the A closer. Okay. So A closer, A derives B, B derives C. So this is what so key is what actually? So key is A. So what we have to do, see here A derives B, right? What you can say about this FD? Is it full functional dependency or partial functional dependency? Observe, your key is A, that means only single attribute is there in your key. That means this is fully functionally dependent on primary key actually. So that is why it is going to become full functional dependency, because LHS side whatever is there, that is your key actually. So what you can conclude from this example is, if any relation have a primary key with a single attribute, that is automatically in the second normal form. This relation automatically in the second normal form because of the key have only one attribute. So that is what very importantly note down as a note, a relation with a single attribute in the candidate key. So candidate key is nothing but primary key, right? So if primary key have only one single attribute, that is always in the second normal form. You no need to do actually. So always immediately after finding the key, observe that whether it have one attribute in the key or more than one attribute. If it have one attribute, then finalize it is already in the second normal form. If it is not if it is have more than one attribute in the key, then you have to do the process whatever we did. Okay. Hi. So now let us see the next normal form, that is third normal form. Okay. So it is very simple if you understand the second normal form. Okay. So what does it mean? Let us see here. So here if you see, if any relation, if you want to tell that is in a third normal form, the very first thing you have to check is whether it is already in second normal form or not. So like if you want to tell any relation in second normal form, first of all, it must be in a first normal form. So that is what it is, a sequential thing actually. So if you want to tell this is in a third normal form, means it must be first of all in second normal form. So that is a simple thing. Then the next one is very importantly here, there should not be any transitive dependency actually for non-prime attributes. That is very, very important. So this you will get the clarity with the example actually. First of all, what is transitive dependency? So this is what? This is regular mathematical thing only. A derives B and B derives C. So that A derives C. Okay, so this is actually a transitive dependency. So what is happening when you have like this? This kind of thing is not allowed actually. Because of course in the second normal form, because of having partial functional dependency, lot of redundancy we are able to reduce actually. But still in the form of transitive dependency, you are going to have a redundancy actually. Redundant data still it is going to be there. Is it clear or not? So if any prime attribute deriving some other non-key attributes means there is definitely a duplicate value. So redundancy is there. So that is we are able to avoid in the second normal form. So try to understand, try to observe my statement that in the second normal form, if primary key have more than one attribute, then every prime attribute, if it is deriving or subset of prime attribute, primary key, deriving some other non-key attributes, then that is leading to the redundancy actually. So that is why we divided into separate table. But non-key attribute, B is a non-key attribute deriving another non-key attribute. So that means this is also leading to redundancy actually. So that is why that also we have to avoid actually. So ultimately there should not be any anomalies. So because if you are able to reduce the redundancy means where we are overcoming the all anomalies, insertion, update, deletion anomalies, we are going to avoid actually. So this same definition we can discuss in another way also. So that is a relation is in 3NF if at least one of the following condition holds, then that is a in 3NF actually. If you take every functional dependency x to y, either x, see any one of these two actually, either x is super key or y is prime attribute. So that means y prime attribute meaning is what? Y is part of candidate key actually. So if any one of these two is satisfying, then we can say that is also in the third normal form. So actually both the meanings are same. Let us observe these two statements with a simple example actually. So here we are going to take as usually one simple relation table, patient ward table actually. So you just observe patient number is here, patient name, in which ward that patient is there and what is that ward name. So here primary key is P number. So that is what you can derive from the FDs actually. So P number closer if you find, we are able to derive all other attributes actually. So that is why here key is going to become P number. Okay, fine, let it be. Now, here if you observe just a layman discussion without observing all these things, you can see how many times word number 1 is there, that many times its name is there actually. So is it not the duplicate values? So that means is it not the redundant data? So that is what actually. And observe that this is the key. P number is the key. So P number is deriving word number and word number is deriving some other attribute, non-key attribute. So non-key attribute deriving another non-key attribute. So if you see from the primary key, so primary key is also deriving word number, but this is duplicate values actually. Is it or not? So that is what actually transitive dependencies, if it is there means still redundancy is there in the table. So to avoid that redundancy, observe where is the non-key attribute deriving another non-key attribute. So you can come here, primary number deriving word number deriving word name. So this is what transitive dependency. So wherever you have the non-key attribute deriving non-key attribute, that FD you take, you consider. Again, LHS part, whatever you have, it's closer, you just find out. So that is what we are going to find out, word number closer. So if you find word number closer, of course, so that itself will come word number and what it is deriving word name. So make this one as one table. So that is what you can see, word as a one table, word number and word name and their corresponding data actually. And after this, what is the original table? So of course, this word number is the primary key. Then original relation is what actually? P number, P name, word number, that's it. Because now this redundant data we are able to eliminate actually, that you can observe here. So that is what the original table is, this one. So you can see now there is no redundant data actually. So each patient in which ward he is there, that number only is there. If at all you need this, what is the ward name of W1? So go to this relation. So that is why this is going to become parent table. And this is going to become child table because this word number is the primary key here. that you are using here actually, so going to become foreign key. So this is what a parent and child relationship we are going to have after doing this one. If your transitive dependency you are applying means there is going to become a parent-child relationship between two tables actually. So now from this, let us have a one simple note, that is third normal form is considered adequate for normal relational database design because most of the 3NF tables are free from very importantly these anomalies. We are able to eliminate these anomalies actually if any table is in the third normal form. So that is what insertion anomaly. If I want to create one more word, I can create in the here actually, though there is no patience. I can insert here W3, some XYZ name. I can insert here, right? Is it or not? So insertion anomaly not there. Update anomaly. I want to change the special word name special to some other thing. So I can change just PQR here only. So it is not affecting any other thing. And deletion anomaly. If you want to delete any word, so you just check that is there any patient here. If it is not there, you can straight away delete that one. So you don't have any anomalies, you don't have any dependency when it is in a third normal form. So that is why this is more than enough to have up to third normal form. Even in real time also, up to third normal form, if you are able to do the tables, that is more than enough actually. That is what this statement is saying. Because mainly you have to handle these three anomalies actually. So moreover, third normal form always ensures functional dependency preserving and lossless join actually. So of course, these concepts we see in functional dependency preserving and lossless join. So if it is in third normal form, it is always ensuring these two also. Okay. So simple that in the third normal form, if you summarize, there should not be any transitive dependency. Transitive dependency there means still redundancy is there in the table. So to avoid that transitive dependency, so non-key attribute deriving another non-key attribute. Identify such a FDs. For that, LHS closure you just find and then make it separate to its table, whatever it is deriving. And then remaining attributes put in the original table. And make that primary key of the divided table in the original table as a foreign key actually, like this. So this is what third normal form. So second normal form, if you don't have partial functional dependency, then that is in the second normal form. If you don't have if you don't have transitive dependency, then that is in the third normal form. Okay. Hi. So now let us see some examples on this third normal form. So the first one is here we have a 4 attributes in a relation A, B, C, D, and these are the FDs actually. So here, first of all, what is the key actually? So let us see, RHS side A is not there. So try to find out the A closure. So A deriving BC, okay, C deriving D. Now, so if you observe that, this is primary key, okay, or prime attribute. So this is deriving. So that is what super key. So this is not a transitive dependency. But here C is not a super key. And that meaning is it is not a it is a non-key attribute, and D is also non-key attribute. So that is what actually we have in the definition. Either X must be super key or Y must be prime attribute actually. So in these two, not satisfying anyone actually. So this is transitive dependency, right? A derives C, C derives D. So that is why for this, try to find out the C closure. So if you find the C closure, C derives D. So these two only, right? Now what is going to happen? So make the relation R1 as C comma T, and in that C is the primary key, and original relation R, A is there, B is there and C covered here C. So because that is the foreign key in R now. Okay. So that's it. So this is the primary key actually. So now this is going to become foreign key. Is it or not? So in this way, you can divide very simple manner. So this is simple example. Now let us take one more. So here also, total 5 attributes are there in a relation. So try to find out the key actually. So here A is not there, C is not there in the RHS part. So AC closure, let us try to find out. So AC closure, if you find, what we are going to get? AC, then A derives B, C derives D, and B derives C. So this is going to become key actually. So key here is AC. And if you observe that before going to check the third normal form, is it in the second normal form? That is what our rule, right? If you want to say it is in a third normal form, first of all, it must be second normal form. But here, if you observe, A is the prime attribute. So this is partial functional dependency. Is it or not? And even C is also prime attribute. This is also partial functional dependency. So first to make this one in second normal form. So for that, what we have to do? So whatever partial functional dependency, A to C, let us take first of all, A to B. Then find A closure. If you find A closure A, and then B only we are getting, and B derives E actually. So this is one, and another one, C derives D actually. So let us take that also. So that means C closure, that means partial dependency, this one. So C closure, if you find C and then D. Now R1, relation R1 is going to become, take this ABE. So that means this is the primary key. Take R2, then CD only. This is primary key. Now the original relation is what? Of course, AC will be there. Then B covered here and C is there. D covered here, E covered here. So that means these two only, and those two are the primary key actually. All attributes are the primary key attributes. So that's it. Now, because see, we already discussed it. This is in second normal form, and this is also in third normal form actually. Is it or not? Because all of them is part of primary key, and we don't have any non-key attributes. Now, two attributes only there. One is primary key, another one is non-primary key. So that means C. Let us take another color here. That is simple. So C derives D. This FD we are covering here actually. So that means primary key deriving non-key actually. So this is also in third normal form. Third normal form. Now let us come here actually. So A derives B. This FD we are covering here, and B derives E also there in R1 actually. B derives E. Now if you observe, primary key is A, so A derives B, non-key attribute to B derives E actually. So R1 further we are dividing actually. So B closure, if you find as usually for the third normal form, BE we are getting. So R1 we are dividing further as R1 dash. So that we are going to take as B comma E, and where B is the primary key, and remaining R1 is what actually? So A, and this primary key here going to become foreign key. So overall, what are the tables actually? So let us take here. So total tables are here R2 and R and R1 dash and R1 actually. So this single table divided into total 4 tables. That is what you have to observe. So in R2, we have CD, primary key is this one. And in R, AC, and this is the primary key. In R1 dash, BE, This is the primary key. And in R1, AB, and this is the primary key. So this is what, now all of them is in the second or third normal form actually, because you have only, first of all, only two attributes. Okay. Hi. So now let us see this example, and this we have to decompose till third normal form actually. Okay. So let us see here. So here we have a actually total 10 attributes are there in this, and we have many set of FDs are also there. So what we have to do, very first thing is, if anybody told decompose up to third normal form or up to any normal form, the very first thing is we have to find the key. So how you will find the key? So we told one simple thumb rule that RHS side, whichever attributes are not there, you collect them actually. So A is there? No. So attribute A is not there. And B is also not there. And C there, D there, E, F, G, H, I, J. So this is these two attributes definitely going to become part of key actually, primary key. Okay, so the very first thing is find the closure for these two first of all. So that is what AB closure, let us find first. So A and B. Now AB deriving C, note down, and A deriving DE, take it DE, and B deriving F, F deriving GH, and of course D deriving IJ. So if you observe these two attributes deriving all attributes in the relation, so that means key is what actually? So key is A, B. So that is what the first step is done. Then now check that whether it is in a second normal form or not. So you can see that A deriving any other attributes in this? Yes, here this is a full functional dependency, but this is partial functional dependency, because part of the primary key, that means prime attribute, deriving non-key attributes. And even this is also partial functional dependency, because part of the primary key, subset of key deriving non-key attributes. So these two are the partial functional dependencies. Of course, these are full because this is non-key, non-key. So these two you don't need to consider. Now come to these two actually. Consider first A derives DE. A derives DE. So what we have to do from this, find the LHS of closure. So A closure, let us find. So if you find A closure, first of all A. So A deriving DE. So note down DE, and D derives IJ. So is it deriving any other? No, actually. So this is what one relation we are going to make it. And next, another partial dependency, let us take B derives F. So B derives F. So B closure if you take, okay. So B and B derives F. F derives GH. So GH. So now if you observe the relations, so R1 is going to become, R1 is this one, A, D, E, I, J. And in this primary key is A. R2 is going to become another relation, that is B, F, G, H. So this is another relation. So here primary key is B. Now original relation R is what actually? Primary key, of course, AB. Find the attributes which are not covered in any of these two relations. A, B, C is not covered anywhere. D covered, E, F, G, H, I, J. So here, this is what the primary key. Now you see, because the prime attribute is only one attribute, so this is in second normal form. And here also primary key is one attribute. This is also in the second normal form. And here, two attributes are there, of course, but A is not deriving C or B is not deriving C, but together deriving C actually. This is also in the second normal form. So that is what, first of all, we ensured these three tables now in the second normal form. Now we have to go for the third normal form for every table actually again. So now let us check R1. So if you consider only R1 first of all, so R1 if you take, so R1 is covering what are all functional dependencies 1, 2, 3, 4, 5. R1 is covering second FD and fifth FD actually. Okay, so that means you see here A is the primary key. So if you take A, D, E, I, J, primary key is A. So A deriving DE of course, and D deriving IJ actually. A deriving D, non-key attribute D deriving non-key attributes IJ. That is what trans to dependency we have, right? So that means what actually, with the fifth FD, we have a trans to dependency. So find the D closure from the fifth actually. So we are going to have D, I, J. So this is another relation we are going to make it. So R1 further divided, like R1 is going to become what actually? Dij, and where D is the primary key. And remaining is what actually? R1. So remaining is what actually? A primary key, and D is the foreign key here, and which attribute is not covered? E actually. So that is what. So this is related to R1. Okay. Now let us take the R2 also. So let us consider R2 now. So R2 covering which for FDs actually? R2 covering 3 and 4. So 3 and 4. And here also if you observe, B derives F. So here primary key is B. So B derives F and F derives non-key attributes this one. That means trans to dependency is there, right? So that is why consider fourth FD and LHS part is F. So F closure we have to find. So F closure is what actually? F, and then G, H, it is deriving. So now R2 is becoming what actually? R2 further splitted into R21. So R21 is what? F, G, H. So F is the primary key, and original table R2 is what actually? B is the primary key, and F is the now foreign key, and GH covered here. So that's it. So this is what R2. What about this one? So AB deriving C and C is not deriving anything else. So R is already in the third normal form. So this is already in the third normal form also. So overall the final tables are what actually? So you can see here R1 dash. So that is D, I, J. Primary key is D and R1. So that is A, D, E. And here primary key is A. And next R2 dash, R21. So that is F, G, H. And primary key is F and R2. That is B, F, primary key is F. And original table R. So that is what? A, B, C. Here primary key is AB. Now all of them are in the third normal form. So all these are in a third normal form. So that is what we need, right? We have to split this up to third normal form. So in this way, if anybody told that try to split the table up to third normal form, then first find the key. After finding the key, every FD you check that whether it is a full or partial functional dependency. If any partial functional dependencies are there, for that particular partial functional dependency, LHS part closer, find out that, make it separate table. For every partial dependency, you do that one and then make them separate tables. And then in the original table, primary key you take, and the attributes which are not covered in other tables, you add in the original table. So this is what second normal form. So then go for the third normal form, identify which FDs are covering that particular relation, and check that is there any transitive dependency. So as usually transitive dependency, if it is there, then that transitive dependency is LHS part, you find the closure and make it separate table actually. That is what, whenever we are discussing functional dependencies, especially we are finding the closure, we told that this is very, very important. Finding the closure is very, very important. Okay. Hi. So now let us see one more example under third normal form. And this is, though it looks simple, something we are going to see in this actually. So he is asking that this is in which normal form, whether it is in second normal form or third normal form. Up to there, it is there. So you see, first of all, always blind thing is what you have to find the key. So find out the key actually here. So you see, on the RHS part of any FD, we don't have attribute B actually. So B must be part of primary key for candidate key. So if I find B closer, you are not going to derive anything. So let us add other attributes actually. So let us find AB closer. Are we getting all attributes? A, B, and AB deriving C, right? So AB is the one candidate key. Then let us have another attribute C also. That combination also let us cross check. CB closer. So CB closer is giving CB first of all, and C derives A, right? So this is also fine. So first of all, candidate keys are what actually? AB is one, CB is another one. If you observe, all of them are prime attributes. In a relation, we have A, B, C. Here A and B are part of candidate key. So A and B are the prime attributes. And here C and B, that means C is also prime attribute. So now if you take in the second normal form is what actually? Part of key, if deriving non-key attribute, is it or not? So part of key is what? So here A, B deriving C, this is fine. Now if you take C derives A. So if you take C derives A, C is what actually? Part of a key, right? Yes, correct. Deriving what actually? Attribute. But whether it is prime attribute, key attribute, or non-key attribute, it is a key attribute. But that means it is not a non-key attribute. That means this is valid, right? So this is going to become full. This is going to become full functional dependency. Got the point or not? So second normal form is saying that part of the key, if it is deriving non-key attribute, but here A is not a non-key attribute. A is a key attribute because it is part of one of the candidate key. So it is there, it is already there in the second normal form. So concluded. Now come to the third normal form. Third normal form is saying what actually? Transitive dependency, non-key attribute derives non-key attribute. Again, take C to A only. C is a key attribute. Is it or not? A is also a key attribute. So there is no concept of non-key attribute deriving another non-key attribute. So because all of them are the prime attributes, the relation R is in second normal form and third normal form. So simply we are going to say it is already in the third normal form. That means it is already in the first and second normal form. Okay, so the relation it is in a third normal form. That is what the answer simply. Okay. Hi. So now let us see the next normal form, that is boy code normal form. Okay. This is actually little stricter than the third normal form actually. Okay. So what is this normal form? Let us try to understand. It is very simple if you understand third normal form. So a relation is in a BCNF when you can say is, if you have a non-trivial functional dependency x to y, where determinant, that means x, must be the super key actually. So that is always we have to ensure. And of course, it must be first of all in a 3NF. Okay. So here the only constraint is x must be super key. But when you come to the third normal form, either x is super key or y is prime attribute actually. But here it must be super key actually. Determinant, x is the determinant, right? So that must be the super key actually. Why we have this one is, though in the 3NF, a lot of redundancy we are able to reduce, but still there is a possibility of having redundancy because of having overlapping candidate keys actually. So that is leading to sometimes some more redundancy still exist in the table actually. So to avoid that one, this constraint making more stricter, that is x must be always super key. That is the simple thing actually. Okay. So now let us try to understand with a simple example. So here you can see a relation R with three attributes. So that is there are three FDs are also there. So what are the candidate keys first of all here? So the candidate keys, if you see, a closer, if you try to find out, a closer if you find, we are getting a deriving b, b deriving c. So candidate key a is one possible candidate key, and b closer also. So you can see a is there here actually, RHS side. That means a can derived by c. So that means even c is also going to become candidate key. In that way you can take directly. Okay, or you can say at least this is super key actually. So in the same way, B closer also, B deriving C, C deriving A. So that is what actually all of them are the candidate keys. And here, all of them are the prime attributes. So this is in a BCNF actually. Or A is a super key, B is a super key, C is also super key, because every candidate key is by default super key, right? Okay. So that is the simple thing. So first of all, this is in a BCNF. This example is in BCNF. Okay. Now let us take one more simple example. So if you take this one here, as usually we are saying that X must be, so that means in all FDs, determinants must be super keys. So what does it mean? So for example, here candidate keys are what? So here candidate key, for example, A closer if you find, A closer if you find, we are getting A and B, C, D, E. So we are getting all attributes, right? So this is candidate key. A is a candidate key. Now, so now from this, is BC is a super key or not? So simple, we can decide very simply. See here, it is deriving A, right? BC deriving A. Is it or not? So in place of A, you can replace BC. Is it or not? Or you can find the BC closer. You will get all actually B, C, BC, then BC deriving E. Okay. And of course A, right? So A deriving E. So even this is also candidate key. But without C, can we get all these things? Or without B, can we get all these things? No, actually. B closer not deriving all attributes, C deriving all not all attributes. So BC is also one possible candidate. So that means this is super key, this is super key. So these two are fine. Now come to this FD, find the D closer. So D closer, if you find, we are getting D, E only. Anything else are we getting? No, actually. So that means this is not a super key. Because this is not a super key, this is not in BCNF actually. It is not in a BCNF. So solution is what actually. So whichever FD is not satisfying, that closer you just find out. D closer, if you find, we are getting DE, right? So that is already calculated. So one table R1 is going to become DE, where D is the primary key. Then existing R is what actually? A, B, C, D is going to become the table, and here A is the primary key. So you can take anyone as a primary key, that is up to you, basing on the relation actually. And D is going to become the foreign key actually. So now this relation divided into two parts. One is R1, that is DE, another one is R, A, B, C, D actually. Okay. Let us take one more simple example. So here, whether this is in a BCNF or not, first of all, let us try to identify. So that is why every determinant you take, that means every LHS spot, find its closure. So AB closure is giving what? A, B, C, D, G. So I'm writing directly because it is deriving C, D, E. So this is fine, right? So AB deriving all, so it is a super key. Now, D closure. So D closure is giving what? D and A only. So anything else it is able to derive? No. So that means this is not a super key. D is not a super key. So what we have to do? So R1 is going to become whatever D is deriving. So that is what DA. And of course here D is actually what? Primary key in this relation. And as usual, normal relation is we are going to have B, C, D, E, and of course here A will be there. Okay. So AB is the primary key, right?
Hi. So now let us see in the SQL select command actually. So this is the very, very important command where we are going to work most of the times. Okay. So it is like a retrieving a data from the database actually. Okay. Our actual skills basing on this particular clause only, select command. Okay. So because if you see on the database, what are all operations we can perform? You can select the data, you can insert the data, you can update the data, or you can delete the data. So these are the major operations you will perform on the database at any point of time. But out of all these operations, most of the times, 99% of the times, we will perform this select command, so retrieving the data from the database. So that is why our actual skills basing on this select command only. So let us try to understand this select command overally first of all, and then we will deep dive further actually. Okay. So first of all, so for what purpose we are using this one? So that the select statement, the select statement is used to select the data from the database actually, very simple. So whichever data you want to show as a output or whichever data you want to retrieve, accordingly we have to write down our select statement actually. So it will retrieve the required data from the database. Okay, fine. So very important thing we must know is select clause structure. How select structure is going to be there. This must be very clear and very strict to follow whatever we are going to show here now. So that is the first one is select. So it is actually we are retrieving the data. What columns, what attributes you want to retrieve. So that you are going to mention after this select. So this is a keyword actually. Select is a keyword you must write down. And after that, in a table, what are all attributes are there or what are all attributes you want to retrieve. those attributes you are going to mention immediately after the select word actually. And then these attributes you are retrieving from where? So definitely one of the table or more than one of the table. So that is what the tables you must mention. So these are the two things you must have whenever you are writing a select statement. Whatever other commands are also there in the select command, but those are optional actually. But the mandatory things, if you want to retrieve the data from the database, is select. That means which attributes you want to select and from which table, because database is nothing but a collection of tables actually. You are going to have many tables actually. So from which table you want to retrieve the data, or from which set of tables actually. So that is what from clause must be there. And after that you have where. So sometimes actually here set of columns, so that is nothing but this is nothing but columns only, as we seen already earlier. And here you can filter the columns actually. Either you can display all the columns in a table or some of the columns you can display. So that means what you are filtering the columns. Now when it comes to the where, here we will write the condition so that whoever satisfying that particular condition, which row is satisfying that condition, only those rows corresponding attribute values you are going to display. So that is nothing but filtering a rows. Here filtering a columns, here filtering a rows. So this is the whenever you have any condition. And then you are going to have group by clause. So this is especially we are using for the groups actually. So similar kind of data whenever is there under any column. So you are going to all similar data part, you are going to group them on that group you want to work actually. So that we will see very clearly in the separate lecture. Okay. And then having clause. So here where is used to filter the rows and having is used to filter the groups actually. So here we are setting the groups, right? So those groups here you can filter. Sometimes some groups are not required. So such a groups, if you want to skip from the output, then you can have having clause. And after that, you want to display the data. This is for displaying the data in the output actually. So in which order you want to display, that is what two orders you have, that is either ascending order or descending order. Of course, we will see every clause separately. In the separate lecture, every clause we are going to see very clearly. Okay. So this is what the structure of the select actually. And in this, all these 6 clauses, this is the mandatory part. So these two, select and from, see from which table you want to retrieve the data and what attributes you want to display. So that is why these are the minimum 2 things you must maintain. And after that, basing on the requirement, you can use any of these things actually. And all of them also at once you can use actually. And now, so this is what the first of all structure of a select statement. And after that, if you see, because here we have total 6 clauses, and of course many other also is possible, but these are the basic clauses actually. Now what we are going to see is which clause you are going to execute first, which clause you are going to execute last. So that evaluation process, in which order it is going to happening, let us observe that also. That is also very important. So now you see that is what order of evaluation. So here that is very simple. First of all, which clause you are going to execute. So that is what from clause actually. Because overall you are working on the tables only. First of all, that table data you must select. On that data only, either select clause, where clause, group clause, having clause, order clause, anything is going to work. So the first source is actually the from. So from the clause, in the from clause, we are going to have a tables or a table. That table data, first of all, you have to retrieve. That is why from clause is going to execute first. After that, you are going to filter the rows based on the condition we have written. Okay, so maybe some rows are skipped because whenever condition is not meeting actually. So on that data, you are going to group them if you have a group class, group by class. Okay, and then if your group by clause is there and may or may not have having clause, so if you have a having clause, then having clause is going to evaluate. So this is what is going to order of execution. And after that, sometimes in the attributes here, we are going to have a expressions also. So after what data you want to select, what data you want to display, that data is filtered, that data, final data is ready. On that, you can have, sometimes you may have expressions in the select clause. So you execute those expressions. And after that, we are going to have distinct, because final data you selected already. That data, distinct as name implies unique data. No duplicates are allowed. Of course, we will see this also separately, let it be. So distinct is going to apply on this set of attributes. And after that, if you have set operators, so set operators are like a union, intersection, difference. So we have different set operators are there. If you have set operators, after final data, after the entire data, what you want to display, that means rows are filtered, columns are filtered, everything is filtered. The final data, whichever is there, on that you are going to apply the set operators if you have. And then the after final data is ready, even after if you have set operators, even that also completed, then you are going to display the data in a specific order. That may be ascending or descending basing on the mentioned thing actually. So this is what the order of evolution whenever you have a select statement. This is very, very important because whenever we are writing any query, okay, first of all, this order we must maintain, and for better understanding or for better efficiency or for better optimization part, we must know in which order all these things are going to execute. Okay, so this is what something about the select clause, and let us deep dive upon this select only in the coming lectures. Hi. Now let us try to understand more about this select statement actually. So as we are saying that we are always retrieving the data from the table. So in our course, especially throughout this SQL part in this chapter, we are going to use the one table. So this is what the table we are going to use. So this table is more than enough that for any scenario discussion. Okay, so that is what, let us just try to understand. Let us make this table well familiar so that whenever we are discussing, things are going to become very easy. Okay, so here you see table name is EMP. It's nothing but employee table actually. And in this table total we have 8 columns. That is nothing but 8 attributes are there. And in this EMP number is actually a unique, you can say this is a primary key. Okay, as we discussed earlier. So this is a primary key. Every value here is, it is unique and you don't have null values. That is what primary key, right? And then employee name you have and what kind of job he is. So that is what clerk, salesman, manager, analyst, president. These are the different categories actually, job categories. And MGR is nothing but manager. So for the Smith, for example, for the Smith, who is the manager? 7902. So who is the 7902? So here 7902 is the Ford. Ford is the manager for Smith actually. So that is what, for every person, one manager will be there except president. So president is the top level person, right? So he don't have any manager actually. So that is why whenever any column, any cell is empty, that is nothing but you have a null value, because this is also matter very, very important actually, that also we will see. Okay, so empty cell meaning is null. Okay, so that we will handle separately, that discussion also there. Okay,
So this is what MGR is nothing but manager. So hire date when he joined, and the salary. What is this salary? This is in terms of dollars assume, and this is the commission. For each employee you have commission, and here more empty cells are there. That is nothing but null actually. Okay. This is DEPT number. So DEPT number means a department. So under which department these employees are working. So actually we have another table department that also we will show you whenever required. So time being, just a department number here we are displaying. So that is another table actually, as we've seen in the normalization, when we split for the different for handling different anomalies. Department is one separate table and EMP is another table. So department is actually a parent table and here employee is a child table, because this department number is the primary key in the department table. Okay, so that is the reason here. This is a primary key, we can say. Sorry, this is a foreign key, actually, we can say. So its originality is there in some other table. Okay, so this is what the table, first of all, we are going to use throughout our SQL part. Okay, now let us see how to retrieve the data from the tables in a simple manner. So but this is because we are writing the first query now. So let us see in a simple manner. So if you see the syntax of a select statement, so select is a keyword you must write down. So it need not be always capital letters. Anything is fine, small letter or capital letter, that is fine. And then which columns you want. So which column you need, those column names you just mention separated by a comma actually. After mentioning the all columns, then you write down the from, that is also mandatory keyword. And these columns, especially these columns, from which table that we are mentioning. So they're very simple actually. So that is what, if you see, then this is what the first thing. Now here we told every column you have to mention separately. But sometimes I need all the columns actually, because sometimes some table may have more than 10 columns or 20 columns. Sometimes maybe 15, more than 50 columns will be there. So writing every column separately is not recommended thing. And you need all the columns at a time. At that time, simply use the star in this position, in the select clause. That is what. So if you use select star from EMP, then entire data is going to come as a output. What is that? This one that you can see. So this is the output you got for this command actually. Okay, so whenever you need, you don't want any filters in the columns, then you use the star. If you need only specific columns, then this is the syntax as we mentioned. So you can see I need only EMP number, ename and department number. And from which table? These column names must present in the table actually, whatever you are mentioning. Okay, so that is what actually here you can see. So output is EMP number, ename, DUPT number. So in this way, whatever columns you need that you mention in the select clause, only those columns are going to come actually. And one more thing is, EMP number is the first column, after that ename and then department number. But you want to change the orders actually, order of display. So for example, I need first ename. So then simply you write down select. First I need ename. So give ename. And then I need a department number. And then I need EMP number. So you just give. So here, whatever order you are mentioning, that is nowhere related to the order you have in the original table. This is the original table. Okay, so in which order you want to display the columns, in that order you can mention actually in the select clause. And of course, after that from table name. So that is EMP. And terminate with colon. So this is what actually the first thing, in what way you want to display the data. Okay, so now here let us see one simple thing. So let us write down some queries actually here. I need commission and salary. So what we can write down? So we need only commission and salary of every employee. So every employee means let us display his number and salary and commission. So that is what you can see. Select. So whose salary? That is why EMP number. Let us display. So EMP number, and we need salary, and we need commission. So that's it, right? And from which table these columns are there? So that is what from always. So we are retrieving these columns from EMP table. So that's it. So very easily you can filter the columns actually. Unnecessary columns you can skip, and the necessary columns only you mention in the select clause. So let us just display every employee name and his job, what under which category he is working. So that is what, in that case, what we will write down. So select. So e-name, we need only e-name and his job. So that is what job. So these two columns from which table actually? So from EMP table. So like this, you can mention only one column you can mention. So that is what I need only, for example, I need only MGR. So see, so here in the output, how many rows it is going to display? You just count first of all, how many rows are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 rows are going to get actually output here. And here also output is 14 rows. Always remember that this is also important for us. 14 rows you are going to have in this table, and 8 columns we are going to have. That is what. Okay. So EMP number, e-name, job, MGR, hire date, sal, commission, department number. Total 8 columns, 14 rows we have. This is also required. Sometimes we need actually. So I want to just display, see now the magic, if you see, I want to just display commission part. So that means select only commission. Why I am writing this part, let us see, from EMP table. So what is going to happen is output, how many lines it is going to display actually. So though you have null here, everything it is going to display. So that means total 14 rows it is going to display. As it is, this entire column data is going to display actually. Okay, there is no filter actually. Null values also as a with the empty cell, it is going to display actually. Okay, so this is what a simple thing, how we are going to have a select statement. And it's a syntax. If you need all the columns, then you put a star in the select clause so that all columns are going to come in the output. Or if you need a specific columns, at least one column must be there. At least one attribute, and more than that, any number of attributes which those must exist in the corresponding table, which you are mentioning in the from clause actually. Okay, so this is the very basic thing we must understand, because select statement we are going to use in the 80% of the course in the SQL chapter. Okay. Right. So now let us see in the select clause, whenever required, we can use the keyword distinct actually. So this has specific reason as name implies actually. So if you see here, why we are using for the distinct. So this is used to return only distinct values as name implies. That means it will eliminate automatically duplicate values actually. So sometimes you need old data, though the duplicates are there under any specific column, but sometimes you don't need duplicate values actually. So whenever you have such a requirement, we can go for this one. That is why this is an optional keyword actually in the select clause. So if you see, it's a syntax distinct, and if you are going to take the set of columns here. Set of columns all together. If any duplicate rows are there, those rows it is going to remove actually, because those are the duplicates, right? So in that way it will eliminate actually. So that we will see. And of course, see, after entire result is ready, upon that result, if any duplicate rows are there, those rows automatically it is eliminated. So only one row it is selecting actually. So for example, if you see here, simple example, job is one column here. You can see job is one column. We want to display only one job. See, without having distinct keyword, it will return 14 rows actually. 14 rows it will return without this distinct. But with the distinct, you can see how many rows it will return. So that is what you can see. So the output is, you can see clerk, salesman, and here salesman is there, here salesman is there, here salesman is there. All these are the duplicates. So only one value it is returning. So clerk only one time, manager only one time, analyst only one time, president only one time. So this is what, whenever you have such a requirement, you can go for the distinct keyword. Is it clear? So normally it will return 14 rows. Now you have 5 unique values in this column. So all those 5 columns it is going to display actually. Okay. Sometimes you have more than one attribute here in the select class. At that time you can see here job and manager. So here you can see one different thing you must understand. People will confuse that this distinct keyword you are applying only on this column. No. So these 2 columns are there. Upon these 2 attributes, if any duplicate values are there, for example, you can see here clerk 7902, clerk 7902 combination as a single value. So if clerk 7902 anywhere there, then that it is not going to return. For example, you can see salesman 7698. Together one combination, same combination here you have, that it is not going to return. And manager 7839, and here manager 7839 repeated. These 2 things is not going to come. Only these circled combinations are going to return. That is what actually, whatever attributes you mentioned here, out of all those attributes, okay, rows, if you take only unique rows, it will return actually. So in that way, 7 analyst here is there, 7566, and here also analyst 7566. This is not going to come. Is it clear? Now salesman 7698. Here salesman 7698. So this is also not going to come. Of course, president and null unique. So that is going to come. And clerk, see here, clerk 7902, here clerk 7788. So both combinations are different. So this is going to come. And clerk 7698. So do you have 7698 till now with clerk? No, this is also going to come. And clerk here 77782, you don't have actually. So such a way here salesman 7698. So this also you can remove. So in such a way, whatever attributes you mentioned, in that combination, duplicates are going to eliminate as it is mentioned in the definition. So that is what you can see the output of this query. See here. So here clerk 4 times are there, but with the combination of MGR, it is unique action. So that is what here total we have we have 8 rows are there. So here also 8 rows we have in the output. So in this way, whenever you have a distinct values, you need distinct values on the attribute combination. So go for the distinct keyword actually. Okay. Hi. So till now we've seen that select class and from class. Okay. So now let us explore more on this actually. So we are going to extend with where clause actually. So you see, especially select clause, what you are mentioning in the select clause, We are mentioning the attributes actually. That means column names we are mentioning. So that means whichever columns we need, only those columns you are placing there actually. So that means you are filtering the columns actually. So that means your attributes filter is done. But sometimes you have to filter the rows also. I don't need specific rows. Okay, so those rows if you skip and required rows only you want to display. So for that we are going for the where clause actually. So that is what actually where clause is used to filter the records. That is nothing but for filtering the rows. So that is what it is used to extract only those records that will fulfill the specified condition. So in case of columns filtering, you just mention column names actually. But in case of rows filtering, we are going to eliminate by using the one a condition. Which record is satisfying this condition, those records are going to return, and which are not satisfying, those are not returning actually. That means you are displaying. So that is what, let us try to understand its syntax, simple manner. So now we are not concentrating on this part, select clause. This is not required for us. Now this is done already. So whichever columns you mention, or if you need all the columns, you can mention star and a table name. So here you are mentioning the condition. That is what. So here, whoever satisfies this condition, only those records you are selecting. So for example, for more better understanding, if you are doing especially this where clause first time, so you can see here simple example. So that is display employee details whose job is clerk. So you can come to the under the column job, come to the job. Here if you observe, we need only clerk information. Is it or not? He is asking only clerk's information. So this record must come, and here one more clerk, this record, this record, this record. Only 4 clerks are there. These 4 clerks details only we need. That is what Smith, Adams, James, and Miller. So what we can write down actually, you can see we have to select, and he mentioned employee details. That means we are going for the star because all columns is required, all columns are required. And from the table is EMP. Now condition is what actually? So job must be clerk. So that you can observe in the query, you can see. So we need all columns, so store from the table EMP. So especially the condition part you observe here. So in the condition part, what we are writing, job is equal to clerk. So under job column, whoever have a clerk, only those records it will return. So the output, if you see, this is what. So you can see Smith is the clerk, Adams is the clerk. Here Adams is the clerk, James is the clerk, and Miller. This is what we've seen already. Is it or not? So that in that way, you can write down the condition. This is what you try to concentrate. And this is very, very important because you are going for the most of the times filtering the rows, then the columns. Columns filtering is simple. Only mention the column name. But you have to filter the rows, our actual analytical skills, our logical thinking, basing on this where clause only. And another example, if you see, display employee details whose job is clerk. So here, actually, instead of this one, whose department is 10 actually. Okay, so whose department is 10. So only 10 department employees we need. So that is what you can see. Whoever is working under the 10th department. So now you are filtering on this column, whoever have 10. So simply DAPT number, that column name. So here in the condition, simply column name you will mention. And of course, here I am using equal. There are another operators are also there. And here value you are going to write down simply. Condition is nothing but. So an operator is need not be always equal. So that part we will see separately, how many operators and what are those meanings. So in this case, we need only under the department 10 who are working. So in the condition part for the column department number equal to 10, if you write down, this is what the output we are getting. So in this way, by using the where clause, we can filter the rows actually. So this is just a basic thing of the where clause. We are going to see many things in this where clause actually. So that as we are moving step by step, we will see all those things. Okay. Hi. So now let us see here different operators we are going to use in the where class actually. Okay. So actually we've seen in the last lecture only one operator, that is equal operator. But sometimes we need other operators also based on the requirement. So that is what, of course, these are the well familiar operators only. So that is greater than, less than, greater than or equal to, less than or equal to. And this is the symbol for not equal. And not only this, of course, you can use this one also for the not equal symbol. Okay. And these are other operators you can use. These things separately we will see actually. And these have separate lectures we need actually. So let it be these three, last three. And these six operators, okay, very regular operators, their meanings also very simple. Okay. So for just practice purpose, let us write down few queries based on the given statement. So it's recommended that please try yourself first of all, write the query based on the given thing, and then you cross check what we are writing here. Okay. So now here list the employees whose salary is greater than 1500. So he is asking the condition on the salary column actually. So what you can write down. So here you see he is not asking any specific columns in the output actually. So that means he need all the columns in the output. So that is why select. Since we need all the columns, we are going for the star. And from where you need the data? From the employee table. So that is what from table name is EMP. So that is what table name is here EMP. And now the condition part, now actual part, where salary must be greater than 1500. So that is why here I am going for the where what actually column name is sal. So salary must be greater than 1500. So that's it. Very simply we can write down. Is it clear? So on which column he is asking the condition, you identify that column or attribute, and whatever that, basing on that operator you select, write down accordingly. That's it. So now let us try to write down another query. So list all employees except managers. So this is a little tricky. So how you will write down? We don't need managers, but other employees required actually. So how you can write down? So here you can see, first of all, here also, he is not asking any specific column. So that is why we are displaying all the columns. So that is select star. From the table is EMP, of course, as usual, EMP. Now come to the where clause, where. So now you see, he is asking the employees except managers. So managers, where under which column actually we have managers, this job category, right? So under this column, we have to put a condition. So which is the suitable operator for this one? So except manager means if it is not equal to manager, then those employees we need, right? So that is what, where job type not equal to manager. If it is not equal to manager, then we can take down. So that is what you can see here. For example, it will see how the execution is also going on is, it will come to the first row. Let us see on this. So that for every query also same way we will see actually. For the first row, it will come to the first row, and wherever condition is there, job. So going to the job value, clerk. Clerk not equal to manager. Yes, it is true, right? So this record is going to return. And then it will go to the next row. Same thing, salesman. Salesman not equal to manager. Condition true. So this is also going to return. So like that next column, salesman going to return. But now here, manager equal to manager. So actually here capital, here small, that is not a problem actually. That we will handle accordingly. Okay. So manager is not equal to manager. Actually, manager is equal to manager, right? So this record is not going to return. This is not going to come in the output. And same way, next also not going into the output. Next also not coming in the output. And this is coming because analyst, president coming, salesman coming. So there is no manager further. So all records are coming actually. So out of 14, these three are not coming. That means 11 records it is returning. So that means 11 rows you are going to have in the output. That is very important. Sometimes if it is a competitive exam or any interview, they will ask how many rows it is going to return. So that is also matter. Observe that only 3 managers are there in the job under job column. So only those records is going to return. Now let us try to write down another query. So that is list the employees who are working in the department 10. So I think this is a very simple one. So list the employees. So all employees is asking. So select star from EMP table name where, see here I am writing where in the same line. Here we written in the different line. Don't think that both of them different. So you can write in the single line or you can write down different separate line, each clause. Select clause in one line, from clause in one line, where clause in one line. That is not a matter actually. So where DAPT number is 10. So that's it. Okay. So, and then another query, if you see, display the details of the employee Turner. So only Turner is what actually under in this table. Turner is actually a employee name. So that employee details we need actually. So that's it. We will write down select. Only one employee details it is asking star from. You can write down small letters also. These keywords select from where all these things from EMP. So here we will write down where ename actually. Turner is here. Ename where ename is equal to Turner. So only Turner, this entire row is going to come as a output. So here only one row is going to return actually. So in this way, so here just main information is what are all other operators we have. So those operators you can use basing on the given statement or basing on the requirement. Okay. Right. So now let us see our next concept in where clause. So actually till now we've seen that in the where clause writing only with one condition. But sometimes we have to go for different conditions actually. And different possibilities will be there. Okay. So sometimes either or condition or sometimes both the condition. So whenever you have more than one condition and basing on the situation, you are going to have another operators, that is the and operator or operator not operator. So these things, especially and or, are using for connecting different conditions actually. And of course, and is different, or is also different. Okay, their meanings are different. So let us see. Okay. So that is what actually and or operators are used to filter the records based on more than one condition especially. So if one condition is there, simply we can write down basing on the previous discussion, last lecture we've seen. But when you have more than one condition, we need connectors that is and or. Okay. So let us see the and operator. So and operator when the condition overall condition is going to become true. So we have a condition 1 and a condition 2, and in between you have a operator and. When it is going to return true overall, that particular record is going to return when condition 1 is true and condition 2 is also true. So this part you might have seen in the digital logic or any mathematics, okay, somewhere you might see, but the same meaning is same. Both the conditions must be true, so that overall condition true, so it will return that particular record. That is what, when it will display a particular record, if all the conditions separated by and are true. Even not only these two conditions, you can have more than this also. All conditions must be true, then only that particular record is going to return or display. So same way, when you are going to display or record, if you use the or operator, at least one actually. So any one of the condition, if it is true, then overall it is true. Or if all conditions are false, then only it is not displaying. At least one condition, if it is true, then entire record, entire condition is true, so that that record is going to display. So that is what simple not operator is what. So simply it is negation, right? If condition is true, so we are going to have a condition. Before that, if I write not true is actually a false, not false is actually a true. So that means you see the not operator display a record. If the condition is not true, that means if it is false, if the condition is false, then not false is nothing but true. At that time, this record is going to return. That means actual condition must be false, so that overall it will become true. Then it will display the record. So let us write down simple queries so that we will get familiar actually. List the clerks whose salary is greater than 1500. So what is your understanding here? So here you see employee salary must be greater than 1500. Is there any other condition? He specifically mentioned that clerks actually. That means this is one condition and this is another condition. Got it? So that is what, first of all, select command, select. Then we need all columns. So that is why star, and from which table? From EMP. Okay, fine. This is simple. Then where condition part, which rows we need actually. So employee must be a clerk actually. That means job type must be clerk. So that is what, job is equal to clerk. Not only this, his salary must be greater than 1500. So what is the operator you have to use among these three? And actually, whoever clerk, whoever salary 1500, both actually. That is why we are going for the operator. And then salary column is this one. So sal must be greater than 1500, even not equal to 1500. So that's it. So now if whoever satisfies this condition, both, that you can observe actually. Here job is clerk, fine. Salary is less than 1500. So this record not returning. And so clerk, here you have another clerk. His salary is 1100 only. So he is also not going to return. Clerk 950 only, clerk 1300 only. So it is not returning actually no records. It will return 0 records. For example, here if you give 1000, what will happen? This record and this record, 2 records it is going to return. So nothing wrong with 1500. Only thing is no output actually. This statement is correct. This query is correct. Only thing is both the conditions, no record is satisfying. But if you write down 1000, then 2 records are satisfying. Clerk and greater than 1000. Clerk greater than 1000. So Adams and Miller satisfying this condition. If it is 1000 actually, especially. Okay. Now let us see another query. So here list all employees who are either manager or working in the department number 10. So how we can write down this? So here if you observe that we need employee details, either he is a manager or working in the department number 10. That means you see, or operator, any one actually, need not be both, at least any one of them. So that is what simple. This is simple, right? So select star from, select the star from EMP. So where, what we can write down? So manager. So job type, either manager. So job is equal to manager. Or this is important. You see anyone actually, or department number is 10. So DEPT number is 10 equal to 10. So whoever satisfy any one of this actually. So you can see simply the first record. So the first record, it is not 10 and not manager actually. Next, not manager and not 10. So let us see, these three are satisfying. So let us note down here, these three are satisfying because manager, and there is no manager further, but this is 10, this is 10. So total here 3, here 2, total 5 records it is written. Is it or not? Because anyone actually, manager or department number 10. But here if you observe, one record satisfying both. But that is not a matter. If at least one of them is true, then other not required. And one more thing, if you see, especially this we will use in case of optimization part, you return job equal to manager, department number equal to 10. So if this condition is true, first part if it is true, job is equal to manager, then it is not going to evaluate remaining because the operator is or. If one of the condition is true, then overall it is true. So it is no meaning that if you evaluate further also. So that is why remaining condition part it is skipping. If first condition is false, then it is going for the other condition. Even here also in case of AND operator, if first condition is false, then overall it is going to treat as a false, because as mentioned that in case of AND operator, all conditions must be true. But if your first condition is false, then there is no meaning of executing remaining actually, because overall it is going to become false. So that is what in case of optimization, these things are going to be useful. And that is why actually job equal to clerk, salary greater than 1500, which you have to write down as a condition 1, which you have to write down as a condition 2, basing on the data you have actually. So those things we will see in a separate lecture actually. So this is just for the information how to use these operators. Okay. And then let us see one more example for not also. So here you can see the list employees who are not managers. So how you can write down for this? So you see by using not operator, let us try to find. So you can see here, select star from, select a star from EMP, where so you see, if I write job equal to manager, job equal to manager, only managers will come, but job should not be manager actually. Then operator not we are using in front of this condition. What is going to happen? For whoever the manager, for them condition is going to become true. So not true is false overall. Whoever not manages, this part, condition part is going to become false. Condition is going to become false. Not false is actually true. So it is true is becoming for whom actually? Whoever not manager. So that is what required, right? So whoever not manager, all those employees details it is going to display. Is it clear? So in this way, in simple manner, we can write down actually.
Okay. So now let us see by combining all these operators, different queries actually. Okay. So in that, the first one is, so here you see, list the employee names who are either salesmen and salary less than 1400. Okay. Or working in the department number 20. So here observe that he may be either salesman and less than 1400 salary, or working in the department number 20 actually. So that means either this or this has to satisfy. So that is what, first of all, select. Here observe that he is asking only names, employee names only he is asking, not any other. So that means let us take only e name. From table is what actually? EMP. Fine. Then actual part is here where actually we have to combine both actually. That is what? He may be either salesman and 1400 salary actually, less than 1400. So that is what actually is. Salesman means job is salesman, job is equal to salesman, and here the connector is and, because salary must be less than 400 and sal less than 1400. Either this whole part, that means this you have to evaluate separately, or if not this, or what is another option, our department number may be 20. So that is what DEPT number, or DEPT number equal to 20. So what does it mean actually? So either this inside the braces, either this is true or this true. So such a employee is required actually. So you can see here, he is not salesman, but department number is 20. So this record is going to return. Next one is salesman and salary is not less than 1600. And also his department number is not 20. So it is both the conditions is false in this record. Then here salesman and salary is less than 1400. So that means this record is also going to come. So like that. So here 20. So simply whoever have department number 20, they will definitely will come. And salesman and less than 1400 actually. So this salesman is over. Here one salesman, but salary is 1500. Here another salesman and salary is less than 1400. This one. So how many records are coming? 3 here, 4, 7. Total 7 records it is written. Is it clear? Such a way you have to evaluate also. Sometimes if you want to display output actually. Okay. And then, so try to write down for the next query. Similarly, what is that actually? List the employee names here also, who are neither salesman nor salary less than 1400 nor working in department number 20. So he is saying any of these three actually. He should not be salesman, should not be less than salary less than should not less than 1400, and department number not 20 actually. So opposite to this whole thing, this part. So that is what, how and all you can take. So you can see here. First of all, select. So we need only names, employee names, e-name. Then from table name is EMP, where, so what we will write on the condition. So any of these three actually. Okay. So that means actually, first of all, let us go for the opposite. So anyone, all of these three. So all these three who are satisfying, for example, those persons only required assume, we told. Then if you negate this part, then that will become the statement, right? Given statement. So that is why first what we are doing is
job is salesman, job equal to salesman. Actually here operator is and we are using. All three actually we are seeing. So and sal less than 1400, sal less than 1400 and department number equal to 20. So whoever satisfying all these three, not those persons actually. So that is what you apply, not before that. So only such a records it is returning actually. So in this way you can combine all operators actually. Okay. Now let us take the next one. List the employee names who are managers and working in the department number 10 or 20. So managers and either 10 or 20. So here how you can take. So in simple manner, select. So select names only here also, ename. Then from table EMP, where, so here you see, here either managers. So job is equal to manager, job equal to manager. And here if you see, so let us take as capital letters, anything is fine. Then here department number either 10 or department number 2 times you can take. We have alternate also, that we will see. Okay, 20. Any one of these two actually. That means put this in a brace. So if any one of these two is true and this is true, such a records you are returning. So in this way, so little complex queries you can write down actually. Okay, that means we are combining and or not all together. Okay. Hi. So now let us see another clause in the select statement, that is order by class. Okay. So this is very simple, order by, as name implies. So sometimes it is required that data you want to see in a specific order. So only two orders, that is either in a ascending order or in descending order. So whenever this kind of requirement is there, so that facility is there actually in the SQL. So that is with this order by clause. So order by keyword we are using for sorting the result set. Actually, that is what, even in the whenever we are discussing the initial discussion, that is select statement, order by clause is going to work at the end actually. That is what, because result set, after rows are filtered, after columns are filtered, everything is finalized. Only final data is there which you want to display. Upon that, it is going to work actually. Upon that data, basing on your requirement, either in ascending order or in descending order, data is going to display. So by default, actually, it is a ascending order. If you don't mention in which order you want to display, that will consider as ascending order actually. And to sort the records in the descending order, suppose if you need in the descending order, use the keyword DESC, that's it. So now you want to display the data in ascending order or descending order. So what is the syntax actually? So that is very simple. As usually, from clause, select clause and from clause. When you come to the order by clause, after that you can write down what are all columns you want to display in a specific order. You mention them. At the end, ASC means ascending order, DESC means descending order, any one actually. If you don't mention, that is by default is this one. If you need in descending order, you have to mention DESC actually. Okay. So let us see one simple example so that it will become familiar. So list the employee names in the ascending order actually. So we want to display the data in a ascending order. So employee names especially. So as usually, first thing is what? Select the data. Select what we need, employee names, e-name. So we are going to take e-name from which table? EMP. This is normal previous discussion only. Now we are going to apply order by. So order by, then which column you want to display in ascending order? That is what in e-name. So I can close here like this, terminate this statement, or you can write down ASC. Anything is fine because by default it is in ascending order, right? So now what is the result? This column, e-name column is going to display in an ascending order, alphabetical order actually. So that you can see the result. So here you see Adams is the first one, then Allen, Blake, Clark. So all these are in a ascending order actually. You can observe that. Okay. So this is simple. Actually, you mentioned only one column actually. People will have a confusion whenever you have more than one column in the order by clause. And one more thing you have to observe, in the select clause, whatever columns are there, those columns only must exist in the order by clause. Anyone or more than one. Because the columns which are not there in the select clause, if you have here, that is not meaningful, right? So whatever data you are displaying, whatever attributes data you are displaying, only those attributes must exist in the order by class. Okay, so that is one thing you must understand. And after that, now, if you have more than one column in a order by clause, how data is going to display? So that is very important understanding. So let us go for that. So here, actually here we are going to display not the employee names. We are going to display job and MGR. So we need both of them in the ascending order. So for that, what we will write down first of all statement, select job MGR. This is fine, MGR from EMP. Very importantly, come to order by clause. Order by. Okay. Now, so I am writing here job, comma, MGR. So by default ascending order. So what is going to happen? Observe that. You return first job and then MGR. So first it will consider job. In the job ascending order, who will be the first? Analyst. So here one analyst. So let us take another color. So here analyst there, here analyst there, and here analyst there. And MGR 7566. So since both of them have the same value, will both actually two records first will come. After analyst, who is the next clerk actually? Clerk you see, here you will get the clarity. Here three clerks are there. So these three clerks, and then you see in case of MGR, four different values actually. So these four, after this is sorted, these four are in a sorted order. So if you see the output, then you will get the clarity. Of course, these two, fine. You come here, whenever these are same, next you are going sort for these actually. So the first priority for the sorting is this one. Whenever they are same, and then they are going for sorting next actually. Is it clear or not? So that you can see 7698 first, 7782 next, then 88, and then 7902 is the next. And of course, here manager and here MGR is same. Of course, this is fine president, and here is same. So you will get the clarity from the clerk part actually. So in which order you mentioned, the first column have the high priority. So basing on this, it will sort first. If anywhere equal is there, then wherever equal part is there, in the second attribute, those values it is going to sort again in the ascending order. So this is what actually going to happen whenever you have more than one column. So this is very, very important understanding. The same thing if you need in the descending order, you just apply DSC. then in the reverse order it is going to come. So that is what actually, if you understand ascending, listening is simple. So in this way, if you want to display any data in a specific order, you can use the clause order by. Okay. Hi. So now let us see one of the important concept in where clause actually, whenever we have to go for the condition, especially you are dealing with the patterns actually. Suppose string patterns, if you want to observe, how you have to do actually. So how to frame the conditions. So that part, let us try to understand very clearly. So that is what by using like and wildcard operators. Okay, so very easily let us try to understand in the basic concept. So that is, first of all, if you see, wildcard characters are used to substitute one or more characters in a string actually. We will come back to this point actually. We will understand automatically if you see the actual concept. Then wildcard characters are used with like operators because we are dealing with the strings actually, and especially patterns. We need specific kind of patterns. When you need specific kind of patterns, you have to, that means especially with the strings, we have to go for the like operator. That means simply, if you are dealing with the strings, that means condition you are framing with the strings means you are going for the like operator actually. And like operator is used in where clause. That is what we, in the where clause, for the condition part we are using the like operator, such for a specified pattern in a column. So whatever column you mentioned, on that column what kind of patterns you need, that we are specifying in the form of condition in the where clause actually. So all these things let us try to understand in simple manner. Okay, so what are the wildcards actually? First of all, so this is one wildcard. So that is the percentage. It is used for matching 0 or 1 or more characters. Its meaning is, if you simply place this one means maybe zero length string or 1 length string or more than 1 length string, any length string actually. Simply starting from 0, any length strings, for that we are going to use the percentage. And another one is underscore. So this underscore is matches for exactly one character. Okay, so if I write simply like this, that character may be anything but one length actually, exactly one length. By using this two, you can specify any pattern. Okay, that is what let us try to understand in simple manner with the simple examples actually. So that is what you can see here. We are going to take EMP table here. Especially let us try to observe on the ename actually. Okay, so let us see here. So now query one, if you see, for better understanding of, for better usage of these two, let us take query one. So the display names of employees whose name starts with the A actually. So this is what you need, a specific pattern. What kind of specific pattern? Employee names who are starting with the A actually. Is it or not? So that is what we need. And after A, you can have anything after that. Is it or not? So that is what. So for that, how you will write the query. So we need only name. So select the ename from which table EMP. So here where, on which column you are putting a condition, on ename like. So here we have to write what is the condition. So like you must start with the A, yes, correct. And after that you can have anything, and that may be 0 length or more than or equal to 0 length actually, greater than or equal to 0 length. So that means for that what we are using this one, right? Percentage, right? So after A, just to mention percentage, that's it. Now what does it mean actually? Starting with the A, and after that any length, any string you are going to allow. So that's it actually. So you can observe here, ename whoever starting with Alan. So Alan, if you take, okay, starting with the A and after that any length, that is what meaning, right? So percentage meaning. And any other Adams is there. Adams is also starting with the A, okay, and after that any length. So you are going to have two records. You are going to get the output, that is Allen and Adams. So that's it. So in this way, for specific pattern strings, how to search in the column is by using the wildcards and by using the like operator. So as we mentioned here, you can see this you're working with always, like operator is working with always strings. And for a specific pattern, you are going to use these wildcards actually, operators. Okay. Now for more better understanding, let us take few more queries. So if you take the second query, display names of employees whose name ends with R. So this you can try first of all, then we will, then you can see here. So here if you see, select the ename. This is as usually ename like. It must end with R. So last letter must be R. That means before you can have anything, right? So before you can have anything and any length. So that is what percentage again you are using. So that's it. So you can see whose name ends with R actually. Here Turner is there. Turner and Miller. So two employees are there whose name ending with R, that you can observe here. Ending with R, before that any length actually. Now let us take one more query. Display names of the employees whose name length is 4. Now you can see this is different than previous two. Okay, fine. These two, this part is same. Ename like. Which kind of pattern you need? Length must be 4 actually. Length must be 4. And for one length you are using underscore. Now 4 length actually. 1 underscore, 1 length, 1 more underscore, 2 length, 1 more underscore, 3 length, 1 more underscore, 4 length. Whoever have exactly 4 length, that means 4 underscores if you give, then what you are going to get? That such a names you are going to get in the output. So that is what you can see. Which name have 4 length? King have 4 length and Ford have 4 length. And in this position you can have anything. In this position you can have anything. So in any position, that is what, wherever underscore is there, you may have any character actually. That is not mentioned. But it must be 4 length. So 4 underscores you just use, whatever length is mentioned, whatever that n. So that many underscores you just mention actually. So that much length enames only going to display in the output. So how simple it is, you see. Okay. Now the next one, the next query, if you see, display names of employees whose name second character is A. So now this is little tricky actually. Together you have to apply. So you see actually second character must be A and first character may be anything. And after that you can have anything. Is it or not? So that is how you will frame the condition. Second character must be A means first character may be anything, that is 1 length actually. Exactly 1 length. Exactly 1 length means use underscore first. And after 1 length, second character must be A. And after second character, you can have any length string. So that means apply percentage. So both the wildcards you are using in one condition. That is what actually pattern you need. So that means whose names second character is A. What is actually second character A. And of course here word is also 4 length. We didn't mention actually. Here word is also there. Okay. Now let us come here. So here word second character is A and after that any length. And who else we have actually? James is also second character is A. So Martin is also second character is A. Is it? So that is simple. So in this way we can write down. So now you can try for this one and then you see actual answer. Okay. So for every query also, first of all, you try actually. Ultimately you have to get benefit, right? So let us see here. So select ename, where ename is like. What we need actually, display names of the employees whose name contains EAM. That means AM is the substring. Anywhere have any means apply the percentage. Maybe starting with AM or in between AM and maybe ending with AM, and after AM you can have any length. That is why before and after you just apply the percentage. So that is why whoever have a substring AM, all those names only we are going to display. So who have AM actually? Let us observe here. Adams have AM. So that is what one name is Adams, and James also have AM. James. So I think those two only, AM substring, and before any length and after any length. So that you can observe actually. Now the final one, display names of the employees whose name second character from last is ye. So you see opposite to this query, fourth query. So how you will write down? So last have only one, and before you can have any length. So that's it. You see how simple. So let us observe here. Alan last second from last to second character is ye. Alan, and Jones also same thing. And then Turner, and James. So you can see many names are satisfying this condition. James and Miller. Yeah, total 5 names are satisfying this condition. You can see from last. And this is what actually, these are the 6 queries actually for better practice we did. This is what, in this way we can use the like operator and wildcard operators actually. So like is a operator for comparing the strings actually. And if you need specific pattern, then we are going for the percentage and underscore. So percentage is for the 0 length or more than 0 length. So simply greater than or equal to 0 length. And this is exactly equal to 1 length actually, underscore. Okay.
Hi. So now let us see another important thing in the where class when you are dealing actually. So that is null values actually. Okay. This is very important, especially the columns which have null values. So first of all, let us try to understand what is null meaning and how to deal with the null values actually. Okay. So here, a field with null value is a field with no value actually. So that means, for example, if you take the EMP table, you can take especially the commission column actually. So here, out of all total 14 columns, we have actually values. You have values 1, 2, 3, 4, 5, 6, 6 fields. We have values, and no value is 8 fields actually. So this don't no value, this no value, like this. All empty things are nulls only actually. So they don't have any value actually. So those things you are going to treat as a null actually. Okay. And if you see a field with null value is one that has left blank during the record creation. Is it? So that is why whenever you are entering this particular record 7902, you didn't mention the value of this field actually. That is why it is left as a blank. That blank is nothing but null. That is what we are saying. First of all, at the time of creation of that particular record, you didn't enter anything. You left blank actually. So that automatically SQL treating as null value. But one thing you must have a clarity that null value is not as a 0 or it contains some space. You should not consider like that. Okay. It is not 0 or any space. It is null, which is left as blank actually. It is not neither 0 nor space actually. Okay. This is you should carefully observe actually. Okay. Nulls are different things. Maybe at the time of creating that particular record, value may be not available or maybe not applicable. At that time, you are going to ignore that particular field actually under that column. So that is why system automatically treating as a null values.
That is really very, very important. Okay, fine. But the here thing is that how to test for null values actually. So whenever you are applying any condition on commission, for example, how to deal with these null values actually. That is really very important. Another thing. So dealing directly with the null values, directly you cannot use actually. So that is what you can see here. Testing null values with the comparison operators such as equal or not equal are not possible. You cannot compare equal to null or not equal to null. So you are going to have a special operators to deal with nulls actually. So that is what the say we have is null one thing and is not null another thing actually. Following. So if any column have a nulls, those nulls to deal, we are going to have is null and is not null. So for example, first thing is null syntax. If you see, very simple. Select a class as usually from class and tables you mention. And in the where clause, on which column you want to put a is null. That means under this column, whichever field have null, those records it is returning. So for example, if you apply the on the commission column is null. So whoever have a null value, those records it is returning. So that is what you can see. 7566 7698 7782 7788. These are going to have a null values. So that is why these 4 records and here these 4 records null values. So these 4 records are going to return in the output actually. So total 8 records it is returning because under this column, whoever have a null value, those e names it is returning actually. So that is what Jones, Blake, Clark, Scott don't have any commission, and Adams, James, Miller, Ford also don't have any commission. So very simple. Okay, so such a columns only it is returning, and such a attributes whatever you mention in the select clause, those column values only you are displaying in the output. So in this case, 8 records it is returning. Now similarly, if you see the another thing is not null, so you can observe how you are going to is not null. So same way is not null you are mentioning actually. So now that meaning is what? Whoever have a not null actually. That means you can see here, this is not null, this is not null, this is not null, this, and this. Total 6 records don't have not null. Is it or not? So that is what if you see the select clause on the commission, where clause, commission is not null. Whoever don't have a null value. So that means these 3 and here these 2 and here this one. Total 6 records it is returning. Who are those? Smith, Allen, Ward, and here King, Turner, and here Martin. So that is why specifically we mentioned 0.0. It is not a null. It is some value actually. That is why it is not null. Okay. So in this way, first thing is base at the basic level. If any column have a no value means it is a null. So whenever you want to go for the comparison with a null, this is what the usage actually. So basing on the requirement, either you can use is null and accordingly you can use is null or is not null corresponding to that particular column name actually. Okay.
Hi. So now let us see one of the very important concept in SQL, that is aggregate functions. So these have many applications in SQL actually. In many places we are going to use it actually. So let us try to understand first of all at the basic level, what is this aggregate functions, what are all we have, and for what purpose we can use them. Okay. So it is very simple first of all that what aggregate functions will do commonly. So these aggregate functions, very importantly, set of values as input. So you are going to have a set of values as an input we will give. Always, very importantly, always only one value you will get as a output. That is what the one important thing must you understand from the aggregate functions. You may give the set of inputs, more than one input you can give. That too as a set actually. So set of values we are giving as an input, but over that it is doing some calculation based on the function, and any aggregate function finally giving only one value as a output. So that is the very first thing we must understand. So that working style of aggregate functions. Then these aggregate functions often we use actually in group by clause, having clauses actually. Some meaningful purpose is there actually for these three especially. So in select class we will use, in group by clause we will use, in having clause we will use. But we will not use these aggregate functions in the where class. So those things we will deep dive actually when you see these corresponding concepts actually. So in the group by, for what purpose we will use aggregate functions. The main purpose of the aggregate functions is actually, you can see a real application in these two only actually. So that we will see explore more at that time. So that is one thing. Now what are all aggregate functions first of all? So let us see in simple manner what we have actually. So the first one is sum. So you see these are not big things actually, as name implies we can understand in very simple manner. So sum is actually calculate sum of values. We are giving set of values, right? So it will simply sum all the values in that set. And average, so you can guess what it is doing actually. So calculates the average of set of values. Always what set we are giving upon that set, it is doing something actually. Here sum, here it is average, and then min. Min means what actually? It is finding the minimum value from this set actually. Same way max, it is going to get the maximum value out of all these set of values. And then count actually. So it is simply counting the number of rows in a table specified actually. So this is somewhat extra explanation is required, but time being let it be, we will see this separately. And very importantly, we have to understand from this actually, basing on the meaning of these aggregate functions. If you consider these two, sum and average, you can apply always on the numbers only, because we have many different many data types, right? Is it possible to apply on any data type? That is not possible, right? Summing. So you cannot sum a plus b, right? If it is a character type, you cannot sum them, right? If they are numbers, then only you can sum them or you can average them. So that is the reason these two aggregate functions always working on the numbers. Okay. And then especially min and max. These two, see, in the numbers you can find out minimum value, maximum value. And at the same time, if you have a text also, so that means text means, for example, if I have ABC, XYZ, PQR. So in this min means alphabetically minimum. That is what A. This is going to become min. Alphabetically max. This is what the max. So that is why even it will work on the text also. Not only on the text, it will work on the date also. So in the dates also you can work it actually. Okay. So this is what actually min and max. Min and max is working on numbers, text, date. And count function is going to work on anything. Okay. So this is what, first of all, very first thing we have to understand from the aggregate functions. Then if you see, all aggregate functions above are going to ignore null values. So because actually as a parameter we are passing here one attribute actually. Some attribute we will give. From the table, one of the attribute we will pass. Then in that attribute, that means under that column, if you have any null values, it is going to ignore them. So especially that, but except count. That is why I told count we are going to handle separately. We will discuss that separately actually. Okay. Now to get the more clarity on these aggregate functions, what we are doing is we are going to take one sample relation, one sample table, that is what student, And here were their roll numbers, their names, their marks we have actually. So now let us see what aggregate functions will do on this table actually. So first of all, let us see the sum function. So how you will write the query, you can see here. Select sum of marks. As we told, we will pass one attribute. Okay. So that means the set of values is nothing but what actually? So set of values are going to become these are. So that means here we are passing 80, 60, 90, 40, 70, 60. So these are set of values you are passing. That is what we given the definition, right? Aggregate functions, what we are giving, set of values as a input. So under this column, what are all values we have, those are we are passing actually. Then what it is doing, it is summing all these values because the function name is sum. So it is summing all the values, whatever you passed, and then it is giving single value. That is what we told, only one value. So sum of all these what actually, that you can see in the output 400. So if you sum all these things, we are going to get 400. Okay. So try to understand that set of values is nothing but whatever attribute name we are passing here, under that attribute, what are all values you have, those are going to become set of values as an input for that particular function. Basing on the function name, it is going to do accordingly, it is working accordingly, finally returning only one value. That is what the definition of aggregate functions, right? Yeah. So that is the sum function, very simply we can understand. And after that, if you see average actually. So even this we told what actually is, it is going to find the average of given input values. So here also that is what, if I write a query average of marks, then what is going to happen? First it is summing all these values, that is 400. And how many values are there? Total 6. So that is what the average, right? So you can see the output 66.66 is the average. Okay. So remembering the aggregate functions is not big deal actually, because these are the regular things in general. In general also we will use. Okay. Only thing is how to use them, where to use them, how to not to use them. This kind of constraints, if you know, then you can play with the aggregate functions. Okay. And then next the minimum. So as usually we are going to find the minimum value out of all these under this marks column. So that is what the query you can see, min of marks. So in the under this attribute, whatever be the minimum that we are going to find, so the output is 40. So that because 40 is the minimum, right, out of all those values. So that is one thing. And then max. So in the max also same thing, query, we are going to find the maximum marks from the this set of values, then maximum is 90. So hope this aggregate functions usage is very simple. See, sometimes actually instead of this sum of marks, we can do some other things also. So what we are doing is here sum of, we already seen another keyword distinct. Okay. So here you can apply distinct. So distinct of marks, if you apply, what is going to happen? Remaining query is same, select the sum of distinct of marks. Then now what is happening here is, it is not allowing the duplicate values. So you can see, is there any duplicate value? Yes, 62 times is there, but it is going to consider one time. So then what is happening actually? 80 plus 60 plus 90 plus 40 plus 70 only. This 60 it is not considered. So that means out of 400 minus 60, if you remove, you are going to get 360 only, 340 only. This is very, very important. So if you apply distinct on that column, what is going to happen? First, it is selecting all the values and eliminating the duplicates. That set you are passing to the sum. That is what simple understanding. So then that in the remaining set, how many values we have, that summation it is finding. So we are getting 340. So same way here also you can apply actually. That is what average of distinct of marks. Then what is going to happen? So of course result is same, distinct of marks, result is same. You will get this much. So 340 by, now how many values? 5 values only. So how much we will get actually? So here also I think this is 60.8 something, right? Yeah, I think this is 68.0. So we are going to get 68 as an average actually. So this is what actually. So, but here we cannot apply distinct. Even if you apply distinct also, min and max are not going to change. Because if duplicates are there, duplicates we are removing, but still that minimum value will exist, right? So even if you apply in this also, you can write down in min and max also distinct, but results are not going to change. But in case of the average and sum, results are going to change if you apply distinct on that particular column actually. Okay, so this is what, first of all, out of 5 aggregate functions, 4 aggregate functions, sum, average, min, and max. So the next one is count aggregate function. We are going to see separately, that is in the next lecture. Hi. So now let us see the aggregate function, one of the aggregate function count in this lecture actually. Because it have different variations actually. It is not that much straightforward like other aggregate functions. Okay. So that is why let us see what are all different variations, what count have actually. So for that, one sample relation we taken here, that is what student as usual one only. The only thing is here we have a null value extra. Okay. So you see the first variation is we can pass instead of the column name, that means attribute name, you can place the star also. So star meaning, in general, star meaning is what actually clean closure. So the clean closure meaning is what actually you are going to include everything. So everything we are going to consider. So that is what even meaning of this count star in this aggregate functions also. That is what return total number of records, including null values and duplicates. Okay, because if you pass any column name, sometimes maybe null values will be there, duplicate values will be there, but it is going to consider everything actually. So that is null and duplicates. So that is why if you write a query like this, select count star from the student table. So simply how many records are there in a table, all those count it is returning. That is what the output is 6, you can observe. Okay, so simply how many rows are there in a table in a relation, that many it is returning actually. So that is the first thing. So always remember that if you need total number of records in a table, simply you can use the count star actually. Then we have another variation. So that is count column name if you pass. Now, if you pass exclusively some column name, so that means it is going to return number of records by excluding null values. So this is also somewhat important actually. So you can see null values it is not considering, but it is considering the duplicate values. So that you can see if you write a query count of marks actually. So the column name is marks here. So in this marks column, if you observe, it is excluding null, right? So this is not going to consider. So now by excluding this null value, how many are there? Total 5 are there. So that is what the count is 5 now. Okay. So this is another variation in the count actually, because all these things are important whenever required actually. Now another variation if you observe, count and inside column name, before that we are placing a distinct. Now you can guess that for what purpose we are using this one actually especially. So here we excluded null values in case of column name if you pass. Now if you place a distinct, it is collecting only, it is not considering null values and duplicates actually. So that is what saying this this meaning actually, distinct null, not null values. That means null values not considering, and of course duplicates are eliminating. So if you observe, of course, anyhow null it is eliminating, and is there any duplicate here? Yes, 60 duplicate is there. So now distinct values are how many? Total 4 are there. So that is what, if you write a query on the marks, count distinct of marks, then this is excluding null and duplicates, so that output is 4 only. So this is what count is really tricky, and it have many variations. So basing on your requirement or application, you can utilize this count to aggregate function actually. Okay. Hi. So now let us see next clause in the select statement, that is the group by clause. So this is a very important clause, and we have many real-time applications also. So first of all, let us try to understand what is this group by clause. So as name implies, actually nothing is there. Very easily we can understand. So you can see here. So first of all, its definition is the SQL group by clause is used in the combination with select statement. Of course, we will use this one with the select statement, select clause, to arrange the same data into groups actually. So wherever same data is there, into groups. So for example, in a classroom, there are students. So you can make all males as one, all male students as one group, all female students as another group. Is it or not? Or you can make the groups like all grade A students are one group, grade B students are one group, grade C students as one group, like this. So this is what we are making the groups by using some similar data, same data. So for more better understanding, we are going to take our regular EMP table. So in this EMP table, if you observe, EMP number, ename, job, sal, and DEPT number we have, that is what department number. Now what we want to do here is, in this data, we want to make it a groups actually, basing on the department number. So how many department numbers are here actually? 10, 20, 30. So department wise, we want to make a group. So that is what you can observe here. First, if you see, all these yellow colored employees are in the department number 10. So that we are going to make as one group. And all red colored employees, you can see they are the department number 20 employees actually. Is it or not? So they are going to become another group. So that is what 10 is one group, 20 is another group. That is what the same data. So that means simply the employees who have the department number 10, they are going to become one group. Then 20, another group, 30, another group. That is what green colored employees. So that is what actually, first of all, making a groups actually. On these groups, what we are going to do, that is what the further discussion. So first of all, this is what the same thing. Now, if you see the syntax, how you are going to use the group by clause. Of course, select clause from clause. So select clause, selecting the columns, and from clause, from which table you want to retrieve the data is saying, and the condition, it is filtering the rows as usually. After where clause only group by clause is working, and where clause is optional when you are using the group by clause. That is up to us actually, based on the requirement. If you need to use the where clause, you can use it actually. That is not a problem. Okay. Now this is what the syntax, and you can have one column or more than one column in the group by class. So that part also we will see, with one column and more than one column, how it will work, we will see actually. Now if you see, this is what the example we are going to see. So select this part actually we are going to discuss in the lecture. Now from clause, from where actually, from the EMP table, group by DEPT number. So that is what we are grouping the department number. Okay, fine. Actually, Okay, here as we discussed in the department number 10, 3 employees are there. In the department number 20, 5 employees, and here 6 employees are there. What you are going to do with these groups actually? So that is what actually you can see the actual important point. The group by statement is often used with aggregate functions. So actually we are going for aggregating by grouping the different employees in this actually, or simply for each group you are going for the aggregation. That may be a count function, that may be a max of something, min of something, sum of something, average of something, to result set by one or more columns actually. So that is what one or more columns you are grouping. On that you are applying these aggregate functions. Now let us see actual select clause here. So now you are grouping the department number that you can display in the output. So here if you see the count function, count to star, count. So this is of course alias name, we know already. This is what alias name. Okay, let it be. Now count to star. So what this is doing is, in the department number 10, how many records are there? In the department number 10, 3 records are there. That is what the count. So that you can see the output. So 10 records are there in the department number 10. And in the second group, 5 records are there. In the third group, 6 records are there. That is what in the 30, 6 records are there. So that is what this is doing, aggregate functions. Now, another function if you take sum of cell actually. So output is as sum. Now if you see sum of cell. So in the 10th department, 3 employees are there. Those 3 employees, 2450, 5000 and 1300. So all these 3 you are going to sum actually. And similarly, 20 whoever have all of them salaries, we are going to sum. And similarly, 30 whoever have department number, their salaries we are going to sum. That is what you can see here. So for example, if you take 10, so 5000 plus 1300, 6300 plus 2450, so 8750. That is what you can observe here. So same way, if you sum all the salaries of department number 20 employees, department number 20 employees, we are going to get 10,875. Similarly for this. So that is what, if you observe on which column you are grouping, on the basing on that group, you can perform either count or sum, or next if you see average, so average salary you can find, that is what 8750 by 3, 10,875, 10,875 by 5, so 9,400 by 6. Then if you find the average, this is what you are going to get. Then next aggregate function, min of all this. So if you take the 10th department, so minimum is 1300, yellow color. And if you take the 20th department, minimum is 800, red color. So minimum is 800, this one. And the department number 30, if you take, minimum is 950, green color. So that is what we are going. So in each group, basing on the aggregate function you are applying, that one result it is going to return. So if you see one record, one result per group actually, that is really very, very important. If you apply the aggregate functions directly on the table, it will return only one value. So here also it will return only one value or one result, you can say, per group actually. So that is what you can observe. That per group is basing on the column you written in the group by clause. So this discussion is really very important. Now you can see here max of cell as maximum. So maximum salary. So in each group, maximum salary, 10 is one group. So in the 10 maximum salary is 5,000, and in the 20 maximum salary is 3,000, and in the 30 maximum salary is 2,850 actually. So this is what, in this way you are going to use the group by clause. So simply whatever column you are mentioning in the group by clause, whoever have the same data, all of them are going to become one group. On each group, you are going to apply the aggregate functions. And whatever column you are going to perform group by, that column you can display in the output. And in the remaining columns, definitely aggregate functions in the output. That is what you can see: count star, sum of cell, average cell, min cell, or maximum cell. So these are the main aggregate functions, of course. Okay, so that is what always along with the group by class, you are always going to have a aggregate functions in the select class. So this is really very, very important. We have many applications that we will see more when you are going for the complex queries actually. Okay. Hi. So now let us try to understand further in the group by class. So that is actually, so in the previous lecture, we've seen that with single column actually. Now let us try to understand with multiple columns. So here you can see, so multiple columns. So here you can see, whenever you have a multiple columns in the group by class, how it is working actually, how it is grouping them. So that is what you can see here. So we are going to mention as usually this part, more than one column we are going to mention. So for example, as usually our example, if you see the department number and job. So you see here department number. See, this order is also very important. Okay. So basing on that order only group is going to form. So first department number. So that is what, if you take yellow colored, that is the 10. Now what is the next one? Job. So these two together as one group, that is really very important. So that means in the 10th group, if you see in the 10th group, so department number and job we are displaying. And this example you can see, count star as count. So you see how groups are formed. So department number 10, 10, 10, 10 manager is one group, 10 president is one group, 10 clerk is one group. So these are three different groups in the 10th department itself. And then you see in the 20th, 20 clerk, 20th group, 20 department number 20 and job is clerk. This is one group. And 20 manager is one group, 20 analyst is one group. So pair with these two columns, different pairs, different groups, how many are forming? How many distinct combinations you have actually? That is what simply distinct combination. So that is what 30 salesmen, 30 managers, 30 clerks. Now aggregate function here we are applying count. So on these two columns, different groups, how many records are there in each group actually, as usually this one. So 10 manager is one only because 10th department itself 3 employees are there. So 3 groups are means each definitely are going to have at least one. So that is what one here. And after that if you come to 20 clerk, so you can count actually 20 clerk. So this is one, 20 clerk, and this is another one, 20 clerk. So that is what count is. Total number of records in this group, 20 clerk is 2 actually. And 20 manager is 1, 20 analyst is 2. So 20 analyst, this is 1 and this is 1. So 20 analyst is 2. So that is why you can see count is 2. So then 30 salesmen are totally 4 are there. So that part you can see these two, and this is the another one, and this is the another one. Okay. So 30 salesmen. So not the manager here. This is the salesman. Yeah. So of course totally 4, not the manager actually. So that is what total 4. Manager is 1, 30, and the manager is a clerk, and 30 is 1. So first of all, try to understand this is nothing but these groups are how forming. The columns what you are mentioning the group by clause, their combination, distinct combinations it is considering as one group. On that you are applying your aggregate functions. That is what we have to understand. So once this is clear, then the next one, if you see the sum of salaries. So 10 manager. So only 10 manager is one person. So that one person sum is 2450. So like that 5000, 1300. So here you can see the 20 clerk. So 20 clerk, this one 800 and 20 clerk 1100. 800, 1100 is 1900. That we can observe. So like that similarly remaining, and 30 salesmen if you see 5600. So 4 employees are there. Their salary summation is 5600. Okay. Then if you see the next one, average salary of average. So average salary. So 2450 by 1. So average salary in these three cases same. Here because 2 employees are there, by 2 950. Okay. And here only one, so same thing. Here 2, that means 3000. So here 4, so 1400, 4s are 5600. And here 1 means same thing you will get. Then next minimum salary. So in each group minimum salary, whenever one is there, that is the minimum, that is the maximum, that is the average. That is what you have to understand in one case. And remaining case accordingly it is going to change. Now you can see for the maximum also. So here overall what we have to understand is, okay, when you have more than one column in the group by clause, all those columns distinct combinations is going to consider as one group. How many records are there satisfying each one group? On those only you are applying your aggregate functions. Okay, so that is what, whenever you have a multiple columns on the group by clause, how it is working. That is also very important. Okay. So now let us see the next clause, that is having clause. So this is actually extension to the group by clause action. So let us try to understand for what purpose we have a having clause. So it is very simple one. So you see having clause enables you to specify the condition that that filter which group results appear in the result action. So actually group result is there. Upon that it is going to work actually. So we are putting a condition on a groups. So which group you want to display as a output, that you are going to decide by using having clause actually. So for example, this is what the table we are observing, and these are the groups actually. So 3 groups are there basing on the DEPT number. Is it or not? 10, 20, 30. Now syntax, if you see having clause, this is what actually up to here normal thing only, whatever we discussed, and extension to that having clause we have. So having, and we are going to put a condition. So whatever groups you prepared here, those groups you are filtering by using having clause. That's it. Very simple understanding. Now if you see the example, so this is what we seen earlier, right? So select EMP number, EMP group by DEPT number. So now if you have DEPT number comma count star, that means department wise you are counting actually. So then this is what the output you got. Is it or not? In the 10th department we have 3 students, 3 employees, and in the 20th department we have 5 employees. In the 30th department 6 employees. Now we are not we don't need this result actually. Now assume that we have a condition that we need only the department numbers which have more than 4 employees actually, which have more than 4 employees. So 10 department only 3 employees, 20 department have 5 employees, and 30 department have 6 employees. So we need only these 2 groups in the output. At that time, you can see we are putting a condition. So if you observe here group by class, whatever groups are made on that group, this is what the count you calculated. On that count, you are putting a condition here. That is what we are specifying a condition so that group results it is filtering. Is it or not? So simply 3 greater than 4, condition false. Next 5 counts are 5 greater than 4, condition true. So 20 is coming in the output, and then 30 that means 6 greater than 4, so condition true. So that is why in the output you have only those 2 records. You can observe that. So simply try to understand having clause we are using for filtering the groups simply. Okay, basing on some condition actually. Okay.
Now, if you see, having clause is added to SQL since where clause cannot use it with the aggregate functions. This is really very, very important condition that in the where clause. So here you can add where clause, right? Here you should not use aggregate functions like count or sum. All these aggregate functions you cannot use actually, because you see aggregation is happening after groups actually. When you are going for groups after where clause is completed. So if where clause is already filter the rows and then you are going for the group by. After group by execution over, it is never going back to again where condition. So that is why aggregate functions simply aggregate functions we are not going to use in the where clause actually, because where clause is going to execute before group by clause. So as we discussed already, where clause is for filtering what actually? Filtering rows, filtering tuples. But the having clause is for what purpose actually? Filtering groups actually. That is what try to understand the difference. So that is what actually where clause is used to filter the rows basing on the condition. Same way having clause is used to filter the groups basing on the groups actually. So whatever group by clause is created, that is what this is created first. On that, whatever condition you mentioned here, that condition we are applying. So that is what very simple understanding of the where having clause actually. So try to understand this main difference also. That is what these points. These points are very important. We must be careful whenever we are using the having clause actually. Okay. Right. So now let us see the next concept in the SQL. So that is set manipulation operators. Okay. So actually, if you know the mathematics set theory, so whatever concept there, the same thing we are going to apply here actually. But this is in case of data actually. That means in the database on the columns you are applying this set manipulation operators. Okay. So that means between the records you are applying this set manipulation operators. So let us see, first of all, what is this one? The following rules you must hold if you whenever you are applying set R and set S. For example, those are the two relations. That means those are the two tables actually. So these two rules you must apply actually. So those are things. The first one is R and S must have the same quantity of attributes actually. What does it mean? For example, I am simply doing relation R union relation S. What does it mean actually? For example, relation R have attribute A, attribute B, attribute C. And relation S have relation, for example, P for Q, R, and S it have. So when you are performing union, how many number of attributes here we have? Here also you must have same actually, but here you have 3, but here you have 4. So that is what actually he is saying, both must have same. So for example, if I remove yes, only 3 attributes we have actually. So that is what the first rule. And after that, attribute domains must be compatible. So this is another next one, important one actually. So that if you observe, these two data types, so domains, corresponding attribute domains must be compatible. So that means a domain of A, domain of P, that means the data type must be same. Then only you can combine them. For example, A, B, C, A have data 1, 2, B have data, for example, small a, small b, C have data, for example, 2.4, 3.6. Now, P, Q, R, that means A data type is integer. And here, for example, P data type is char. That means what we are going to have A, P, Q. So for example, we have these values actually. When you combine these two, A, P, Q are 1, 2, then A, P, Q, you are going to have. That is under one column. Now, if you see what is the data type of this if you combine, because whatever data under P is going to under A actually. Is it done? Now, here it is integer. If here it is integer, here if it is char, so that is what not compatible. So that is why Attribute domains must be compatible correspondingly. So that meaning is what? First attribute in the first relation, first attribute in the second relation must be same. Similarly, third in the both relations. Like that, how many attributes you have? Corresponding attribute domains must be same in both the relations actually. So that is what another thing you must ensure. And another rule is duplicate tuples get automatically eliminated. Of course, this is fine. So for example, assume this is now both the uh, here both the domains are same, assume. So that means this is also uh, compatible. So for example, here we have a data 2b 3.6, that is possible. And that means this is integer, this is char, and this is float, assume. And correspondingly pq are also same domains actually, because 1 and 2 you are satisfying. And the third one, what is meaning of third one? For example, 3 x 7.2, 4 y 6.4. Now when you combine these two, that means that may be union, that may be intersection, that may be minus. But ultimately, if you go for the union, this record, and this record already there actually, duplicates automatically you are eliminating. This and this you will get actually, especially in case of union only. In case of intersection, common things anyhow you will select. And in case of minus, something is happening actually. So those things we will see individually in the next lectures. But here, if you understand, duplicates automatically going to eliminate by set manipulation operators. So try to understand these three rules must hold when you are applying set manipulation operators, that is union, intersection, and minus section. So what is the first one? Number of attributes in the first relation and in the second relation must be same. Corresponding domains must be same. And of course, duplicates automatically it is going to eliminate. So that is what, if first two, if you are ensuring, automatically third one is going to ensure by the SQL actually. So this is what, first of all, rules for using set manipulation operators. So in the next lecture, let us see union, intersection, and minus together actually. Okay. Hi. So now let us see how union, intersection, and minus are working in the SQL actually. So in the last lecture, we seen the its rules. Now let us try to understand. So here, if you see the first one, union operator. So how union operator is working? So simple that it is used to combine the results of two or more select statements actually. So we are going to have two select statements. So by following these two rules, so by using those two rules, it is going to combine the results actually. How and all? Let us try to observe. So let us take one simple database. So here we have a three relations: depositor, borrower, and loan. And corresponding data, if you take in the depositor, you have the two columns, and this is the data we have. And in the borrower, two columns, and this is the data we have. And in the loan, this is the data we have. Now observe that loan number here we are using in the loan. Okay. And here account number, actually in the loan you have a loan number, branch, and amount. So let it be. So we will come back to that. Now how union we are going to use it here. So here if you see the query, first of all, find the names of the customers who have a account or loan or both actually. Okay. So account meaning is in the depositor you are going to have an account. Loan meaning is in the borrower we are going to have a loan actually. And both meaning is both in both what we have actually. So that let us try to observe here. First of all, the select the customer names from the depositor. So from this query, who are all going to come? Customer name from the depositor. Only customer name, that is what? A, B, C, F we are going to have. And then he also told loan actually. So that is why from the borrower table, we are selecting the all customer names. So from this, what we are going to have? D, B, C, E. Okay. if you see the output, what we are going to have, output in both, both must be compatible. That is what he told. So quantity of the attributes must be same. Here one attribute, here also one attribute, and domains must be compatible. Yes, correct. Here character, here also character. Both of them is varchar. Now in the output, customer name you are going to display. What will be the output? That is what you are applying union on these two results. That is what you can see. Two or more select statements, results you are going to combine actually. So this result is ABCF. This result is DBC. So A, B, C, F. And when you come to here, D, it is going to take, but B already existed. So duplicates automatically eliminating, right? So that is why B is not going to take again. C already there, but E not there. So E is also going to take in the output. So total 6 records, it is going to return this output. Okay. So that is what union is applying. So try to understand all these three rules. Automatically duplicates are eliminated in both. Only one time it is considered, and it is compatible. Both the attributes, whatever you are trying to display, both must be compatible, and the number of attributes in both must be same. That is what we guarantee. And when you apply union, it is combining the both the select statements results actually. So this, in this way, union is working. Okay. Now let us try to observe intersection. So that is what in the next slide. So here you can see intersection. So intersection meaning is what? So if you see union meaning is what? This and this. So that is what a depositor and borrower, both you are going to consider. Now intersection meaning is what actually? General mathematical meaning. So common part you are going to consider. That is what you can see. It is used to select the common rows from both the relations actually. So for example, find the names of the customers who have both account and loan. This is not or operator actually. This is and. That means in both must be there. So that is why same query if you take, here we are going to have A, B, C, F, and this is C, F. Okay. And here we are going to have D, B, C, E. Okay. So this is what. Now he is asking intersection operator you are applying, intersect. So then in the output, what we have? So first table, whatever column, corresponding column is there, that name you are going to display in the output, customer name, and common. A is not in both, B is not, B is both actually, and C is in both, and this is F is not in both. So that's enough. So 2 records it is returning. That is it. Okay. So this is the intersection part. So normal mathematics set theory, whatever we are going to have meaning here also same thing, but this is talking about the rows actually. Entire row in both if exist, those rows only you are going to return in the output. Okay. Now let us see the next one, difference minus operator actually. So that is what if you observe minus operator is what actually, if you have two relations R1 and R2, we want to select all those tuples that are present in only R1 but not in R2. So that is what if you take R1 and R2 only present in R1, not in R2. That means even common part also you want to exclude actually. So that is what you can see. This is what the as usually tables. Now find the names of the customers who have loan but not an account. So only they must have a loan actually. They should not have any account here. Such a customer names we have to display. So that is what customer name from the borrower. First you select customer name from the borrower. So customer name from the borrower is D, B, C, F. And then customer name from the depositor. So in the depositor, A, B, C, F actually. This is E. Okay. Now, what we are saying actually, minus. So from this you are removing. So in the output, what we are going to have, that observe. So customer name. Okay. So you see here, A is not here. B is here actually, that you have to exclude. Common part you have to exclude. C is also common part. So that means D and E. Observe, D don't have an account. D don't have an account. E also don't have an account. So such a customer names we need, right? This is what the output. For example, if you see who have, for example, who have account, okay, but not loan. Reverse if you are asking. Then what we have to do, swap these two statements actually. That's it. So that means in the first output, you are going to have ABCF minus DBCE actually, DBCE. So that meaning is what? A is not in both, B is common, C is common, F. Now what you can say, A and F don't have any loan actually. So that is what meaning, right? Who have account but not a loan. So that is why if you simply swap, output is different actually. But in case of minus intersection, even if you swap these two, output is same. Even in case of union and intersection, if you swap that means you can say commutative. If you swap the results, if you swap the queries, output is same, maybe order is different. But in case of minus, if you swap the queries, then output is going to change. That is what you can see in both cases. Okay. So this is what set manipulation operators, that is union, intersection, difference. Okay.
Hi. So now let us see one of the important concept in SQL and very logical, that is joins actually. Okay. So whether you are a student or a working person, if you are looking for the database developer, definitely database is nothing but many number of tables definitely will be there. So to get a required data, you have to go for the joins actually. That means you have to join the tables actually. So you must have the clarity when you are joining the two tables or more than two tables, what is going to happen background actually. So let us try to understand first of all what is join meaning, and let us deep dive in this concept actually. So the first of all, the definition of join is simple. That is what a SQL join statement is used to combine actually data or rows from two or more tables actually. So of course we are going to have some condition common field between them. So that is what we are going to explore more. So this common field part is actually our discussion, but just try to understand that what is meaning of join. So to get the first of all, instantly what is meaning of join, let us take one simple example here. So assume that this is the relation 1 and A and B are the attributes, that means column names A and B. And here these are the rows, two rows we have in this relation 1 table actually. Let us take another one, relation 2, where attributes are C and D, two columns are there and three records are there. Now, if I write a select statement on these two, a simple select statement when you write, what is going to happen in background? So let us see that. So this is what I written. I want to display all the columns from both the tables. So that is why star, make it simple first of all. Very important part is this green colored part. Relation 1 comma relation 2 we just written in the query. But what is happening in the background? That is very important. So the relation 1, the first record it is taken here, that is joined with this first record in the second table. Same thing, relation 1, the relation 1, first record joined with the second record. First record joined with this third record in the relation 2. So simply, every record of relation 1 is going to join with every record in relation 2. So that is what three rows you are going to have in the result. Not only that, even second row in the relation one also same way it is going to combine. So total, this is what the result actually. So you can see this is the first record in the relation one and all records in relation two. Same way second record in the relation one and all the records in the relation two. So here you have two rows. Here we have three rows. So 2 into 3, 6 rows are going to generate in the output. So what we can conclude from this, here m rows, here n rows. So simply if you write like this, then total number of rows in the output is what actually m into n. That is simple understanding. Because everyone combining with every other in the other table, right? So that is the first thing. So this is what first of all join and its result actually. But this is not recommended for actually. Upon this, we are going to do so much work actually when you are combining the tables. So that is the reason. First of all, this is actually called as Cartesian product. So this is called as a Cartesian product actually. That means Cartesian join. Or sometimes you can call as a simply cross join. Simply you combine. So this is simple. On this data, we are going to put many constraints actually. So that filter is going to happen on this Cartesian product. That is what first of all you must understand. Then now let us see broadly, first of all, different types of joins actually. And each join we will see separately so that we will get the better clarity. So types of joins, mostly overall we have two types of joins. The first one is inner join. So in the inner join, you can see here theta join, equi-join, natural join, self-join. Total 4 types are there. And of course, all of them is very simple. Okay. Only thing is, first of all, here in the cross product, what is happening? Try to have a visualization. That is more important. Now, another one is outer join. This is inner join. This is outer join. So meaning wise, it is very simple actually. Here we are going to have a condition. Of course, here also we are going to have a condition. Only the rows which are satisfying the condition, those only will come. Here, the rows which are satisfying this condition will come. Not only that, some other attributes also, some other rows also going to be there in the output. So other rows also going to be there. Just a rough idea here. When we are discussing, we will get the more clarity. Here, just whoever satisfied the condition, those rows only is going to come. Those records only coming in the output. But here, satisfied rows, not satisfied rows, basing on the join you are using. So that clarity we will get when you are discussing. Okay. So this is what, first of all, try to understand. It is not a big deal actually. At the student level, especially, people will confuse at this concept actually, at this topic, joins. But nothing is there. First of all, we are joining two tables, general discussion. And after that, here if you see, when you simply write relation 1 comma relation 2 in the from clause, then internally cross product is going to happen. That cross product output is like this. So this is what the visualization you must have actually. Okay. So try to understand here two types of joins, inner join, outer join, and we have different types internally for everyone. So let us see each join separately in the coming lectures. Hi. So now let us see one of the important concept in SQL and very logical, that is joins actually. Okay. So whether you are a student or a working person, if you are looking for the database developer, definitely database is nothing but many number of tables definitely will be there. So to get a required data, you have to go for the joins actually. That means you have to join the tables actually. So you must have the clarity when you are joining the two tables or more than two tables, what is going to happen background actually. So let us try to understand first of all what is join meaning, and let us deep dive in this concept actually. So the first of all, the definition of join is simple. That is what a SQL join statement is used to combine actually data or rows from two or more tables actually. So of course we are going to have some condition common field between them. So that is what we are going to explore more. So this common field part is actually our discussion, but just try to understand that what is meaning of join. So to get the first of all, instantly what is meaning of join, let us take a one simple example here. So assume that this is the relation 1 and A and B are the attributes, that means column names A and B. And here these are the rows, two rows we have in this relation 1 table actually. Let us take another one, relation 2, where attributes are C and D, two columns are there and three records are there. Now, if I write a select statement on these two, a simple select statement when you write, what is going to happen in background? So let us see that. So this is what I written. I want to display all the columns from both the tables. So that is why star, make it simple first of all. Very important part is this green colored part. Relation 1 comma relation 2 we just written in the query. But what is happening in the background? That is very important. So the relation 1, the first record it is taken here, that is joined with this first record in the second table. Same thing, relation 1, the relation 1, first record joined with the second record. First record joined with this third record in the relation 2. So simply, every record of relation 1 is going to join with every record in relation 2. So that is what three rows you are going to have in the result. Not only that, even second row in the relation 1 also, same way it is going to combine. So total, this is what the result actually. So you can see this is the first record in the relation 1 and all records in relation 2. Same way second record in the relation 1 and all the records in the relation 2. So here you have two rows, here we have three rows. So 2 into 3, 6 rows are going to generate in the output. So what we can conclude from this, here m rows, here n rows. So simply if you write like this, then total number of rows in the output is what actually m into n. That is simple understanding. Because everyone combining with every other in the other table, right? So that is the first thing. So this is what first of all join and its result actually. But this is not recommended for actually. Upon this, we are going to do so much work actually when you are combining the tables. So that is the reason. First of all, this is actually called as Cartesian product. So this is called as a Cartesian product actually. That means Cartesian join. Or sometimes you can call as a simply cross join. Simply you combine. So this is simple. On this data, we are going to put many constraints actually. So that filter is going to happen on this Cartesian product. That is what first of all you must understand. Then now let us see broadly, first of all, different types of joins actually. And each join we will see separately so that we will get the better clarity. So types of joins, mostly overall we have two types of joins. The first one is inner join. So in the inner join, you can see here theta join, equi join, natural join, self join. Total 4 types are there. And of course, all of them is very simple. Okay. Only thing is, first of all, here in the cross product, what is happening? Try to have a visualization. That is more important. Now, another one is outer join. This is inner join. This is outer join. So meaning wise, it is very simple actually. Here we are going to have a condition. Of course, here also we are going to have a condition. Only the rows which are satisfying the condition, those only will come. Here, the rows which are satisfying this condition will come. Not only that,
some other attributes also, some other rows also going to be there in the output. So other rows also going to be there. Just a rough idea here. When we are discussing, we will get the more clarity. Here, just whoever satisfied the condition, those rows only is going to come. Those records only coming in the output. But here, satisfied rows, not satisfied rows, basing on the join you are using. So that clarity we will get when you are discussing. Okay. So this is what, first of all, try to understand. It is not a big deal actually. At the student level, especially, people will confuse at this concept actually, at this topic, joins. But nothing is there. First of all, we are joining two tables, general discussion. And after that, here if you see, when you simply write relation 1 comma relation 2 in the from clause, then internally cross product is going to happen. That cross product output is like this. So this is what the visualization you must have actually. Okay. So try to understand here two types of joins, inner join, outer join, and we have different types internally for everyone. So let us see each join separately in the coming lectures. Hi. So now let us see another join, that is equi-join. Okay. So we are not going to learn anything new from this join actually. This is what we already seen actually. And all you can see. Equi-join is done when theta join uses only equivalence condition. That's it. See, actually there we seen some of the comparison operators, right? That is equal, less than, greater than, less than or equal to, greater than or equal to, not equal to. But in the condition part, if you are using always equal, then that is equi-join. That's it. Nothing is there. So that is what you can see here. These two tables, if you take, so the query is same. So display roll number of students who taken course DS actually. So in all, for getting the output of this query, in all conditions, if you are using equal, then that is going to become equi-join. So let us see what is that one. So let us select what we need actually. We need roll number. So roll number from the student table. So first of all, let us take here from. So that is a student. Alias name we are going to give S, and course alias name we are going to give C. Now we need roll number from the student table, that is what S dot roll number, and we need C name, course name. So that is from the course table. So that is what C dot C name. Now we need to put a condition, that is what where clause. And here if you see, first of all, these two tables you have to join, right? Okay, that means on which constraint you have to join them. That is what basing on these two. Is it or not? CID here. So that is what S dot CID equal to C dot CID. Now, every student, what course they taken, that result is ready now with this condition, getting or not. Every student, what course they taken, those records are ready. In those records, and operator, in those records, C name must be DS only. That is what our requirement. So that is what DS only we are mentioning. So try to understand it with the first condition. Every student, what course they taken, those records are ready. Now by applying the second condition, what is happening in those records, wherever you have DS, only those records it is returning finally. So that what is going to happen, roll number and course name, C name, it is going to display. Roll number 1 taken the DS data structure, and who else taken roll number 3 taken DS. So this is what the output, these are the two attributes we are displaying. So this is what actually equi-join is simple. In the condition part, if you are simply applying equal operator for all the conditions, then we can say that is equijoin. Okay. Hi. So now let us see another join, that is a natural join. Okay. So this is somewhat interesting actually. So how this natural joining is doing, let us try to understand. So you can see here, natural join does not utilize any comparison operators. Very important. You are not going to have any comparison operators for joining the tables actually. Main condition, we are not going to put by using this actually. How and all we are doing? In this type of join, the attribute should have same name and domain. So let it be this point, we will see. Then in the natural join, there should be at least one common attribute between two relations actually. So you can see what does it mean. For example, these two records, if you take these two relations, if you take, what he is saying actually, same name and same domain. That is what you can see. CID here, CID here. Both of them is same name and their domains also same. That means their data type is also same. We are entering only characters. So that is what. And that too, at least one common attribute. Yes, here CID is the common in both the relations. Then only you can apply the natural join. Suppose, see, okay, first of all, let us try to understand. So natural join you can apply only when if you have at least one common attribute from the both the relations. That common attribute domain must be same in the both the relations. Here if it is character, here if it is integer, that is what not common actually. The domain is not same actually. Okay. So whenever you have like this, how you will apply the natural join? So you see here, it performs selection forming equality on those attributes. So how it is working internally? You are not going to put any condition explicitly, but internally it is going to do something. That is what actually it is applying the equality operator on the common attributes actually. So student.cid equal to course.cid, automatically it is applying internally. Whoever not satisfying, of course it will eliminate. That is normal process. And whoever satisfy equal, those attributes will appear in the output. So this is normal thing only, but internally how it is applying on the common attributes, how many you have, for all those, it is putting the equal operator. So what is its syntax you can see here? Select star from, this is the relation 1 and this is the relation 2. Just write down in between natural join. Then automatically it is cross-checking that in the relation 1 and relation 2. What are the common name attributes? If you have one attribute, on that one attribute, it is going to put a equality condition. If you have two attributes common in both, so first common attribute apply the equal and second common attribute apply the equal. Got it or not? So that is what actually happening. So for example, common attribute 1 equal to common attribute 1 from the both the relations, relation 1, relation 2. If you have one more actually, then in between them logical operator and is applying, then common attribute to 2 is equal to common attribute to 2. So these two are from the relation 1, these two are from the relation 2 actually. So that is what the tricky part. It is, so you are not putting the where clause here. That is what you have to understand. Without writing the where clause, it is applying internally the condition that is because of this natural join. So that is also very, very important. So for better understanding, let us take one simple example here. So that is what he is asking, the roll number and course of every student. That meaning is what? Roll number and course name we have to display in the output. So how you will do this one actually? So that is very simple. For example, select what we need actually. See, of course, here we mentioned the star, but we can take the column 1,
whatever columns you want to put, that is normal discussion. So what we need actually, s dot roll number and c dot course name, c name. So these two are from where? From, yeah, now important part. Relation 1, that is student, alias name, let us give S. Then what we have here, natural join. This you are joining naturally. This we are joining naturally with course table. That is what course. Here you can take course C. So that's it. You observe that we didn't written any where clause. Because if you want to put any condition, you must have where clause, right? But we are not writing. But internally, what we are going to have, s dot cid equal to c dot cid. It is applying internally. So that matched records only it is coming output. So roll number, course name in the output. For the roll number 1, he taken DS. For the roll number 2, B means DBMS. For the roll number 3, again A means DS only. For roll number 4, C nothing but operating system. So this is what the output we are getting. So try to understand all different types of joins actually. So sometimes if you want to write down optimally without having many lines, you can go for natural join. Okay. So now what we will do is, to get the more clarity, we are going to take one more query on the same tables by applying natural join. So that is what you can see here. So that is what actually display the roll number and course of students who taken the course DS. See, this query we already seen in another exam, in another join actually. But here how you will write down, that is the matter. So here also simple actually, select, then we need roll number, s dot roll number. Let us take alias names here and c dot course name. So that is what c name. Okay, this is fine. Now come to the from clause. So as we discussed here, first of all, you have to join these two by applying equal operator. Because you have a common attribute in the both and their domains are also same, go for the natural join. So that is what student, yes, natural join. This with another table course, alias name is C. See, if you leave like this, what is happening actually? It is going to come like this result. Both of them is same right here and there. But we have an extra constraint that course must be DS. So for this, we have to go for the where class. So here with what intention this query we are providing is, whenever natural join is there, of course, how many common attributes are there, upon all those, it will put a equal condition. But if anything extra is there, for those only you go for the where class. Because this maintaining in the natural join is not possible. So that condition you write down explicitly. That meaning is what? C dot C name must be DS. So that is what. So this we are unable to cover in the natural join. So other conditions you come to the where class. So with this, what is happening? Roll number 1 take in the DS and roll number 3 also take in the DS. So this is what actually natural join. Very, very important natural join. Simply when you are applying the natural join on two relations or two tables, first of all, internally it will cross-check that how many common attributes are there with the same domain. That means same name attributes, how many are there. How many are there, that many equal equi-join condition, it will put in internally automatically, though we mentioned explicitly in the query. And other than that, if you have any extra condition, that you put in the where clause. So this is what actually natural join. Okay. Hi. So now let us see another join, that is self join. So you see, this is as name implies self. So till now we actually seen that we are joining the two tables. We are joining one table with another table, actually another relation. But in case of this, as the name implies, self join means we are joining the one table with itself actually. So that is what simple, right? So that you can observe that a self join is a join in which table is joined with itself. So this is only possible whenever you have like this. It is also called, of course, unary relationship. So table have a relation with itself. So that is what, especially when a table has a foreign key, which is referencing its primary key actually. Because we know already primary key and foreign key. And one example also I showed whenever we are discussing this primary key and foreign key. So the table's primary key, whatever is there, that you are referring in the same table in the another attribute actually. So that, for example, so let us take this table. So employee table. So you can see the employee number is the primary key here. So these are the employees. Here, if you observe the MGR column, MGR is nothing but manager. So for each employee who is the manager, their ID we are writing under this MGR column. So who is the manager for 2? For the Hari, manager is employee number 1, that is Krishna. Krishna is the manager for Hari actually. Ramu's manager is what actually? 2, that means Hari actually. So this is what, first of all, this second point you can say, relationship. So this is the foreign key now, and this is the primary key. Employee number is the primary key because it is referring in the same table only. So that is what, first of all, self-referring unary relationship. Now, how you will perform self-join on this? That is basing on the query actually. Now let us see the query. List each employee manager. So for the Krishna, who is the manager, for Hari, who is the manager, for Ramu, who is the manager, we have to tell. So how you will write down this one actually? Okay. So let us so let us start in this way. Select class. You just start somewhere actually. Definitely you will get the idea. And I am not filling this part right now. Go for the from clause. So here we are joining means two tables required. But both the tables are employee table only, right? So let us take employee and E1 and another table employee E2. So that means this table 2 times you taken and both the tables are combined. That means cross join is happened. That means here 4 records are there. So 4 into 4, 16 records are now there. So what I am doing is, for better understanding, to frame the condition here, because we need each employee manager. So what we are doing here is, I'm going to take the second record, how you combined with the E2. So that is what you can see here. So this is E1 part, this is E2's part. And in that, one of the record in the E1, second employee, how it is combined with E2 records actually. So employee 2 with all persons we have. So from this, what you can understand, from here you can write down this condition part first of all. And then here also, who is the manager, who is the employee, correctly we can write down. Simple observation, come to the employee table, original table. Here I am saying Hari's manager is 1, is nothing but Krishna. So Hari, Krishna, where you have that combination, Hari here, Krishna here. So that's it, right? So you observe here, manager 1, in this table he is the manager, in E2 he is the employee. So wherever this match is occurred equal, those persons E name ename we need. So from the E1, ename is going to become the employee, and from the E2, ename is going to become the manager. Got it or not? So in that way, let us try to frame the condition. So first of all, let us frame the condition. That is very important. So what is the condition? You can observe that wherever MGR in the E1 is equal to employee number in E2, wherever it is same, that is what corresponding employee and its manager. So E1 dot MGR, if that is equal to E2 dot ename, E2 dot EMP number. Because here employee MGR number is also nothing but employee EMP number, right? So in that way, we are putting the condition. See, don't confuse. Only second employee details we taken from the E1. How it is joined with E2, we taken all scenario. From that scenario, this is what the joining condition. So with this join condition, what is going to happen? We have only this record, and with 3 also correspondingly record will be there. Now from the E1, ename is going to become employee. So E1 dot ename, okay, give the alias name simply employee, and from the E2 we need ename, but he is the manager actually. So E2 dot ename, but he is the manager, give the alias name manager. So that's it. So what is going to happen? So in the output, if you observe, employee and alias name is manager. So let us take manager. Of course, for 1, there is no match, but for the 2, 2 means what actually? Hari, and his manager is Krishna. And for 3, Ramu, who is his manager? 2 is nothing but Hari. And for 3, Karim, his manager is 1 is nothing but Krishna again. So these are the 3 records it is returning. So that is what, always take a simple scenario. If you have any confusion, take one of the row, how it is joining with other thing, especially in case of self join. This is what confusing thing actually. So here if you take E2, here if you take E1, then things are going to change. Here if you take E2 dot ename as an employee and E1 dot ename as a manager, then you are going to get the wrong results. So that is why you must be very careful whenever you are using the self join. Okay, so in this way you can list the each employee manager actually. Okay. Hi. So now let us see outer join. So till now we've seen that inner join part. So now let us see what is outer join. So in the inner join, as we discussed already, whenever you write any condition, the records which are satisfying that condition only coming out actually. That means only those records you are returning. So that means you are displaying. But what is the meaning of outer join? So outer join, it is not only just returning the records which satisfy the condition, some records which are not satisfied also returning actually. Okay. So that is what it's meaning. The SQL outer join returns all the rows from both the participating tables which satisfy the join condition. That is one thing. Along with that, rows which does not satisfy also it is returning actually. But this is which records has to return though not satisfied. That is what we have to understand actually. Okay, so that is very simple thing. So here we have a different types of outer joins are there. One is left outer join or simply left join, a right outer join or simply right join, or you can say full outer join. So let us see these three things one by one. First of all, just try to understand what is outer join. Not only satisfied records, condition satisfied records, and also not satisfied some records it is returning. That some records is going to talk these three parts actually. Okay, so now let us see these three things one by one in the next lectures. Hi. So now let us see the first one in the outer join, that is the left outer join. Okay. So as we already discussed that condition satisfied records, not only that, not satisfied records also coming in the output actually. So how and all, basing on this meaning only, concept is there actually. So you can see here, always in the join, two tables are participating. So in that join, if you take a left side, first parameter, first table as a left and the second table as a right. So that is what left outer join actually. So here you can see overall this sentence meaning is the rows which you are returning, all matched rows, of course it is returning, and not matched rows, not matched records from the left side table are also coming in the output actually. So for that for better understanding, let us take these two tables. So in this, if you put a condition that where CID from the student table is equal to CID from the course table, so that these first four records are going to come. But for the 5 and 6, there is no match actually. So if you put this student table as a left side, then these two records are coming in the output. So that part let us see with the clear explanation. First of all, syntax for using the left join is this one. So select star in the from clause. If you observe very importantly, this is the left table, table 1, and table 2 is the right table always. So this is the left table. And actually we are not going for the where clause. This you have to observe actually. If you are putting any outer join, then immediately after left join second table included, you have to go for the keyword on and then put a condition actually. So we on which column in from the both the tables you want to put a condition, put that condition. Then what is happening? Whoever satisfied all matched rows, of course coming in the output, but not matched rows from the left table are also coming in the output. So let us try to write down from this only. So that is what actually, this is left table, right table. This is what matched part. Matched part is coming and also this part is also coming in the output. So for example, we want to display names of the students who taken the course, which course they taken. Okay. So for that, names of the students who taken the course actually. So that what we are writing, select, select, let it be, we will come to the from clause first of all, from. So left table, we need all the students actually. That is what student. Then keyword we are going to use left join. So that is what left join. And then right table is a course. Let us have here course. Then we have to put a condition, right, on student.cid equal to course.cid. Then with this, what is happening actually? So that is what you can see the output. So because we are printing all the records, all the columns from the both the tables, we are going to take star here. Now you just observe here, Ravi taken course A, that is nothing but DS. That is what you can see here matched. So this is from the student table, right? And this is from the course table. Student.cid, A, course.cid, A, both of them matched. So that record came. And here also this record, Krishna record came.
matched, matched, matched. So that means for the first 4 records match is occurred. But for the next 2 records from the left table, especially because it is left join, in the left table, these 2 records don't have any match, but still those are coming in the output actually. Okay, fine, but whenever not matched records are coming in the output, what about corresponding cell values in the other table actually? So here we are going to have by default null values actually. So that you can see here, null, 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 null. So this is what left join. So very simple that. So requirement is like this. Whichever table you are placing in the left side, you need all the records, whether they are matched or not. Then put such a table in the left side if you want to use left join. Okay, so if you understand the left join, now understanding the other join, right outer join is very simple. So first of all, try to understand this one. We matched records and also not matched records from the left table are also coming in the output. So that is what you can observe from this table actually. Okay. Hi. So now let us see other outer join, that is right outer join. So if you already done the left outer join, then understanding this one is nothing. Okay, you can guess what is this right outer join. So that is what's very simple. So now you want to include the right side table data which are not matched actually. Okay, not only the matched rows, not matched rows from the right table actually. That is what second table you want to display in the output. So that is what, as usually, let us take the same example here, student table and course table. And here the syntax is same. What is that one here? Right join actually. Now this is as usually condition, but we are not going to have where clause. That is important actually. That condition, when you are putting the any outer join, that condition after putting the join, immediately we are combining with the on actually. On this condition, put this right join actually. So what is going to happen now? Right side table, second table, whatever you have, that table entire data you want to maintain in the output. That means not only the matched data, this is what common data. Common data is nothing but matched actually. And this is not matched, this part, this is not matched. This also we need in the output. So this is what we written. So now let us try to write down the same query. We need all the courses in the output along with each student what course they taken. So as usually, let us try to write down select star. We are displaying all the data from which tables. That is what student. This is what actually right join. Simply in these places you have to substitute the things. Right join. Then other table is course. Let us take here course. Then condition we have to put, right? That is what on. On which column you want to put a condition? Here CID student table. Here CID course table. So that is what student dot CID equal to course dot CID. So now this is what happening. All matched records, this condition matched, this condition satisfied records are coming this one, and not matched are also coming because of this right join. So that is what output you can observe here. So you can see all the records from the course table we have, and not only those which are not matched. D and E, no student taken actually. Course D and E, nobody taken. But still those are there in the output because that is the second relation actually, second table, because right join means right table data entire thing will exist. Automatically here we are going to have null values. in all these positions. So this is what, after understanding left outer join, understanding right outer join is simple. So here, common data, matched data, not only that, not matched data from the second table, right table, we want to put in the output. Okay. Right. So now let us see the other outer join, that is full outer join. So now you can guess actually what is this one. We already seen left join, left outer join, right outer join. Now if you see the full outer join, so it is nothing actually. Of course, matched records and unmatched records from both left and right tables actually. So there is no big deal for understanding this one. So if you understand left and right outer joins, this is full outer join, meaning is that not only matched, unmatched records from the both the tables you are going to put in the output. So that is what same tables if you take, then this is the syntax actually. So in place of left or right outer join, we are putting the full outer join and we are putting a condition here. Then what is happening? You can see now. So this is matched part. So matched part anyhow it is coming basing on this condition. Whoever satisfying this condition, all of them is coming. Not only that, from the table 1, not matched records, and from the table 2, not matched records are also coming in the output actually. So for example, on this only same thing, if you write down what is going to happen, select star from, so the left table is student, and we have to put full outer join. So let us put that keyword full outer join. So let us continue here. Then right side table is what actually course. Then put a condition. What is the main condition here? So student.cid, it is equal to course.cid. So concept is same. If you understand one thing, all those things are similarly only. So now what is happening? Matched records coming. That is what here. So if you see the output actually, so here CID, here CID, here same, 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 same. So these 4 records are matched. Okay, fine. These 2 records, not matched records from the student table. That is what 5 and 6 not there. So those are came here in the output. Correspondingly, in the same rows from the course table, you have null values. That is also important observation. After that, if you take the right side table, for the right side table, these 2 records don't have any match. So those you are maintaining here. And correspondingly for the left table rows, you are going to have null values. So this is what very, very important thing. So in the full outer join, it is very, so don't think that not matched records of second table coming in this part. This is wrong assumption. Many people confuse with this only. So left side table not matched records coming, and corresponding rows from the right side table have a null values. Similarly, for the right table, not matched data is coming. Correspondingly, for the left rows and for the left side, going to have null value. So this is what actually full outer join. So this is what overall outer join actually. So outer join is nothing but matched records, not matched you are considering as a outer. That is why inner join also, if you observe in the inner join, only condition satisfied records you are getting in the output. That is why it is inner, condition is satisfied. But in case of outer, of course matched records and also not matched records. Out of the condition records are also coming in the output. Okay. Hi. So now let us try to write down for this query what is the answer actually? So what he is asking, list all clerks of department number 20 actually. So that means job must be clerk and department must be 20. And observe that both must satisfy actually. So that is what, first of all, select, and you need, he didn't mention which columns required. So let us display all the columns, select star, and from which table actually? So from EMP table, so from EMP. So this is what important thing, right? Where, so job must be clerk. So that is what job is equal to clerk. So that is clerk. And very importantly, department is 20 actually. So that means relation between these two conditions. So let us take first of all department number is 20. And these two conditions, anyone or both must be satisfied, both must satisfy. So that is why and operator you must take. So in the department number 20, whoever clerks are there, those details you are trying to display from the EMP table. So that is what simply you can write down the query for this. Okay. Now let us go for the next one. So here in this you see list the details of the employees in the ascending order of department number and descending order of job actually. So actually in the order by clause, you are going to use two columns. That is department number 1 and job is another one. And both is not in the same order actually. One is in the ascending order, another is in the descending order. And you don't have any constraint. You don't need to filter any row actually. So that is what first thing you must observe. So select. So you are going to display every information. So that is by star. And of course, from table is EMP. So the very important thing is here order by class. So that is what let us take order by. So in this order by clause, he mentioned first ascending order of DEPT numbers. So that is what department number you must display in the ascending order. So that is what DEPT number in the ascending order. That is what ASC is the keyword. And the descending order of jobs. So that is what job is the descending order. So let us take job in the DESC. So what is going to happen? Ascending order in the department number. So let us see some output actually, some outputs. Okay. So we will see only DEPT number and job actually. Automatically remaining things are same actually. Or let us take EMP number also. So for example, DEPT number first ascending order. So DEPT number, this is the one number and this is 1 and this is 1. So 3 tens are there, DEPT numbers. In these 3 tens, you can see here in the descending order actually. Job must be in the descending order. So this is one manager, this is president, and this is clerk. In these 3, if you take in the descending order, so that means president is the highest one. So that is what president. So that means what is its EMP number? 7839. And then manager. So manager EMP number is 7782. Then we have a clerk. So clerk means 7934. Got the point or not? And next you are going to have 20. So 20 is in the next part is 20 actually. So you can take here one row 20. So in the 20 descending order of job actually. So let us take another color for easily differentiate. So 20 is this one, and we have more rows, right? Total 6 rows we have, total 5 rows we have 20. So here we have a clerk, here we have a manager, and here we have analyst, and here we have a clerk, and here we have an analyst. So you can see out of all, in the descending order, which one you will get first? Actually, manager. Okay, so that is what manager. Okay, so manager 7566 actually. And after the manager, you have clerk. This is the one clerk, and here also clerk is there. Is it or not? So that means, so 20 clerk, EMP number is 7369, and another one 20 clerk. So what here we are trying to tell is, so let us take this clerk also 7876, and then you can go for the analyst actually. Here analyst, here analyst. So that is what 2020. So analyst. So that is first analyst is 7788, and here also analyst, that is 7902. So similarly 36 records you are going to have. Observe that what you mentioned first, that you have first in the ascending order, that is what DEPT number first in the ascending order, 10, 20, 30 like that. And then in that 10, all elements, job data you are displaying in the descending order. That is what you can observe. So this is in a ascending order, this is in a descending order, you can observe that. So in this order, first it will ascending order of this DAPT number. In that data, next job part, it is going to put in a descending order. So that way it is going to display the output actually. That you have to observe very clearly. Okay. So this is what the query, first of all, this is the query for this given question actually. Now let us go for the next. So here you can see display all the unique job groups in the descending order actually. Is it? So now you can see how you can answer this one. So this is a simple one only. So how you are going to display actually. So you can see here, you have to display unique jobs. That means distinct jobs. So select, you need distinct jobs. That is what keyword we are going to use is distinct. And what you need actually, on which column you want to apply distinct? Job actually. And this data is available from EMP table. Okay. And he told that descending order actually. That is what order by clause, if you take order by job in a descending order. So that is what keyword is DESC. So if you observe what is the output actually. Okay. So what is the output you are going to have here? So let us just try to observe. So here job you are going to display distinct actually. So clerk is one thing, salesman is one job, manager is another job, analyst is one job, president is one job. These are the distinct jobs. Out of all, descending order we need. So if you observe, salesman is the highest one in the descending order, salesman. And after that, next if you take president actually, so president, and then we are going to have manager, and then we have a clerk, job type, and then we are going to have analyst. So these are the 5 groups you are going to have. First of all, unique groups, and in each job category you have different employees actually. So this is what he is asking, right? So for that, this is the query. Okay. Hi. So now let us see this query. So what he is asking accordingly, let us try to write down the query actually. So as usually he is asking employee number. So some column, name, direct column, e-name, employee name, and salary. But here if you see daily salary he is asking of all employees in the ascending order of annual salary actually. So EMP number we need, e-name we need, salary we need. Other than these three columns, daily salary and annual salary and ascending order of annual salary actually. So that is what actually we need actually. So how you will get daily salary? So this is for 30 days, right? That means for 1 month, for example. Of course, maybe 31 days month is there, 28 days month is there. But when you go for the daily salary, so on an average, we will go for 30, right? Most of the times. So that is why salary must be divided by 30. So that is daily salary you are getting. And what about annual salary? This is 1 month salary. So you just multiply that with salary actually. Every employee salary you just multiply with 12. So that is going to become annual salary. Is it? So let us apply same thing in the select clause actually. So that is what you can see. Select first EMP name, employee number, EMP number, then E name, and then we have salary. So that is what salary. Next, daily salary. So salary we are going to divide it by 30 actually. So that let us take as alias name. So daily salary. So daily salary. And after that, what we need actually annual salary also let us try to display. So how you will get annual salary? Just multiply every employee monthly salary with 12. That is what we discussed. So that is going to become annual salary. So let us take alias name. So that is annual salary. Okay. So this whole information you are going to get from EMP table. And he is asking actually all employees, you no need to filter any row actually, is it or not? So directly we need actually order by class. So that is what order by. Then what you have to write down. So this as per this you want to display actually in the ascending order. So increasing order you have to display. So that means you can use alias name in the order by class. So this alias name you are going to use. So that is annual sal. So that whoever have the highest, of course, whoever have monthly salary highest. So that is what king. He is the last row. His data is in the last row actually. And the minimum salary is what actually 800. So 800 into 12. So whatever we are going to get. So that is the first row actually. This is the first row. So this is the first row. And who is the next one? So here you can see 950 is there next minimum. So he is the second row. So like that you are going to have the data actually. Is it? So who is the next one? Let us identify next one. So he is the next one. And also 1252 times is there. So 3 and 4 rows actually. So like this you can sort them actually. So in this way we are going to have the data. Okay. So first of all try to understand this is what the query for the given statement. So we need mainly first 3 columns are straightforward columns from the table. One is daily salary, another one is annual salary. Okay. Hi. So now let us see this query. So here the given statement is list the employee number, name, salary. So this is straightforward and experience of all employees actually working for the manager 7698. So first of all under 7698 who are working? So let us observe under MGR you must have employee number 7698. So this employee working under 7698 and ward is also working under 7698 and here you can see Salesman is also, Turner is also working under 7698, and James is also working under 7698, and here Martin is also working under 7698. So total 5 persons are working actually under manager 7698. Who is 7698? First of all, he is the Blake. Okay, so let it be. Okay, that is not a problem actually. You just filter first of all whose MGR is 7698. So only for those rows, this experience we have to calculate actually. So that is what we have to do. So first of all, let us take the select clause. So select. So we need employee number. So simple EMP number. And then we need name. So E name. And he is asking salary. So normal salary, sal. And very importantly, experience. So this experience part, let us try to write down in the next line for better understanding. So I'm going to write down here. You can see. So experience, how you will calculate. So date of join, date of hire date. So that is what hire date you have to consider. That is when he joined you have. And the current date actually. Right now, what is the year? What is the month? So that you are going to get with the sys date. Got the point? So you have to subtract this hire date because this is the, so for example, if you take the two numbers 10 and 5, if anybody asks what is the difference between these two, big number is 10 minus 5, that is what 5. Similarly, this is what the highest date actually, current date. Then this is the old date, means this is the less than this one actually, sys date. Higher date is less than sys date. So higher date you have to subtract from the sys date actually. So that is what we are going to do. Sys date. So it is giving current date, and higher date we have already. So from the table higher date. So difference between these two, how you are calculating is months between underscore between. Got the point? So months between sys date comma higher dates. In these two dates, how many months are there between? It is going to calculate. So you need to tell in terms of, for example, years. So you just divide by 12 actually. So now you are going to have this experience in terms of years. So that we are going to take as alias name EXP experience. For this entire line, this is what the alias name. Then you are going to have a from class. Okay. So that is what from EMP. And first of all, you have to see, this is just selecting the data, but you have to filter the rows, right? That is where we need the where class. Where class. So where, what you have to filter, manager must be 7698. Under this manager, all employees experience you need to display. So that is what actually where MGR is equal to 7698. So that is what the query for this given statement. So you can extend actually, suppose you want to display the data in the ascending order of their experience. So for example, ascending order of experience actually. Then what you will do? So you are going to have a order by class. So where you have order by experience, right? So that is what alias name you can use in the order by class. So whoever have the least experience from there, so here automatically it is working in a ascending order, that we know already. We already discussed it actually. Okay. So in that way, who have the less experience, so less experience to highest experience person's data, it is going to display actually. So 5 records it is going to display as per their experience in the ascending order. Okay. Hi. So now let us say this statement. So list the employees who are either clerk or analyst actually in the descending order of their names. So how you can display this one? This is straightforward, right? So simple, select star. So because he didn't mention any specific column, so let us display every column actually from the table. And from EMP table. So first of all, we need to filter the rows, right? Either clerk or analyst. So where job type actually. So where job is equal to either clerk or actually any or analyst. So that is what R job equal to analyst. Job equal to analyst. Okay, and he is asking that descending order of their names actually. So that is why order by uh, order by names. So that means order by e names, but he need in the descending order. So that means the DESC keyword you must use, so that so alphabetically in the descending order, their list is going to display who are either clerk or analyst actually. So here, this query you can write in another way also. Is it or not? So everything is same except this line. So this line, let us see here. So that line only you are going to just writing in another way, where, so where condition, where, so job, we already discussed the keyword in operator. So that means you can mention specific set of things in this in, and the relation between these elements, the relation among the elements inside in is or operator actually. So that is, we need either clerk or analyst. So anyone actually, anyone if it is matching, then it is going to say, it is going to return that particular record actually, that row. So that is what this meaning and this meaning, internal implementation of in operator is this only. Try to understand. So that is why you see why these two records they are discussing is this where clause 1, this where clause 2. Which one is best one? You written like this, internally it need to convert and execute actually, and filter or execute. Here direct execution only, because into conversion not required. So here internal conversion is going to happen to this part, and then you are going to execute. But in this directly execution. So that is why this is the better one than this actually. But this is user friendly. This is user friendly when you have more list. Is it or not? When you have more list in internally, so every time you don't need to write down its column name and with what you want to match and R keyword. Simply in and with what you want to match, all the things, elements you just write down as a set here. Then internally it will convert like this. So that is why this is the better one for the user actually. Second one is the user friendly notation, and this is optimal for the system actually. First one. Okay. Now let us see similarly another statement. So here if you see, list the employees who are working for the department, either 10 or 20. So this without saying you can write down actually. Here it is also straightforward, right? Like previous one. So that is what simply you can write down. Select star, he didn't mention any specific column. So star from EMP table. So you need to filter, right? So where so department number, DEPT number. So here you can use keyword again in, right? In either 10 or 20. But the pointer. So that's it. So hope this part is clear. So here you can simply mention the in operator, so that internally automatically it is applying or operator among all the elements you are providing in actual. So that means DEPT number 10, this is equivalent to, as we written in the previous statement query, DEPT number 10 or DEPT number 20. DEPT number 20 actually. Okay. Hi. So now let us see a query for this statement actually. So here he is asking that who are joined in the year 1993 actually. Is it? So that is what actually. So in the year 93, who joined? You can observe here. One is Smith joined in the 1993. And here you can see Clark is also joined in 1993. And any other? So we have only two employees who joined in this 1993. So what we can write down here? So one thing is, so that is what actually. So one way you can write down like this, select. So he is asking just employees details. So let us display everything actually. Let us select the star from table is EMP. Okay. Then, so in the condition, what we have to write down, that is what the filtering part, right? So you are applying the condition on the hire date. So let us take the hire date. Okay. Then, so this hire date must be in 1993. So that means 1st Jan 893 to 31st December 93. Is it or not? So who joined in this range? All employees we need actually. So hire date is between, you can use, right? The operator between you can use. Is it or not? So between. So between. So here you can see 1993. So the month is first month, January. And so this is the month and this is the date, right? First. So first month, first date actually. Okay. 2. So here we must need and means it is between operator, right? So we must have a and operator. And what we must have here? 1993 only, but it is the 12th month, date is 31st. So whoever is there in this range for the hire date, those employees you are trying to display actually. So that means only 2 employees it is going to return. So that is what you can see. First year, format is year, month and date actually. So that is why in that format only we are trying to compare actually. Is it? So this is one way of writing actually. So what we can write down in another way. So that is what second one. So only where clause I am just writing because remaining part is same. So where, so you can do like this actually. To care, hire date we are taking. Okay, fine. So hire date, which part we need? Only year part we need. So that is what we are going to take year part. Y. So that means full year we are taking. That means like 1993. So 1993. So year format is 4 digits, right? So that is what. So that you are taking in a char form. That you are comparing with equal to what actually 1993. So this is one way of writing the same thing. Is it or not? So here we are using between operator. Here we are extracting only year from the hire date. That we are taking into char form. That we are comparing with what required year actually. So in this position, you just replace, if you need 1993, you can place it. If you need 2000 year, so you just replace this position. This part is same. So similarly in this, if you need 2000, here 2000, here 2000, you must replace actually. So this is one way, this is two ways you can write down the query for this given statement actually. Okay. Hi. So this statement, if you observe, list the employees who are joined in this month, in the month August 1998 actually. So if you observe, this is similar to previous one with a little change actually. Okay. So earlier in the last question, you just have a year actually. Now here month is also added. So how you can retrieve the data in this specific month of this year. So that is what. So this also you can write down in the two ways as we written previous query. So that is select. Here also he is asking all details of the employee because he didn't mention any specific column. So that is why select the star from EMP. So table name is EMP, where, so condition here we have to write down. So what is the condition here we are writing? One thing is by using between and operator. So that is what where hire date, so joining date between. So operator is between, we are using between. So similarly, see, actually August month is a what actually 01 August 1998 to, so August month is 31 days. So 31st August 1998. So whoever joined in this range, we need those employees actually. So that means between we are applying upon this. So that is what 1998. Okay. And month is what actually August, that is in digits 08 month. And from first to two, that means and operator here we have to use between and combination actually. Then 1998 August 31st actually. So whoever is there in this range, in this hire date part, those employees we are trying to display. So who is there actually in this range? You can see 1998. So he is joined in 1998 August actually. So Alan is one record. So is there anybody? He is also 1998, but he is a 12th month actually. That means it is a December. So only one employee is there. So that means it is returning one record. So writing this is very important, first of all. Okay. What is another way, as we've seen already? So or same thing. So we are going to take only where clause, where, because remaining part is same. So where, keyword where. Here also similarly, to care function we are going to use. Then in the hire date, which part you need to extract actually? Month and year only you have to extract from the whole hire date. So that is what we are going to extract the month. So in 3 letters of the starting of the month, and then year actually. So y, complete year. So this must be equal to, so August 1998 actually. So in this we can this you can replace with any other required month and year actually. Okay, so that is why this is better sometimes if you want to change frequently the month and year, because here total 4 places you have to change accordingly, but here only at one place if you change, then as per the requirement it is giving the output actually. Okay, so that is what actually in the previous query similar kind of thing we've seen only with a year actually. Here we've seen month and year both together. Okay.
Hi. Now let us try to understand more about this select statement actually. So as we are saying that we are always retrieving the data from the table. So in our course, especially throughout this SQL part in this chapter, we are going to use the one table. So this is what the table we are going to use. So this table is more than enough that for any scenario discussion. Okay, so that is what, let us just try to understand. Let us make this table well familiar so that whenever we are discussing, things are going to become very easy. Okay, so here you see table name is EMP. It's nothing but employee table actually. And in this table total we have 8 columns. That is nothing but 8 attributes are there. And in this EMP number is actually a unique, you can say this is a primary key. Okay, as we discussed earlier. So this is a primary key. Every value here it is unique, and you don't have null values. That is what primary key, right? And then employee name you have,
and what kind of job he is. So that is what clerk, salesman, manager, analyst, president. These are the different categories actually, job categories. And MGR is nothing but manager. So for the Smith, for example, for the Smith, who is the manager? 7902. So who is the 7902? So here 7902 is the Ford. Ford is the manager for Smith actually. So that is what, for every person, one manager will be there except president. So president is the top level person, right? So he don't have any manager actually. So that is why whenever any column, any cell is empty, that is nothing but you have a null value, because this is also matter very important actually, that also we will see. Okay, so empty cell meaning is null. Okay, so that we will handle separately, that discussion also there. Okay, so this is what MGR is nothing but manager. So hire date when he joined, and the salary, what is this salary, this is in terms of dollars assume. And this is the commission, for each employee you have commission, and here more empty cells are there, that is nothing but null actually. Okay, this is DEPT number. So DEPT number means a department, so under which department these employees are working. So actually we have another table department, that also we will show you whenever required. So time being, just department number here we are displaying. So that is another table actually, as we seen in the normalization, when we split for the different for handling different anomalies. Department is one separate table and EMP is another table. So department is actually a parent table and here employee is a child table, because this department number is the primary key in the department table. Okay, so that is the reason here, this is a primary key we can say, sorry, this is a foreign key actually we can say. So its originality is there in some other table. Okay, so this is what the table, first of all, we are going to use throughout our SQL part. Okay, now let us see how to retrieve the data from the tables in a simple manner. So but this is because we are writing the first query now. So let us see in a simple manner. So if you see the syntax of a select statement, so select is a keyword you must write down. So it need not be always capital letters, anything is fine, small letter or capital letter, that is fine. And then which columns you want. So which column you need, those column names you just mention separated by a comma actually. After mentioning the all columns, then you write down the from, that is also mandatory keyword. And these columns, especially these columns, from which table that we are mentioning. So they're very simple actually. So that is what, if you see, then this is what the first thing. Now here we told every column you have to mention separately. But sometimes I need all the columns actually, because sometimes some table may have more than 10 columns or 20 columns. Sometimes maybe 15, more than 50 columns will be there. So writing every column separately is not recommended thing. And you need all the columns at a time. At that time, simply use the star in this position, in the select clause. That is what. So if you use select star from EMP, then entire data is going to come as a output. What is that? This one that you can see. So this is the output you got for this command actually. Okay, so whenever you need, you don't want any filters in the columns, then you use the star. If you need only specific columns, then this is the syntax as we mentioned. So you can see I need only MP number, ename and department number. And from which table? These column names must present in the table actually, whatever you are mentioning. Okay, so that is what actually here you can see. So output is EMP number, ename, DUPT number. So in this way, whatever columns you need that you mention in the select clause, only those columns are going to come actually. And one more thing is, EMP number is the first column, after that ename and then department number. But you want to change the orders actually, order of display. So for example, I need first ename. So then simply you write down select. First I need ename. So give ename, and then I need a department number, and then I need EMP number. So you just give. So here, whatever order you are mentioning, that is nowhere related to the order you have in the original table. This is the original table. Okay, so in which order you want to display the columns, in that order you can mention actually in the select clause. And of course, after that from table name. So that is EMP and terminate with a colon. So this is what actually the first thing, in what way you want to display the data. Okay, so now here let us see one simple thing. So let us write down the some queries actually here. I need commission and salary. So what we can write down? So we need only commission and salary of every employee. So every employee means let us display his number and salary and commission. So that is what you can see. Select. So whose salary? That is why EMP number. Let us display. So EMP number, and we need salary, and we need commission. So that's it, right? And from which table these columns are there? So that is what from always. So we are retrieving these columns from EMP table. So that's it. So very easily you can filter the columns actually. Unnecessary columns you can skip, and the necessary columns only you mention in the select clause. So let us just display every employee name and his job. What under which category he is working. So that is what in that case what we will write down. So select. So ename, we need only ename and his job. So that is what job. So these two columns from which table actually? So from EMP table. So like this, you can mention only one column you can mention. So that is what I need only, for example, I need only MGR. So see, so here in the output, how many rows it is going to display? You just count first of all how many rows are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 rows are going to get actually output here. And here also output is 14 rows. Always remember that this is also important for us. 14 rows you are going to have in this table, and 8 columns we are going to have. That is what. Okay. So EMP number, ename, job, MGR, hire date, sal, commission, department number. Total 8 columns, 14 rows we have. This is also required. Sometimes we need actually. So I want to just display. See now the magic. If you see, I want to just display commission part. So that means select only commission. Why I am writing this part? Let us see. From EMP table. So what is going to happen is output, how many lines it is going to display actually. So though you have null here, everything it is going to display. So that means total 14 rows it is going to display. As it is, this entire column data is going to display actually. Okay, there is no filter actually. Null values also as with the empty cell, it is going to display actually. Okay, so this is what a simple thing, how we are going to have a select statement. And it's a syntax. If you need all the columns, then you put a star in the select clause so that all columns are going to come in the output. Or if you need a specific columns, at least one column must be there. At least one attribute, and more than that, any number of attributes which those must exist in the corresponding table, which you are mentioning in the from clause actually. Okay, so this is the very basic thing we must understand, because select statement we are going to use
in the 80% of the course in the SQL chapter. Okay. Hi. So now let us see the another chapter, that is relational algebra and calculus. Okay. So informally, first of all, what is this meaning actually? So we've seen actually SQL and also database, some part we've seen already. So if you see the SQL part, especially how to retrieve the data by using query we written actually in the SQL. So now those queries we are going to see mathematically actually, how you can represent them mathematically. So that is what actually relational algebra and calculus, we can say very informally for better understanding. So now let us see its formal definition. So relational algebra produce procedural query language, which takes a relation as a input and generates the relation as a output. Okay, so that is what it is doing. So simply we will understand in the discussion. And relational algebra mainly provides theoretical foundation. So it is just theoretical. Implementation is not possible directly. So on the paper, you can represent any query by using this relational algebra. So that is on the database and SQL. Okay. So the mainly, what are all operators we are going to see in the coming lectures in this chapter? So that is what actually, first of all, under relational algebra, first of all, let us complete this and then we will go for the relational calculus. So in the relational algebra, we are going to see first projection. So projection is nothing but we will represent with pi, and next selection we will represent with row, and sigma we will represent with sigma. Set manipulation operators, union, intersection, and difference. Okay. And after that, we are going to see the Cartesian product. Then we will see joins, and then we will see rename part also. This is what the row, and we will see the division part. So mathematically, any query we written in SQL, the same thing, how you can write mathematically by using all these things we are going to observe actually. So this is also somewhat important. Mathematically, you must understand if you understand SQL part. So the only thing is, if you know the meanings of all these things, any query you can write down definitely in relational algebra. So in the coming lectures, let us see all these operators one by one and let us explore more. Okay. Hi. So now let us see the first two operators, that is selection and projection. Okay. So let us try to understand these two, because these two are the very important in relational algebra. Whatever query we are writing, any one of them definitely will be there. Especially selection part, definitely projection part definitely going to be there in any query in relational algebra. Okay. So now for better understanding, what we are doing is we are going to take a one simple relation, that is employee relation, which have three attributes: EMP number, e-name, salary. So let it be. So now let us try to understand first of all, what is projection. Okay. So projection actually simply it is for filtering the columns actually. Which particular column you need from that relation you want to display, which columns you want to display. So those columns you can those columns only you can mention by using this projection actually. And what is the symbol we are using for that is the pi. So by using pi, you can select the attributes from the relation actually. So how it will be syntax if you see. So pi, in the suffix, we are going to mention what are all columns required. We are going to mention actually by separating comma. And these columns from which relation, that we are going to mention like this. So all the columns what you mention here definitely going to exist in this relation. If you mention the column which is not there here, that is invalid RA actually. So in this relation, whichever columns you want to display, those you are going to mention here in the suffix of pi actually. So that is projection. So simply try to understand it is for filtering the columns actually. Like a select clause in the in the SQL part actually. Now let us try to see the selection part also. Then we will see together some examples. So here selection, if you see, just quite opposite to that. It is for selecting the rows actually. So if you want to select the rows in the SQL, what we are using where clause. Where clause is for filtering the rows and select clause is for filtering the columns. That's it, right? So this is like a select statement. This is like a select statement in SQL. Okay. And this is like a where clause in SQL. That's it. So just remember in that way, then things are going to become very easy. Okay, selection, how you will represent actually by using this sigma. So if you see it's a syntax also, it is similar to this one, but if you see sigma and in the suffix we are going to put a condition because in the where clause you will write a condition, right? Basing on the condition, whoever satisfying that condition, only those rows you are returning. Same way, where you are writing this condition, here actually, suffix of this sigma symbol. And this condition upon which relation that you are mentioning here. That's it. So very simple, these two actually. In case of pi, that means in case of projection, we will use the set of attributes which you want to display. And in case of the selection, we will put the condition accordingly where clause and select clause. So in the select clause, we will write the attributes, right? And in the where clause, we will put the condition. So similarly, actually. So now let us, by using these two symbols, let us practice few questions and let us see actually. So here if you see, find the names of all employees. So here you can see in the employee table, we have a column E name. So we want to select all the employee names from this table actually. So see, he is asking attributes actually. That means you must use the projection symbol. So that is what we are going to take, projection. And which attributes you want to display? Name actually, E name. So let us mention E name. Yeah. So this E name from which relation? That is what employee relation. So let us take that here. Employee. This is very basic and very frequently in many places. In the throughout this chapter, we are going to use this kind of notations actually. So try to understand simple manner here only. So what are all columns you want to display that we mentioned here? From which table that we mentioned here? So this is what find our names of all employees. So this is equal to in SQL is what actually select only name from employee table. So from employee. That's it, right? So this is what the equivalent SQL query. Okay. Now let us come here actually. Okay. Now let us take another example for this symbol actually, selection. Find employees whose salary greater than 5,000. So here we have a salary column. So salary must be greater than 5,000. That is what the condition you should put. So because you have a condition, we must take the sigma symbol, right? Selection we have to do. That is what you can see. Sigma. What is the condition? Salary must be greater than 5,000. And this condition, where this condition actually on the relation employee. So let us take that employee. So this is what actually find the employees whose salary greater than 5,000. So, but what is okay? This is fine. But what is the problem with this? This selection symbol. That is what the sigma symbol is. It is not going to display the data. It is just filtering the rows actually, basing on the condition. Whoever satisfy this condition, only that rows it is selected. But if you want to show the output, you have to do like this actually. That is what, find the names of employees whose salary greater than 5,000 together actually. So whatever rows here it is selected, in that ename you have to display actually. So first of all, this you have to satisfy, right? So select the rows where salary is greater than 5,000. That means first you have to do this one. So that is salary greater than 5,000 from which table? Employee. Now if you see this part, if you see this part, what is happening actually? This entire is one relation now, because what records we have here? The records which are satisfying this condition. For those records, we need e-name actually, employee name. That is what asking. So here you apply projection. So that is what. Upon the relation of this part, upon the result of this part, you are selecting only e-name. Now you can display the names actually, e-names. But here the data is not displaying, just selected the as per the condition actually. But now whatever records are selected here, though from those records you are displaying the e-name only. That is what we need finally. Whose salary is greater than 5,000? Those employees' names we need. That is what in this query it is displaying. So this is what one simple thing actually. Okay. So with this understanding, let us see some insights actually. So we have a commutative rule, is it or not? So commutative meaning is what? AB equal to BA. If both of them is same, then the operator, whatever we are using, that is commutative. So similarly, so the same query we are going to take here, find the names of employees whose salary greater than 5,000. So that is what we taken here. Find the names of the employees whose salary greater than 5,000. So what we written first of all, we selected those rows which are satisfying this condition. So that is what we written first, salary greater than 5,000, okay, from the employee table. Now this result is one relation now. This result is one relation. So that result, in that result, we need only e-names. That is what projection we are applying. So this is what actually, of course, we done here. Now, can I do first selection? That means, can I do first projection after that selection? Here, what happened is, this is the inner query. So this inner query first you have to execute. Upon that result, you are applying the projection. But now what we are doing is, first we are doing this one. So that meaning is by ename of employee. So first you are selecting only e-names. Upon this result, you apply the condition actually. Tell me, so salary greater than 5,000. Can I write like this? See, this result is actually one relation. That relation contains only e-name column. You don't have salary column in the result actually. So how you will apply this condition? To apply this condition in the relation, you must have this attribute. But in the result of this inner query, you don't have salary attribute. So that is why both of them is not same. This is not meaningful actually. That is why swapping those two operations is not possible. First, you apply the condition always, so that all columns automatically will return. Upon those attributes, now you go for the selection. So always the better is inner part is actually a selection part. That means rows you are filtering, and after that filter the columns. That is what projection. So this is the best method always actually. Okay. So this is one thing you must remember. And in this way, we can write down by using projection or by using selection and together. Okay. And be careful while you are writing like this. So always recommended thing is first you filter the rows. Filter the rows first and then filter the columns. That's it, right? So that filtering columns is simple if you filter the rows, because anyhow all attributes will be there inner. Upon those attributes, whatever attributes required, that only you take it. So this is the best example to understand that it is not commutative. If you swap these operators, result is not same. And that too, this is invalid actually, this part. Okay, so this is the selection and projection operators. Okay. Hi. So now let us see next set of operators, that is set manipulation operators actually. So this is also very important. In this set manipulation operators, we have union, intersection, and difference. So as name implies, it is going to work actually. Okay. So let us see all these things individually. First, let us try to understand that what are all the minimum things you must follow. So that is, whenever you have a two relations R and S, among between these R and S, if you are applying union, intersection, or difference, what you must ensure actually. So that is what you can see. R and S must have same quantity of attributes. For example, relation R is there. Okay, in the relation R, we have a attribute. For example, attribute 1 there, attribute 2 there, attribute 3 is there. And in the S also, that is what same quantity of attributes. That means between these two, if you are applying any of these three, that may be union, intersection, difference, you must have same number of attributes first of all. So that is what, for example, attribute 4, attribute 5, attribute 6. Okay. So these are the three attributes. So this is what first one is satisfied. Three attributes here, three attributes here. That is what we have to ensure. If at all both of them is not same, then these operators were not going to work actually. That is what. That is the first rule you must satisfy. And after that, very important thing is attribute domains must be compatible. What does it mean is, for example, attribute 1 is integer. Here also attribute 1 must be integer. Same domains actually, that is what corresponding attributes in the both the relations must be same domain. If it is char type, then this also must be char type. If it is float, this also must be float. That is what you have to ensure before applying these operators. So then only it is compatible. That is what meaning of compatible. Domains of corresponding attributes from the both the relations must be compatible. That means must be same, very simply. Okay. And the next point is duplicate tuples get automatically eliminated. See, sometimes whatever row here you have, maybe same row exists in S also. But in the result, only one row it will show you actually. So that is what relational algebra automatically eliminating the duplicates. So by default, they are eliminating, very important point. This you must keep in mind. So by default, eliminating duplicate values actually. Not only in these set manipulation operators, in any operator, that may be projection, selection, anywhere, duplicate values automatically it is eliminating actually. That is very important. Okay. So before applying union, intersection, difference, you must ensure these two especially. This is just what it is doing internally saying, but number of attributes in the both the relations and order of their domains also same in the both the relations. So if you manage these two, then you can apply in union, intersection, difference between these two relations actually. Okay. Hi. So these are the rules we already seen in the last lecture. So now let us try to explore each operator one by one. So the first one we are going to see is union operator. See, this is there is no big difference to mathematical union and this union. So concept is same actually. You are combining two sets. That's it simply. Okay. So, but what are those two sets we are combining is two relations data we are going to combine actually one after the other and by eliminating duplicate values. That is even mathematical definition of union is also same, right? In the two sets, it is going to combine. If at all any duplicate values are there, that is automatically deleted. So that is what you can see the definition. Union operation in the relational algebra is same as union operator in the set TD actually. That is what mathematically we have, right? So the only constraint is union of two relations, both the relations must have same set of attributes. This meaning is these 2 points actually. That is what you have to ensure. So let us work on the relations, how this union is working. Let us try to understand clearly. So for that, let us take some set of relations. That is depositor relation. We have two attributes, customer name and account number, and a borrower, customer name and loan number. And we have another relation, loan. Three attributes are there here. For more clarity, let us take some dummy data for these three relations actually. So the depositor, this is the 4 rows we are going to take. And for the borrower also, we are going to take 4 rows. And the loan, we taken this one, this data. Now what we will do is, union operator, how is working on these relations? So simple, let us have a simple query that find the names of the customers who have account means this one, or who have a loan, this one, or both actually. So you see here, some of the customers have both account and loan actually. For example, if you take a B, he have a loan, he have a account and he have loan also. Is it or not? Even C also. And some customers only have loan and some customers only have account and some customers only have loan. So how you will write down both together actually? He is asking either account or loan or both actually. So that means how we are going to write down. So first of all, select the names from the depositors. That is what, how you will select actually. So we are going to select, we are projection symbol we have to use. We need customer names. What is that column name? Customer name. So customer name. And these names from which relation? That is what depositor. Yes, fine. Okay. Then, so here, and then let us come to the borrower also. Here also we need names only, loan names. So loan, whoever taken the customer's loan, those customer names only required here. So that is what write down another query actually. That is also here customer name here, and this is from which table actually? This is from which relation? Borrower. So let us take that. Now this is one result and this is another result actually. These two results we have to combine. See, now try to understand that these 2 points actually, and this also you will observe. R and yes, for example, this is R and this is yes, must have the same quantity of attributes. What you are finally returning only customer name, one attribute, and here also only one attribute it is written. Yes, this is satisfying. And after that, second one is domains must be same. That is what domains must be compatible. So here the customer name is nothing but char only or string, and here also customer name is nothing but string. So that means both of them satisfying. So you just apply between these two results union operator. That is what union. So what is the result actually? If you see the output here, let us note down the output here. So what output we are going to get? So if you see the output, the customer name we are getting actually overallly. How and all? So from first of all, depositor A, customer, one of the customer name is A. Another customer name is B, another customer name is C and F. Now came to this part is over. Now you unions come to the second part, that is borrower. Here D, yes. See here, B already there. That is what it is eliminating duplicates actually. So B is not going to print again actually. And C is also there again, actually already in the result. And E is not there, that it is going to give actually finally. Okay, so I am writing E here. So that is what overall 6 records it is returning. So final result is 6 records. Just try to understand that how to apply union operator. So don't think that in the actual relations, you no need to have compatibility. He is asking the compatibility and quantity of attributes in the result actually. What you are mentioning finally on which you are applying the union operator, on that results, you have to cross check these 2 points. And of course, in the result, automatically eliminating the duplicate values. So in this way, union operator you can apply actually among the or between the 2 relations. Okay. Hi. So now let us see the next operator, that is intersection operator. Okay. So what is meaning of intersection? So this is also very simple. We already well familiar this one in mathematics, right? So intersection meaning is in the 2 sets, common elements it is going to return actually. So that is what even here also, it is used to select the common rows from the 2 tables actually. That is what from the 2 relations. Okay. So if you see the query, so for a better understanding of this one, find the names of the customers who have both account and loan. So who must have loan and account, both actually. So first of all, select the customer names from the depositor and select the customer names from the borrower. And then you apply intersection on both the results actually. So that is what you can see. First of all, select only names from the depositor table. So that is customer name from depositor relation. So it is going to return all these names. Same way, select customer names from the loan also, from the borrower table also, from the borrower table. That is what borrower. So what is going to happen? This is returning, if you observe, A, B, C, F. And this is returning D, B, C, E. Is it? Now, upon these 2 results, you have to apply intersection operator. Is it or not? So that is what you just apply intersection operator. So the result is the output, actual output is customer name. And what is getting the output? Common in both actually. B is there, customer B is there in both, customer C is there in both. Okay, so that is what. Even here also you can apply, understand that how many attributes here you have. Here also you must have same number of attributes. That is what quantity of attributes you must ensure. And at the same time, compatibility. If this is a character, this also must be the character. If this is integer, this must be the integer. That compatibility also you must ensure actually. Okay. So this is what actually from this is the result, and from this is the result. And if you apply the intersection, that is what we are getting common names from the both the sets. That is what B and C. So if you understand union, intersection is also same thing. So this is one relation. That is what he told right from the 2 tables or 2 relations. This result is one relation and this result is another relation. And both the results, you are applying the intersection, then we are getting the common rows from the both the relations. Okay. Hi. So now let us see the last set manipulation operator, that is difference. Okay, so this difference is actually whatever we seen in the set theory. So mathematically, whatever meaning is there, even here also same meaning like a union and intersection. So what does it mean? Let us try to understand simply. If you have a two relations R1 and R2, okay, you are going to select the all rows from the R1, but the rows which are not present in R2 actually. That is what meaning of difference in the set theory, right? So here also meaning is same. So to get the more clarity, let us just take a same set of tables and their data also like this. Now what we will do is, let us have a one simple query that find the names of the customers who have loan but not account. They must have loan, and that person should not have an account actually. So you see D, if you take D have a loan but don't have an account. So such a persons we need. And B have account loan as well as account also. So B should not come in the result. That is what only loan, not an account actually. So that is what, if you see, this is the account if you take, and this is the loan if you take. We need only loan persons. These persons required who are in common, that you have to skip. Only loan but not account. So common part you have to skip from the loan actually. So how and all you will write. So first so first query is what actually? So the first query must be loan one. So select the customer names from the borrower. So that is what we are selecting, only customer names. That is what customer names from the table borrower. Yes. So this is giving what actually, if you see, D, B, C, E is the output from this. Now select the depositors also. So select the only depositor names, that is customer name, but this time this is from depositor. So this is the depositor. Yes. So this is returning what actually you can observe. So that is A, B, C, and F. Now, actually we need only this is not the final result, right? We need the result only loan customer names, whoever have loan but not an account. That is why upon these two relations, you apply set difference operator minus. Then what is going to happen? So the result is if you apply minus in these two sets, D is there, but D is not there in this result. So D must be in the output. B here and here there. That is what common part you have to skip. B should not return. C also in both there, but E not there in this. So you return E. So that is what the actual output, if you see. So if you see the output, customer name, who is coming? D and E actually. And here also it must satisfy those rules actually. Number of attributes here and a number of order of the number of attributes in the projection here and here must be same, and their domains must be correspondingly same. Okay, and for example, so first of all, this is what the set difference. Now we are changing this query little actually. We are just writing oppositely. We need account persons but not loan. So what is going to happen, that you can see. The persons who have account but not loan actually. So this time, this is the account and this is the loan. Now this time we need these persons who have account, they should not have loan actually. So first you have to select the data from the account actually. Whatever required output, that from that relation you select the data first. So that must be the first one. So that is why pi of customer name and this data is from depositor actually. So this is from the depositor. So this is returning what actually? A, B, C, F. And then what else we need actually? Borrower customer names also required. So that is what here customer name. This is from borrower. So borrower. So here we are getting the result that is D, B, C, E. Now upon these two results, if you apply the difference operator minus, then what is going to happen? Result. So result is A is not there in this. Only A have only account, not loan. B have loan and account. C have loan and account. But F have account, but not loan. So that is what here output. So here the customer name, what it is returning actually? A and F. So A and F have low account, but not loan actually. So that is why this order is also matter actually. If you bring this first relation to here and here, output is going to change. So these things, see these things you are subtracting from this actually. So that is why relation R1, relation R2 or relation R2, R1, both the results are different. So it is commutative is not applicable on this set difference operator. On union is commutative. Intersection is also commutative, but the set difference is not commutative. What does it mean? R1 minus R2 is not equal to R2 minus R1. So order of operands is matter actually. Both results are not same actually. So this is what just try to understand that when you have to apply the difference, set difference operator. If you need only specific data from one relation, which is not going to have in another relation. So in such a way, you can apply in both actually. Okay. Hi. So now let us see the next operator, that is Cartesian product, that we will represent with this cross mark. Okay. So what is this one? This is very simple. What is the Cartesian product? You can see. So we are going to have two relations, R1 and R2. So we are just combining these actually with all possible combinations. Okay. So for example, in R1, if you have n rows are there, in R2, if you have m rows, then maximum you are going to get n into m. Because in the Cartesian product, duplicates automatically going to eliminate, right? If at all, if you have any duplicates, it will eliminate. But maximum n into m rows, it is going to generate actually. So that is what we are going to represent with cross mark. Okay. So if you see degree of R1 cross R2, that meaning is what actually? Degree of R1 plus degree of R2. This meaning is especially degree meaning is total number of columns. So for example, in R1, if you have 5 columns, in R2 if you have 3 columns. So these are the attributes actually. Then total columns, total attributes in the result is 8 attributes actually. So let us try to understand this Cartesian product with a simple example. So you can see here, this is the relation R1 and this is the relation R2. Attribute A, attribute B, under that this data we have. Now what we will do is we will perform R1 cross R2. So that means we performed a Cartesian product actually. So what is the output for this? For this, what is the output? First of all, degree of R1. What are all attributes in R1? That means left operand, how many attributes are there? Let us take all of them first. Followed by second operand, that means second relation, all attributes also you can write down like this. Then, now under these attributes, now A, B, C, D, total 4 attributes. That is what this meaning, second point meaning. Degree of R1 cross R2 is what actually? R1 attributes total plus R2 attributes total. That is what total number of columns actually. Now, This is the first row in R1. This you are combining with the first row in R2. That is what 1, A, and here 10x. That is what this one. Same way, this first row in R1 combining with the second row in R2 actually. So that is what here it is same 1, A, and here 20, Y. And one more row is there here that you are combining. So 1, A, here 30, Z. So this is what one row you have you combined with all other rows in R2 actually. Same way, second row also. So that is what 2b and here 10x. Then the next 2d, this you are combining with the second row here. That is what 20y. So this is simple discussion only, but this is very important or for further discussion actually. So 2b and here it is combining with this third row in R2. So that is 30z. So this is what first of all try to understand total how many records it is generated. So in R1 we have 2 rows. In R2 we have 3 rows. Total 6 rows it is generated. All possible combinations it is generated actually. So this is called Cartesian product. So that is very simple actually. And the number of attributes in the result is actually in the first relation number of attributes plus second relation number of attributes. That is what the result total number of attributes actually. And total number of records is actually in R1 how many records, in R2 how many records. Their product is actually the number of records in the result. Okay. So this is simple one only. Now let us see here one simple, let us try to answer this one. How you can use this Cartesian product for our discussion actually. So here you can see these three relations we are already seeing. Depositor relation is there, customer name, account number. Borrower is there, customer name, loan number. And loan is there, loan, branch, and how much amount. So assume their data we have here. So what we have to write down here is, he's asking that find all the customers who have a loan in the branch Hyderabad. So we need customer names actually, whoever have a loan in Hyderabad. So branch is available in this table in the relation loan, and customer name is available. Customer name is available in depositor actually. Okay. Customer name is available in borrower actually. Okay. So first what we are doing is, first of all, we have to join these two. Okay. So what we are doing is, first of all, you perform the Cartesian product, borrower Cartesian product with the loan relation. Then what is going to happen, as we seen in the earlier discussion, here 4 records are there, here 4 records are there, 4 into 4, 16 records are going to generate from this. Now what we need actually in this, whoever is in the Hyderabad, only those customer names only required. So here we are going to put a condition. First of all, condition is what actually loan number here loan number must be match. So that is what the first condition is, borrower dot loan number that must be equal to here loan dot loan number. Loan dot loan number. Okay. Then after that, not only this one, branch must be Hyderabad. So that is what AND operator, and branch equal to Hyderabad. So now what is going to happen? So you can see here what is happening here. 101 here, 101 here matched, and Hyderabad. So customer D is coming, and another one is 104 here and here also 104. Hyderabad is matched. Is it? So two records are matching, right? But this is not displaying the data. We need customer names, right? So what we are doing, this entire result take as a one relation. In this relation, what we need actually only customer name. So by using projection, let us select that one. So that is what borrower dot, what we need? Customer name. Okay. So borrower dot customer name, let us take here. So with this, what is happening actually? So whoever have a loan, the customers who have a loan in the branch Hyderabad, their names we are displaying here. So that is what you can see inner to outer, this action is performing. So here borrower into loan, this Cartesian product is going to happen. So that total 16 records it is generating. Out of these 16, wherever match is there, loan number in the borrower, loan number in the loan. Whoever have a match, only those records it is selecting. So 4 records it is selecting. In those 4 also, branch must be Hyderabad. So only 2 records are there with the branch Hyderabad. So what we are going to get output? So we are going to get the output, that is customer names. Whose customer names we are getting here? So here 101 loan number, whoever have 101 loan number is D, and here 104 also Hyderabad's 104 loan number is E. So it is finally returning 2 records actually. So this example, especially we are discussing how to use the Cartesian product sometimes. So because we are combining 2 tables right here. So at that time, based on our requirement, you can apply this Cartesian product actually. Okay, so of course we will see more examples on this Cartesian product also, and we will see which one is better, and later we are going to see joins also. So at that time, this much also not required. So let us see all those things. This is the first thing, that how to use the Cartesian product. Okay. Hi. So now let us see another operator, that is rename operator. So this rename operator is very simple. As name implies, you can guess for what purpose we are using this one. So that is what actually it is used to assign a new name to a relation actually. So sometimes it is required that we have to give the alias name. Simply we can say in the SQL terminology. So that means you are going to change the name for the existing one. So at that time, mathematically, this is what the symbol we are using actually, row you can call. So that is what the symbol we are going to use is row, we can pronounce it actually. And this renaming we can do in 2 ways actually. First of all, so that is first thing is we can change the name to the relation. So that means for a table you can change the name actually. So that is simple, how and all. So for example, if you have a student relation, student. So this is what the relation. So now we want to change this one to another name actually. So I want to change this name. So operator is row, and here I am going to mention new name. So simply syntax what we can write down for this especially. Okay, row, new name, here we are mentioning, and here we are mentioning old name. So that automatically this new name you are assigning to this old name relation actually. So this is one way of assigning. See, sometimes this may not be direct relation. Sometimes what is going to happen is you may have a expression. So you may have a big query and finally you are getting some result actually. For that result, you want to give the new name. So that is what again here you can use it, that new name actually. So in the previous discussion, we seen a different joins or selections, projection. By using all those things, you written some expression. That final expression result, whatever is there, that result you want to remember with a one name actually. So in that way, you can name it right in this way. so that this name for later purpose you can refer actually. So that is the reason sometimes it may be the expression, sometimes it may be the direct relation, for that you are giving the new name. So this is the first type, is actually you are giving the name to table or relation actually. And what is another one actually is changing name to the attribute. So you can give the alias name not only for the relations or the tables, you can give also the names for attributes actually, alias names. So for the attributes, how we can give actually. So similar fashion, for example, I have like this now. So same way, I have a student relation already. So I selected two attributes from this relation. So that is, one is name, another one is branch. So these are the existing two columns or two attributes in this table actually. Now I want to change the names, change the names for these two attributes actually. So at that time, what we are doing here, here we are going to give the new name. So for this name, I am giving the new name. And for this branch, I am giving the new branch. So that's it. So what is going to happen? Correspondingly, here how many names you given, that many names definitely exist here. So this is going to assign to this, and this is going to assign to this. So the first new name assigning to the first attribute in the projection, and the second new name assigning to the second attribute in the projection. So like that, as many, how many here you have, correspondingly that many new names are going to be there in the row actually. So in this way, simply you can give the names. In alias names is nothing but so in this way you can give the alias names or new names either for the relation or for the attributes actually. Okay. Hi. So now let us see very important concept in this algebra. And of course, this part we've seen already in the SQL also. So now notationally in the relational algebra, how we are using actually. So that is what join. So this join meaning and all these things we've seen already actually. So here also meaning is same. Join is a combination of Cartesian product. Of course, this is Cartesian product only, but we are going to have a one selection process. That means we are going to have a one condition actually. So we are going to have at least one condition. Basing on that one condition, in this Cartesian product, only some of the records which are satisfying this condition are going to return actually. So very simple discussion. So that is what actually, along with the Cartesian product, we are going to have a selection process that is nothing but a conditions actually. Okay. So in this join, as we've seen already, we have types of joins actually, many types are there. In that, the first one is conditional join and equi-join, natural join and outer join. In this outer, left outer join, right outer join and full outer join. So these are the different join operations we have. Let us try to understand all of them one by one individually. Okay. So joining is very important, as was discussed in the SQL part. In real time, if you are writing a query in select query, if you are writing, that is definitely more than one relation or table you have to use for retrieving the data. That means you are joining you are joining at least two or more than two tables actually. At that time, which join you are performing, what way if you perform, you can do the things optimally. So that understanding you must have actually. So that is what, after seeing all of them, we will get to know what is join and where we have to apply all these things. Okay. So let us see all these joins one by one in the coming lectures. Hi. So now let us see the first join, that is conditional join. So this is also called as a theta join. Okay. So what is this one? Let us try to understand in simple manner. So here you see theta join allows you to match two tables based on the condition actually. Okay, so this position, so here you can see the symbol. So this is the conditional join symbol, and here we are going to have a condition. So that is nothing but theta actually. So in this way also you can write down. So join and theta. So this position is actually a condition we are going to write down. So simple. Now, what are all conditions you can use? So comparison operators we have. So all comparison operators you can use in the condition actually. Sometimes maybe equal, sometimes maybe greater than or less than, greater than or equal to, less than or equal to, sometimes not. So all these kinds of comparison operators, whatever we have, we can include them in the condition actually. Okay. Of course, we are representing this with theta, that is fine. So now let us try to understand, let us try to develop the few queries based on this given statements actually. So for that, we are going to take a one table student and another table is course. Observe that student table have roll number, course ID, marks, and course table have course ID and a course name. So what is the query he is asking? So what we need actually, display the roll number and course name of each student. So student number 1 taken which course, student 2 taken which course, those names actually required. So observe that first of all these two relations we have to combine them. So when you are combining them, which attribute you have to use actually, course ID is required. So basing on that, we are going for the combining actually. So that is what, how and all, let us see. So first table is student and another relation is course. Okay. Where we write the condition, in this position, we will write the condition. It is not a Cartesian product actually. That is what you have to understand. Okay. Basing on this condition, without Cartesian product itself, it will return the result actually. So what is that condition? In the student table, CID, and in the course table, CID must match actually. So that is what student dot CID. So in the student table, CID must be equal to course dot CID actually. Only such a records you are selecting. Now this is the result. So from this result, what we need actually, roll number from the student table and course name from the course table actually. So that is what here we are writing. So from the student table, we need a roll number. So that is what roll number. And after that, what we need from the course table, we need course name actually. So that is what asking, display the roll numbers and course names of each student. So what is the output actually here? That is very simple that, so student roll number, student dot roll number, course name. So under these two attributes, what values we are getting? So here A is their course ID basing on this condition. This A is matched with this one. So that means roll number is 1 and here course name is DS. So student number 1 taken data structures actually DS course. And then next here B matched. So that is what student number 2, that particular records in both the tables taken DBMS course actually. Okay, then here A actually again. So this is matched with this record. So that means student number 3 taken DS. And here C, course CID, course ID is C, here it is C, OS. So that is what student number 4 taken operating system. So this is what the output from this statement actually. Is it clear? So if you see further deep in the SQL, how you will write down this one, same thing. So that is very simple, right? So select student dot roll number, comma, course dot CNAME. These are the fields required. These are the attributes you want to display from which table actually? From student table and course table. Then these two Cartesian product is going to happen, but from that, which rows only required? Where? So student dot CID, course ID must be equal to course dot CID. This is corresponding SQL statement. So this is a relational algebra expression. Equivalent SQL is this one actually. But for both, result is same, this one. So now let us take one more example to increase little complexity actually. So that is, here you can see, display the roll numbers and course names of each student who got more than 65 marks actually. So one more condition extra you are adding for this. So this is also simple. First of all, let us take both the tables. So that is student. So that you are joining with course, and what is the condition? Here condition. So first of all, you have to match this CID and this CID. So that is nothing but student.cid. In the student table, CID must be equal to course table CID. After that, that is what AND operator actually. After that, here marks must be greater than 65. So we are using another operator here, greater than 65. So it need not be always equal actually. So that is what student dot marks. This must be greater than 65. So two conditions we are putting here actually. On this result, from this result, what we need actually, roll number and course name. So that is what student dot roll number, comma, course dot course name, C name. So this is the equivalent statement actually, very simple. Okay, so if you write, it's a corresponding SQL statement. So nothing is there here. So here we are going to put one extra condition in the where clause. That's it. Okay, so I'm just writing that extra condition. So that is and after that. So that means whatever here we have, everything is there. After that, and student dot marks must be greater than 65. So that's it. So this whole thing, after this, you just add this one. So in this way, actually, conditional join or theta join we are using actually. So don't forget that any operation if you are using in the where clause, that means here if you are using condition by using comparison operators, then that is coming under conditional join. So basing on one particular condition, you are joining them actually. So that is also called as theta join. Okay. Hi. So now let us see the next one, equijoin. So this equijoin is very simple. We already learned in the previous discussion actually. So let us see just for formality. So here actually in the theta join, if you are using always equality symbol, then that is actually a equijoin. So there is no big thing about the equijoin actually. So actually we have all comparison operators, right? So, but here, if you are using only equal operator, that is what the equal operator only if you are using, then that is going to become equijoin actually. So for example, same query, if you take roll number and course of each student we need. So at that time, what we written actually, student, and we are joining this with course. So here, what is the condition? So condition is student dot CID, course ID. This is what equal. So we are using the operator. What comparison operator we are using? Equal course dot CID. That's it. So upon this result, what we need actually roll number and course name. So roll number is from the student table. So student dot roll number, and course name is from the course table actually. So that is what course dot cname. So the only thing is this query we already seen earlier. The only thing is if you are using the equal operator in the condition part, then that is going to become equigiant. So there is no big thing about this part actually. Okay. Hi. So now let us see the next join, that is natural join. Okay. So what is this natural join? So this is very simple actually. So let us see first of all, natural join does not use any comparison operator. Very, very important thing. You are not going to put any condition actually. Then how it is going to perform the join operation and how it is returning the values. So let us see. So we can perform natural join if only if there is at least one common attribute exist in both the relations actually. So there must be at least one common attribute. So that is what you can see in the student table and the course table. What is the common attribute? CID is the common attribute. So CID is common in both the attributes, right? In the both the tables. So that is what at least one. So one attribute is there which is common. But we have one constraint on this common attribute actually. What is that one is, you can see here, same name, that is what in both actually same name CID and domain. So domain is nothing but it's a data type. So if it is integer, this must be integer. If it is float, this must be float. Simply you can say compatibility must be there. Okay, so compatibility must be there here actually. Then only you can perform natural join. Okay, so very simple that how many common attributes satisfying these two, same name and domain, on all those attributes, you are putting automatically equijoin actually. Okay, so how let us see here, simple. So the same query I'm taking, display roll number and course name of each student. So how simply in the natural join we are going to do, you can see here. So this is what student natural join on course. That's it. But what is happening internally? Internally, in the student and course, it will identify that who are all common attributes. So identified CID is one common attribute. Then internally, automatically it will perform student.cid equal to course.cid condition automatically putting. That is what equal condition only, not any other conditions. That means other comparison operators are there, right? Greater than, less than, all these things it is not putting by default, and only equal operator is putting on the common attributes in the both the tables. Suppose if you have more than one common attribute, how many common attributes are there? On all those common attributes, it is putting the equijoin and connector is AND operator. So because we have AND or logical operators, right? So how many conditions? If you have two conditions, that means if you have two attributes are common in both the tables, then two conditions it is going to frame, right? And between them, it is putting AND operator. That is what my meaning. Then, so that is what internally this much work is happened in this. So automatically you have only whoever matched this condition. Those records only we have here. That is one relation. On this relation, what we need actually, we need only roll number and course name. So that is what again, student.roll number and course name. So that is what course.cname. So only these two attributes were written. So this is useful. If natural join is useful, naturally, whenever common attributes are there in the both the tables, and if it is satisfying this one, especially domain part, then you can go for the natural join. You don't need to write down explicitly the condition part. And not only that, how many attributes are common in the both the tables, That many conditions it is framing by using the equal operator, and between every condition, it is going to put the logical operator and actually. So this is what simply the natural giant. So that is why its name is natural. Whenever common attributes are there in the table, and if your requirement is whoever matched actually, that means equal join you are equi join you are performing internally. Okay. Hi. So now let us see next kind of joins, that is outer join. Okay. Before going to see what is actually this outer join, let us see something opposite to this part actually. So that is what we already seen, that theta join, equi join, natural join. So these three joins actually have one similarity. So that is these three we are actually calling as inner join. Okay. Why it is inner join? Okay, so these three actually, whether it is theta join or equi join or natural join, we are going to put a condition. Whichever record satisfying that condition, only those records in the output it is returning actually. So that is what inner join. So if you see its a definition, an inner join includes only those tuples or rows with matching attributes, and the rest are discarded in the resulting relation. Whichever not matched actually, whichever not satisfied the given condition, those are not returned actually. That means those are not coming in the output. So whichever tuples, that is nothing but rows or records, matched, those only including in the output actually. So that is why it is called inner join. Now, just quite opposite to the inner, this is outer. So now let us try to, it is easy to understand what is outer join. So now you can see here, this part is same, okay, including the tuples which are matched. That is same even in the outer join. But what is the extra thing? You just understand. So outer join includes not only tuples with matching attributes and also rest tuples correspondingly. That means whichever not matched also, it is including in the output actually. But very important word here is correspondingly. So this correspondingly meaning we will see in the discussion. So which tuples it is going to display in the output, which tuples is not going to display in the output, though they are not matched with the condition. So again here also in the outer join, we have three outer joins are there. One is left outer join, another one is right outer join, and one is full outer join. Okay. So let us try to understand all these three in a simple manner in the coming lectures actually. Okay. So simple that inner join gives the result which are satisfying the condition. And in the outer join, not only satisfied records, the condition whatever is there, not only satisfied records, and also some of the records it is going to return in the output correspondingly actually. So that we will understand basing on these words, left, right, full. Okay, so now let us see in the next lecture, left outer join and remaining actually. Hi. So in the last lecture, we've seen that what is outer join. Now let us deep dive further. So in that, the first one is left outer join. Okay. So this is very simple. Let us take here two relations. So two tables we are going to take, R and S. First of all, left outer join we are going to represent like this. So this is normal join symbol. For that, left side you are giving these two bars actually. So what is this meaning actually? Left side why we are representing? So remember that this is the left side table and this is the right side table, or left relation or right relation. Okay. Now, so you can see all the tuples from the left relation, that is what are going to included in the resulting relation actually. So we are going to get the output, right? In the output, how many records are there in the R? all of them are going to be there, whether they are satisfying the condition or not. That is very important. Left side. So what about in the right side? If there are tuples in the R without any matching tuples in the right relation yes, so whichever not matched in yes, then the yes attributes of the resulting relation are made with null values actually. So first of all, simple thing is here, left to outer join means left side whatever table we are going to have, whatever relation we are going to have. How many rows are there originally in that relation? All records definitely going to be there in the resulting relation. That is what you are ensuring. That is why it is left. So left side you are covering completely, and right side which are matched, those only you are taking. Now for not matched records, you are placing the null value. Let us get the more clarity with a simple example. So here you can see we are going to take a table, student table, where student name, roll number, name, and his course ID, what course he taken. And here two students didn't taken any course. So let it be. Let us take another relation, that is course ID and its corresponding name. So that is what here we have. Now if you observe, we are going to have this relation, that is I'm going to put a left outer join, that is R, and here we have that symbol and right symbol yes. But you must place the condition here. What is that one? So here actually not R yes, right? So here actually this is student and course relation. So that is why let us take correspondingly only. So student relation, student, and so here we are going to take a left outer join. So take corresponding symbol, and right side table is course. Now what is the condition? This is normal. First of all, condition is like a normal join only. So we want to put student dot cid equal to course.cid. So this is what its output we need actually. Okay, then what is going to happen? You just see here, whoever satisfying this condition, for example, student.cid A matched here. So this row is going to come, and B matched here. So this row is going to come, and A matched here. So this row is also going to come. Now here, this is matched. But you see, here you don't have anything actually. So that means these two students not taken any course. But because it is a left outer join, this is the left side table actually. Student is the left side table. So these two records are also coming in the output. And correspondingly, under these two columns, we are going to have null values. Let us observe that output now. So you can see here. So this is what the output for the above query actually, for this statement. So you can see correspondingly wherever match is there, all those records you got. So these four records are matched records. So these four records, if it is not a simple join, these four records are going to come in the inner join also. But here, these two records don't have match. So at that time, what is going to happen actually? Here we have a null value. So it is empty, meaning is we have default null actually. So that is what actually left outer join. If this is clear, understanding right outer join is very simple, right? So first of all, this is what the left outer join. Always left side relation going to have all the records in the result, whether they are matched or not. And the right side relation records, whichever matched, only those are going to come in the output. Okay. Hi. So now let us see right outer join. So because we completed already left outer join, so you just quite oppositely think about this one actually. So this is very simple one. So now we are going to select all the tuples from the right side table actually. So that is why you can see the bars are now right side. So whatever rows are there in the yes, all rows must be there in the output, and but from the R, only matched records must be there in the output. That is what, right? So that is what it's meaning. All tuples from the right relation, that is yes, are included in the resulting relation. And what about the left side? Left side which are not matched, for them we are placing null value. So that is what, just opposite to the left outer join. So if you take the same example, but the only thing is, if you apply right outer join, so that is what actually we have a student table. So student, and here we are applying right outer join for the course. So right side, whoever is there. So right side we have a course table actually. That means all the records in the course table must be there in the output. And what about the condition? So if you take the condition must be there. So student dot cid equal to course dot cid. See, and one more thing here, need not be always equal symbol. It may be any comparison operator. Okay. So ultimately, whatever condition you write here, that is what actually. Whoever satisfying those records, anyhow, it will come in the output. And basing on the outer join, which side, whether it is left or right side, basing on the corresponding tables records are going to come in the output. And because it is right outer join, so all records from the course are going to be exist in the output actually. So if this is our the relational algebra statement, then what is the output that you can guess actually now? So that you can see. So you see here CID from the student table, course ID from the course table, matched. So whatever matched, those records anyhow there, that is like a inner join. And because it is right outer join, right side table remaining attributes. So remaining attributes, these two attributes don't have any match actually. So those two we have here. So this is what actually right outer join. So in simple manner, we can discuss that. Okay. If you understand left, understanding right is very simple. Okay. Hi. So now let us see the last one in the outer joins. That is full outer join actually. So we already seen that left outer join and right outer join. So full outer join is nothing but combination of both actually. So let us try to understand what is this one. So this is what the symbol we are using for the full outer join. So that you can observe for the normal join, both the sides you have the bars actually. So what does it mean? All tuples from the left relation, all tuples from the right relation must be there in the output along with matched records. Is it? So that is what actually you can see. So all tuples from the both participating relations we are going to include in the resulting relation actually. That means in the output we are going to have total records actually. So if there is no match, whenever no match is there, as usually we are going to place null values. But this is little different actually. You have to combine the both the results. So how it will be, let us try to understand with this simple example. So same tables we are going to consider, student table and course table. Now, first of all, we are going to take a student relation, and upon this we are going to have a condition join operation is full outer join, and right relation is course. So what is the condition actually? So we are going to put a condition, that means we are joining them with cid in the both the relations. So that is course dot cid. Now whoever satisfies this condition, of course those records will come in the output. and which are not satisfied from the left relation, those also will come in the output, and which are not satisfied from the right relation, those are also coming in the output. So that is what you can see the output here. So these are the records which are matched that you can observe here. All of them are same. This is student DCID, course CID, values are matched. But for not matched records, what is happening? These are from the left relation. And in the right relation cells, what we are placing actually null values. And these are from the right relation. So these two only not matched. So those two you taken actually directly. And for this, in the left relation part, we are going to place null values. So that is what actually you have to understand. Okay, so that means both the sides you are applying the outer join, so that from the both the relations which are not matched, those are also coming in the output actually. So this kind of requirement is also sometimes will be there. So that is the reason we have a full outer join. So that is what overallly outer joins is nothing but not only the matched records, not matched records are also you can take into the output basing on the requirement. So that is what if it is left outer join, left relation records, all of them you must have in the output. If it is a right outer join, right relation, right side whichever relation or table is there, all those records are going to include in the output actually. And if it is a full outer join, both the sides relations, tuples, all of them going to exist in the output. So this is what overallly outer join, that is nothing but left, right, full outer joins.